will be a star freelancer. Learn new skills. Set your goals. Increase your skills. Browse over 100 plus videos and ebooks. Jump to starfreelancer.eu.
So in the previous video, we talked about using the switch statement. In this video, we're going to move on now to talk about the for statement, which will be the first of the looping statements we'll look at. Now, we haven't really looked at that before, but looping is something that is very commonly needed in programming, and it lets us execute code a multiple number of times. So there are several looping statements in Java. These statements will continue to execute a block of code repetitively until a condition or some set of conditions is met. In this section of the course, we'll be looking at 3 loop statements. The for loop is probably the most common and the one we'll look at first. It includes setup to initialize variables, check a loop expression, and update code, which often includes incrementing an iteration variable. The while loop might seem simpler because it will just continue to execute code until its loop expression becomes false. And the do while loop is like the while loop, except that it will always execute the code once, regardless of whether the loop condition is true or false, and then continue looping until that expression is false. The for statement is often referred to as the for loop, and the idea is that it repeatedly loops something until a condition is satisfied. When I say repeatedly loops, I mean it's processing a certain amount of code, a code block in other words, a given number of times, or until a particular condition is satisfied. There are 3 parts to the basic for statement's declaration. These are declared in parentheses after the for keyword and are separated by semicolons. These parts are all optional and consist of the following. The initialization section declares or sets state, usually declaring and initializing a loop variable before the loop begins processing. The expression section, once it becomes false, will end the loop processing. The increment section is executed after the expression is tested and is generally the place where the loop variable is incremented. I've set up a project called the for loop and the usual main class with the main method. Let's look at a simple for loop in code. Let's loop from 1 to 5 and print those numbers out using the for loop statement. For, opening parentheses, int counter equals 1, semicolon, counter less than or equal to 5, semicolon, counter plus plus, closing parentheses, opening curly brace. System.out.println, opening parentheses, counter, closing parentheses, semicolon, closing curly brace. So looking at this code, the initialization part of the for loop is the declaration of a variable named counter and initializing it to 1. The expression is counter less than or equal to 5. This means that if the variable counter is ever greater than 5, the loop won't continue. The loop terminates at that point. The increment section is an expression we've seen before, the postfix increment operator. This will increment the counter after each iteration of the loop. So executing this code simply prints out the numbers 1 through 5. So that's kind of fun and easy, and that's the basic for loop statement in its most common form. Okay, so let's emulate a more practical usage for it. We're going to start off by creating a new method and call it calculate interest. So this is going to calculate the interest based on the amount of money that's passed as a parameter. Now, one way to do this is to add code as follows. Public static double calculate interest, opening parentheses, double amount, comma, double interest rate, closing parentheses, opening curly brace. Return, opening parentheses, amount times, opening parentheses, interest rate, divided by 100, close both parentheses, semicolon, closing curly brace. So we put a parentheses in the calculation expression just to make sure from an operator precedence point of view that we're processing it correctly, and that we're actually figuring out the amount, then multiplying it by the interest rate divided by 100. This ensures things are being calculated in the right order, and just to confirm this is working, we're going to create sample code in the main method to call this calculate interest method. System.out.println, opening parentheses, double quotes, 10,000 at 2 modulo interest equals plus calculate interest, opening parentheses, 10,000.0, comma, 2.0, close both parentheses, semicolon. So let's run this and make sure that it does work. We got the result 10,000 at 2% interest is equal to 200. So this is just a simple contrived example of calculating interest on an amount of money and doesn't include compound interest or anything like that. This is one way to do it, but let's just say we want to calculate 3%, then 4%, and also 5%. So we could copy this statement in the main method and paste it like so, changing 2 to 3 in the statement, first the 3%, then the 3.0 value. And we could do this several more times for 4% and 5% interest calculations. You can imagine if you had to do this every time you wanted to calculate different interest rates, it would be, as I said, tedious. And what about if we had 20 interest rates or 100 interest rate calculations? Well, the good thing here is that computers are made for automation, so there's a good solution to getting around this problem. And that's using a for statement to automate this process and ultimately to make it a lot easier now. We've already seen the for loop in action, so here we want to replace these for statements using the for loop. Okay, so how do we do that? First, look at the parameter that's changing in each of these statements, the interest rate. It's changing from 2 to 3, 3 to 4, and 4 to 5. So we know our starting point is 2, our ending point will be 5, and we're incrementing by 1 each time. So let's delete those 3 extra statements we pasted in there earlier. And now let's create the for loop that does that. For, opening parentheses, double rate equals 2.0, semicolon, rate less than or equal to 5.0, semicolon, rate plus plus, closing parentheses, opening curly brace. Double interest amount equals calculate interest, opening parentheses, 10,000.0, comma, rate, closing parentheses, semicolon. System.out.println, opening parentheses, double quotes, 10,000 at plus, rate, plus, double quotes, modulo interest equals, plus, interest amount, closing parentheses, semicolon. Closing curly brace. So remember that the first section in parentheses is the initial part of the for loop. It gets executed before the loop starts processing. This is where we're creating a variable of type double and calling it rate. And we set it to 2.0 to start. Next, the condition needs to check to make sure the rate is less than or equal to 5.0. That is the second part of the declaration. And finally, we'll increment the rate by 1 after every loop iteration. And notice we created an extra variable called interest amount, a double assigning it to the result of the method call. This simplifies the println statement, so instead of hard coding the value 2.0 there, we change that to pass the rate variable. Rate is the variable which is changing on each iteration. And we replace the method call in the println statement with that new variable interest amount. And if we run this code, we can see the interest for each rate printed out. 2% gives us 200, 3% is 300, and so on. So we've used the loop variable, the interest rate, and printed that out, but we also used that rate as an argument to the calculate interest method. Okay, so now I've got a mini challenge for you at this point. Using a new for statement, call the calculate interest method with the dollar amount of 100. And this time, use the interest rates between 7.5 and 10, but increment by 0.25% each time, meaning 0.25%. And print the results to the console window. Okay, so pause the video and add that code, and when you're ready, come back and see how I code this. So how'd it go? Were you able to figure that out? So for this challenge, we have to ask ourselves what's changing each time. So the rate is changing, increasing by 0.25% each time, and we're starting at a rate of 7.5% and ending at 10%. That's all we need to know to set up the conditions of the for loop. So let's start adding this code. For, opening parentheses, double I equals 7.5, semicolon, I less than or equal to 10, semicolon, I plus equals 0.25, closing parentheses, opening curly brace. Double interest amount equals calculate interest, opening parentheses, 100.00, comma, closing parentheses, semicolon. System.out.println, opening parentheses, double quotes, $100.00 at plus, plus, double quotes, modulo interest equals dollar plus interest amount, closing parentheses, semicolon, closing curly brace. So now you might be wondering why we're using the variable name I. We used the variable rate before, and it made some sense when reading the code. I think I've said before that a variable should be named so that the reader of the code has some idea what your code is doing. Obviously, the letter I doesn't seem to do that. And that's true, but in Java and many other languages, I is short for the iteration variable, and you'll see the lowercase letter I used in many loops, as I'm showing you here. You'll also see lowercase j and k used quite a lot as well, especially when there are multiple loops in the code. So whether you use a variable name like rate, like we did before, or just the letter I, as we're doing now, it's your choice. But I wanted you to get used to seeing just the letter I as the loop variable, because this is very common practice in many languages. Next, you can see we're looping from 7.5 to 10 and incrementing by 0.25. We create the variable I as a double and set it to 7.5 in the initialization section. In the loop expression, we check if I is less than or equal to 10, and in the increment section, we use the compound operator to add 0.25 to the variable I for each iteration. Next, we create a local variable for interest amount, and we call the calculate interest method, passing the loan amount of $100 and the loop variable as arguments. And then we print all that out using some dollar signs and our variable in the print statement. Let's first run that. And we can see that the interest amounts range from $7.50 to $10. Okay, so that was the mini challenge. Hopefully you were able to get that. And that was just one of many ways to code the for loop. So next, let's add one more requirement so I can introduce you to another feature of looping. Let's say we only want to print the statement where the calculated interest is less than or equal to $8.50. So, in other words, we want to loop through interest rates from 7.5 to 10, but quit or exit out of the loop if the interest amount ever gets to be more than $8.50. So, how do we do that? Well, one option is to use the break statement. A break statement transfers control out of an enclosing statement. We've seen the break statement in the switch statement, but it can also be used in a loop. A break statement is generally used in an if statement, testing some condition on which to break out of the loop, which is different than the loop expression. So let's code our loop using the break statement. We'll add an if statement after the call to the calculate interest method. If opening parentheses, interest amount greater than 8.5, closing parentheses, opening curly brace. Break, semicolon, closing curly brace. And if we run that, we can see we only get output up to the point that our interest amount in dollars is $8.50, which is what we wanted. So the break statement can be used to break out of a loop, in this case, before the declared loop expression ever evaluates to false, meaning before I ever gets to 10. So the code stops executing the loop here at line 17 at this break statement when the interest amount is greater than $8.50. The code below it on line 19 won't get executed after the code breaks out because now the process has gotten completely out of the loop and skips anything in the loop block below it. Okay, so that's it for the for loop and the break statement. I hope you got a lot out of that. In the next video, we'll give you another challenge with for loop statements. So in the previous video, we talked about the for statement, and in this video, I want to give you another challenge to work out on your own first, then we'll get back together and work through the solution. This challenge will use prime numbers, so if you need a refresher, let's quickly look at a website called Maths is Fun. The link to this page will be in the resources section of this video. It gives the simple explanation that a prime number is not a composite number, meaning it cannot be made by multiplying other whole numbers. Another way to think of it is that a prime number is only divisible by itself and 1. And as you can see there, it lists the prime numbers under 1000. So, for example, the number 7 cannot be divided by any number except 1 in itself. That'll produce a whole number, so it's a prime number. 7 divided by 1 is 7, and 7 divided by 7 is 1, which are both whole numbers, but any other number will result in a decimal number. Whereas 9 can be divided by 3, which equals 3, a whole number, and therefore it's not a prime number. The number 1 is not considered a prime number, but the number 2 is. However, any other number divisible by 2 is not a prime number. That's a super simplified explanation for those of you who hate maths. Don't worry, I'm not going to ask you to create the prime number method on your own. We'll walk through that first, and then we'll use that method in the challenge when we're done. So first, create a project called the Prime Number Challenge with a main class and a main method. Before we do anything else, we're going to create an isPrime method. This method has some great opportunities for reviewing some of the material we've covered, so I want to walk through it with you step by step. First, let's create the method declaration, what I've called a shell declaration in the past. Public static boolean isPrime, opening parentheses, int, whole number, closing parentheses, opening curly brace. Return true, semicolon, closing curly brace. So it will be returning a boolean from this method, true if the number passed as the parameter is a prime number, and false if it isn't. So the parameter name is whole number, and I've used isPrime as the method name. You remember that when declaring Boolean variables, we sometimes used it as a prefix in the variable name to form a question. This same thing is often done with method names, and that's what we're doing here. Right now, because this method isn't really operable, we'll just return true. So let's next set up some simple test cases in our main method. We'll test the numbers 0 through 3 to start with. And here's a decent opportunity to use the ternary operator. If the number is prime, the text will say is a prime number, and if the number is not prime, then the text will say is not a prime number. I'm going to type out the first line, then I'll copy and paste the rest. System.out.println, opening parentheses, double quotes, 0 is plus, opening parentheses, is prime, opening parentheses, 0, closing parentheses, question mark, double quotes, colon, double quotes, not, closing parentheses, plus, double quotes, a prime number, closing parentheses, semicolon. So you can see we're calling the method here, passing it the number 0 on the first line and 1 on the second line, and so on. And this is making the call to the isPrime method from the first operator, the ternary operator, which uses the question mark and colon. So if true comes back from that method, we're really concatenating an empty string, but if it's false, we'll slip in the word not in the text. As I've said before, this may not be the most efficient code because of the immutable string, but for now, it's a way to exercise the skills we've learned so far. Okay, so because our isPrime method right now always returns true, this code, when we run it, will indicate that all of these numbers are prime numbers. But we've got 4 test cases set up ready to go as we build up the isPrime method piece by piece. So let's go back to that. First, we'll check if the number is less than or equal to 2 with an if-then statement. If it's less than or equal to 2, we want to return false if the number is negative, 0, or 1, because these are not prime numbers. If the number is 2, however, we want to return true because 2 is a prime number. So we can do this by returning the value that will be returned from the Boolean expression whole number equals 2 using the double equals sign here, the equality operator. If opening parentheses whole number less than or equal to 2, closing parentheses, opening curly brace. Return, opening parentheses, whole number equals 2, closing parentheses, semicolon, closing curly brace. Okay, so now let's see where we're at and run that with our 4 test cases. So that's good, actually looks right, but not for all the right reasons. We've really only addressed the numbers less than or equal to 2 so far. Let's add a couple more test cases in preparation for some more code. First, we'll add a test for the number 8, which we know isn't prime since it's divisible by 2. We'll also test the number 17. Okay, so we've set up some test cases, and now back to our isPrime method again. This is where the fun starts to happen because we get to use a for loop statement next. So you'll remember to set up a for loop, we need a starting point, a condition to stop at, and a way to increment the variable that we're checking. So let's have this for loop. For, opening parentheses, int divisor equals 2, semicolon, divisor less than, whole number, semicolon, divisor plus plus, closing parentheses, opening curly brace. Closing curly brace. So we create a variable called divisor. This is the number we'll be dividing the whole number by. We'll keep looping if the divisor is less than whole number. If we used less than or equal there, instead of less than, then we'd have the condition that whole number would be divided by itself at the end, and it would then say that the number was not prime, which would be wrong, so make sure this is just the less than symbol by itself. And then we'll increment by 1 each time, so the postfix operator will do the job for that. So thinking about our test case that has the number 8 as the whole number, for example, we'll be looping from 2 to 7, incrementing by 1 each time. And what do we want to check each time? Well, we want to know if the whole number is evenly divisible by that loop variable, which we're calling divisor. What operator can we do this with? The remainder operator, or modulo, modulus operator, whatever you like to call it. So let's add that code. If opening parentheses, whole number, modulo, divisor equals 0, closing parentheses, opening curly brace. Return false, semicolon, closing curly brace. So here we have an if statement that checks if the whole number is divisible by the loop parameter, which we're calling divisor. If our whole number can be evenly divisible by any number other than itself, so that is any number between 2 and 1 less than its value, then that means the whole number can't be a prime number. In other words, we found a number that evenly divides into whole number, which means whole number isn't prime. We start with 2 because everything is divisible by 1, so starting with 1 would give us false positives. But notice that every even number will return a false on the first iteration of the loop, so that's pretty efficient. Note also that we're just putting a return in that if code block. This will exit the loop at that moment when that condition is true, breaking out of the loop and exiting the entire method, returning false. So this lets us get out of the loop as soon as possible because we don't want to continue in the loop unnecessarily. So let's test that. There are other ways we could program this, but this is a pretty easy way to get your answer and get out of the loop, and subsequently the method. When you're using loops, it's a good idea to see if there are any ways to cut down on iterations, especially if the code block that's being executed is complex or creating a lot of variables. One minor thing we could do is change the code to iterate over less values. We could use the halfway mark for a number as the maximum value. Let's make those two minor changes, changing less than to less than or equal to, and whole number to whole number divided by 2. So think about why this is more efficient for a minute and why it should still work. Anything that is divisible by the smallest number, 2, will also be divisible by that whole number divided by 2, so checking numbers greater than half the whole number is really just wasted effort. And running that gives us the same results. Now, there are even more efficient ways to write this code, but we haven't yet picked up those skills, and truthfully, you aren't likely to be coding this method since Java has a method on one of its classes that you can use to check prime numbers. So that looks pretty good. This exercise lets us review the ternary operator, the remainder operator, and also practice using the for loop, as well as talk about method names for methods returning Boolean values and looping efficiencies. So now it really is time for your challenge. Create a prime number counter variable that will keep count of how many prime numbers were found. Create a for statement using any range of numbers where the maximum number is less than or equal to 1000. For each number in the range, check to see if it's a prime number using the isPrime method. If the number is prime, print it out and increment the prime number counter variable. Once the prime number counter equals 3, exit the loop, int, use the break statement to exit. Your challenge is to create a for statement using any range of numbers to determine if the numbers are prime numbers. You use the isPrime method we've just worked on. If it's a prime number, print it out and increment a count of the number of prime numbers found. If you get to the stage where 3 or more prime numbers are found, end the loop. In other words, you'll be iterating through the loop, but you've found 3 prime numbers before the range is fully processed. I want you to exit the for loop, and as a hint, use the break statement to exit. So you need to use an if statement to check the count and use break to get out of the loop even before it completes processing all the numbers in the range you picked. So that's it. See if you can figure that challenge out. Pause the video and do that. Once you're ready to see my version of the code, come back and we'll walk through my solution together. Pause the video now. Okay, so hopefully you managed to get it to work. So go to the main method. I'm going to delete all of the code that's there now. And now let's start with the challenge code. The first thing we need is the prime number counter. We'll just call this count and we'll initialize that to 0. Int count equals 0 semicolon. So now we need to create a loop to go through and call the isPrime method a number of times. You'll remember the range of numbers was yours to pick. I'm just going to use the range 10 to 50. So let's build out the loop code block. For, opening parentheses, int I equals 10, semicolon, I less than or equal to 50, semicolon, I plus plus, closing parentheses, opening curly brace. Closing curly brace. Okay, so this code will start with the number 10. It gets assigned to an int variable called I when the loop is initialized. Remember, it's common practice to use I or j as a loop iteration variable, and that's what we're doing here. So this loop starts out with the number 10, and it will keep looping until the number gets to 50. I've made the condition less than or equal to, so this loop will also process the number 50 if nothing else is included in the code block. And this code will increment the variable I by 1 each time. You can increment by any number you want, but of course, we want to increment by 1 here, so we check every number in the range we've selected. So we've set up our loop conditions. Now it's time for the loop to do something. So let's add the code that checks if the number is prime next, and we'll increment our prime number counter. If opening parentheses is prime, opening parentheses, I, closing parentheses, opening curly brace. System.out.println, opening parentheses, double quotes, number, plus, I, plus, double quotes, is a prime number, closing parentheses, semicolon. Count plus plus, semicolon, closing curly brace. System.out.println, opening parentheses, double quotes, total number of prime numbers between 10 and 50 is plus count, closing parentheses, semicolon. That last line wasn't part of the challenge, but we'll just print how many prime numbers are in our full range first. And if we run that, we get each prime number between 10 and 50 printed out, and we see there are 11 prime numbers between 10 and 50. But that's not what the challenge wanted us to do. It wanted us to break out of the loop when we found the first 3 prime numbers. Okay, so let's do what we're supposed to do. I'm going to remove that last statement where we printed out the total prime numbers in the range. And now we'll add our check to see if we found 3 prime numbers. And if we did, we'll break out of this loop. If opening parentheses count equals 3, closing parentheses, opening curly brace. System.out.println, opening parentheses, double quotes, found 3 minus exiting for loop, closing parentheses, semicolon. Break, semicolon, closing curly brace. So let's run it again and see whether it works. And you can see we print the data for the first 3 prime numbers only, and we get the statement found 3 exiting for loop. So it seems to be working, which is good. So that's our challenge done, and the big thing there again was once we got to the count, when the count got to 3, we decided we wanted to exit the loop prematurely. And we did that with a break. And the break actually exits out of the for loop completely and stops processing at that point, meaning the high iteration variable never made it to 50. It stopped at number 17. We actually didn't have to use a break at all, but I wanted you to get a little practice with the for loop. You can make the loop expression as complex as you want and use variables declared outside the loop. So if we did do this without the break statement, we could replace that middle part of the loop statement where it's checking if I less than or equal to 50, we could add our second condition there. So let's just do that real quick. Let's remove the whole if block on line 11 first. Then we'll change our loop expression and add the condition count less than 3 with logical AND operator. And running that, we can see that it works. It just doesn't print the statement that we broke out of the loop when count was 3. Okay, so that wasn't in the requirements, but it's another way to check for the first 3 prime numbers only. And so that was the for loop challenge. Congratulations if you got that working, and I hope you enjoyed that exercise. In the next video, we'll look at another loop statement, the while statement. So I'll see you in the next video. All right, it's time for another challenge. This is the sum 3 and 5 challenge. So the challenge is to create a for statement using a range of numbers from 1 to 1000 inclusive. You want to sum all the numbers when you're looping through that can be divided with both the number 3 and also with 5. And for those numbers that meet the above conditions, in other words, that are found to be divisible by both 3 and also divisible by 5, you want to print out that number. You also want to break out of the loop once you find 5 numbers that meet those above conditions. And then finally, after breaking out of the loop, print the sum of the numbers you found that have met those above conditions. And for this one, just type all your code into the main method. Now the text for this challenge is in the resources section of the video, so you can go ahead and download that if you need to. At this point, pause the video and see how you go with that challenge. Once you're finished, come back and you can check out my solution. So pause the video now. Alright, so how did you get on? Hopefully you managed to solve that challenge. So in this video, I want to do something differently. I'm still going to type in my solution, and instead of talking about it too much while I'm typing it in, I'll be adding my code, and then we'll be using IntelliJS Debugger to really walk through what's happening. I'll use the debugger to explain the code line by line, but even better, we'll be able to explore what's happening while the code is executing. I've started a new project for this and added both a main class and a main method, as you can see on screen. So first, we'll set up 2 variables we'll need. One is for the count of matches, and the second is the sum of the matched values. After that, we'll set up our loop, which we know should go from 1 to 1000, incrementing by 1 each time. So let me get that code in here. Int count of matches equals 0, semicolon. Int sum of matches equals 0, semicolon. For, opening parentheses, int loop number equals 1, semicolon, loop number less than or equal to 1000, semicolon, loop number plus plus, closing parentheses, opening curly brace. Closing curly brace. System.out.println, opening parentheses, double quotes, sum equals, plus, sum of matches, closing parentheses, semicolon. That sets up our loop to cycle through numbers 1 through 1000, one at a time. I also included the final print statement. So now, in the loop, we want to check if the loop number that's iterating from 1 to 1000, is divisible by both 3 and 5. So we'll have that if condition. If opening parentheses, loop number, modulo, 3 equals 0, closing parentheses, logical AND operator, opening parentheses, loop number, modulo, 5 equals 0, close both parentheses, opening curly brace. Closing curly brace. That's our matching criteria, so if that's true, we're going to do the work, which is count the matches, then add the actual number to our sum variable. So let's add that next. Count of matches plus plus, semicolon. Sum of matches plus equals loop number, semicolon. System.out.println, opening parentheses, double quotes, found a match equals plus loop number, closing parentheses, semicolon. So if we found a match, we increment the count of matches variable by 1. And then we add the matching number, the value in loop number, to our sum of matches variable. And we'll print out that we found a match. So the only thing that's left is to get out of the loop if we find 5 matches. If opening parentheses, count of matches equals 5, closing parentheses, opening curly brace. Break, semicolon, closing curly brace. So if our count of matches reaches 5, then we break out of the loop. Okay, that's the full code. And if we run this code, you can see in the output, we've got found a match equals 15, 30, 45, 60, and 75, and sum equals 225. So that's it. That's the first 5 numbers that can be divided by both 3 and 5 without any remainder, and then the sum of those 5 numbers that are outputted is 225, which is correct. So now, as promised, let's examine what's happening each step of the way, and we'll do that with IntelliJ's debugger. IntelliJ IDEA provides a debugger for Java code which lets you see what's happening under the hood. IntelliJ provides pretty good documentation about using their debugger at the web page shown here, so let's go to that page and see what IntelliJ has to say about its Java debugger. And we can read that IntelliJ IDEA provides a debugger for Java code. We don't have to include any plugins to use the debugger for Java. It's already all set up and ready for us to use. And we can read that we can launch our program with the debugger attached to it. And that gives us access to information on what's happening under the hood. You'll see that there is a lot of information about using the debugger here, and I wanted to show this to you so that after this session, if you want to learn more, this is a really good place to start. But some key concepts you'll need to understand first are breakpoints. And IntelliJ describes breakpoints as special markers that suspend program execution at a specific point. We can toggle breakpoints on at any line in our code, and then, when we execute the code in debug mode, if the code reaches the breakpoint line of code, the process will suspend itself. And the process will stay there, suspended indefinitely, until we tell it to resume in some way or we stop the debugging process. This suspended state lets us examine the internals of the code while it's still running at the very point of code we set the breakpoint. We can see the state of our variables, evaluate expressions on the fly, and much, much more, as you can see from the numerous options shown here on this navigation pane. You'll also see that there are several tutorials available for you to try here as well. Okay, so that's IntelliJ's introduction, but let's walk through the basics together using the code we just created. You can run the debugger several ways. But before we even do that, let's add some breakpoints. The easiest way to do this is to find the lines of code you're interested in pausing at. For us, for this code, I think one logical place to put a breakpoint is on line 8, where the loop will start, iterate, and test the loop condition. And to set a breakpoint, you can simply click here in the grey area to the right of the line number, and you can see that now displays a red circle. That's the indication that we've set a breakpoint. Now that we have a breakpoint, there are several ways to run this code in debug mode. We can right-click on the editor pane, and instead of selecting Run, we can pick Debug right under it. We could simply use that debug icon in the right top part of the IDE window. It's to the right of the Run icon. We could click on the Run icon to the left of the main method in the editor window, and this also gives us the option to debug. And there's also a shortcut for it for me using Windows, that's Shift F9. So whatever way you choose to debug the code, let's just start the debugger up. When we do start it, you'll notice that we have a debug tool window displayed now. There should be 3 separate windows. If you don't see the third one on the right, come over here to this icon and click on it. Then you want to come down here and click on Separate Watches. Okay, so our code started running then was suspended, and here you can see main 8. This is the location of our first breakpoint, and that's where the code has been suspended. In the center, the debug window has our method arguments and our local variables displayed. Because we are sitting at line 8, we haven't yet started to execute our loop, so our count of matches and our sum of matches variables are still 0. We haven't started the loop, so we definitely haven't matched any criteria yet. On the right, we can add variables or expressions that we're interested in watching. I think this would be a good place to add the criteria we set up, so let's do that. Where it says evaluate expression, I'm going to type in the first part of our criteria, loop number modulo 3. Then I'm going to hit this plus icon. This adds this expression to what's called the watch list. This means, as we progress through the code, we'll see these watched expression change values. You'll note here that we actually have an error with this expression to start with, cannot find local variable loop number. And that's because we haven't actually started the loop yet, and that variable doesn't even get created until we start the loop. So right now, that variable doesn't exist in the JVM. But we can still add this expression, and I want to add the other part of our condition, so let me do that now. I'll add loop number modulo 5 this time, and click the plus icon. So let's actually move forward now. And we can do this in a couple of ways. On the left, there are several icons vertically here, and if we hover over those, we see rerun main, modify run configuration, resume program, pause program, stop main, and so on. The two we care about right now are resume program and stop main. Resume will actually start executing the code from where we paused it. Stop will terminate the debugging session. Some other options we have are the icons shown above these panels. And if we hover over them, we'll see show execution point, step over, step into, force step into, step out, and so on. So the one we care about here is step over. These icons let us step through the code or execute it line by line instead of just running it to the next breakpoint or to the end. How you step through it is why there are so many options and are relevant when we start executing methods from other methods. Since, in this code, we're not executing any methods other than main, we can just use the step over icon. So let's click that, and you can see IntelliJ, first of all, is indicating in the main editor window what line of code will be executed next. So now the debugger is sitting at line 9, which is where we'll be testing our criteria. And we're in the loop now. You can see this because loop number is now showing up as a variable in the middle pane of the debug window, and its value is 1. And look over here to the right, where we set up our watched expressions, the two parts of our if condition. These expressions have been evaluated, and their values are shown here. So in both cases, we can see that loop number, which has the value of 1, has a remainder of 1. This means our if condition criteria will be false because we're testing if these values are equal to 0. In fact, we can add those as expressions too. Let me quickly do that. So what I'm basically doing is adding the two sides of our logical and expression that we're testing on line 9. So I'm going to add loop number modulo 3 equals 0 as the one expression. And I'll add loop number modulo 5 equals 0 as the second one. Then, after we do that, we can see that they're both false, so that means our if condition will be false. Let's step over again. And now the code pops down to line 15, and IntelliJ is giving you the information that that condition 2 is false. You can see that the editor window has a lot more information on it in debug mode. So for each line you step through, you can see some of the data on the editor pane as well, which is really pretty neat. And if we step over again, now we're back at the start of the loop, and hitting step over yet again, you can see we can go through the code line by line. Both IntelliJ's editor window and the debugger panel here are telling us the values of the variables. We are now in the second increment of our loop. Loop number is 2. Our watched variables have changed, and we can see remainder is 2 in both cases, and the two halves of our conditional expression are still both false. So now let's change our breakpoint. First we'll toggle line 8 off, then we'll add a breakpoint on line 9. Now our code will pause right before it checks this condition. So instead of stepping through it this time, we'll hit this resume button. And now the code executes until it hits that breakpoint in the next iteration. This time, you can see one of our conditions is true, but not both when loop number has the value of 3. Loop number modulo 3 is 0, and therefore the expression here with equals 0 is true. Okay, so again, we'll change our breakpoint because we're only really interested in the numbers that match our criteria. So let's remove the breakpoint from line 9 and add it at line 10. Now when the code gets to that breakpoint, we'll be in this code where we found a match. And now, hitting the resume button, we can see that the code is paused now at line 10. Loop number is 15, meaning we're on our 15th iteration of this loop. It took 15 iterations to find the first match. So now, let's step through the next couple of lines of code, line by line. We do this with the step over icon. And now, you can see, after stepping over the line, we've incremented, for the first time, count of matches to 1. That's because we've found our first match. And stepping again, you can see that sum of matches has the same value as loop number. That's because sum of matches was 0 to start with, so we added the loop number, which is 15 at this point, to 0 to get a sum of 15. And stepping again, it executed our println statement. We can see this output if we select the console tab here. We can see our output from that line, found a match equals 15. So that's good. So let's select the Debugger tab again. And now we'll hit Resume again, and this will suspend execution when it finds another match. And so now we've found another matching number, a number that matches our criteria, and that number is 30, which is the value in loop number. And if we step through our code line by line, after the first step, we see that count of matches gets set to 2 because we've found our second match. And step again. Now sum gets the value of 45. That's because it was 15 when this iteration started, and here we're adding loop number, which is 30 to it, so we have 45. I hope you can see how watching the debugger and using some combination of breakpoints and using the resume and stepping into features to walk through the code can help you understand what the code is doing and where it might be going wrong. There's a lot you can do with this debugger, and I want to encourage you to explore it and the documentation IntelliJ provides. As a learner, every tool in your arsenal that helps you examine the code at every level is really valuable. Now we could keep doing this until we get through the loop, but I can see after these 2 matches that our code is working correctly, so now I want to change our breakpoint again. I'm going to toggle the breakpoint on line 10, and this time set one on line 16. So now, if I resume this code, the code will only suspend now at the point where we've finally found our 5th match. So let's resume. And you can see our variables there. Count of matches is 5, which is why we're paused here. Sum of matches is 225, and loop number is 75, meaning it took 75 loop iterations to find these 5 matching numbers. And if we look at the console, and here we can see our 5 matches printed there, 15, 30, 45, 60, and 75. And if we hit resume again, our code completes successfully and prints out that final sum, 225. So that was the challenge. And we got to explore the for loop in our challenge in a lot of detail using IntelliJ's debugger. I hope that cleared up a lot of questions you might have had about what this code was doing and how the for loop is working. And I hope you'll try the debugger on your own solution to this challenge, especially if you found that your own solution didn't match mine or you didn't get the same result. Using this tool might help you understand why. And if you get stuck in the debugger, remember there's always this stop main icon, which is red and enabled when you're in a debugger session. Let me start the debugger again, and now you can see it's stopped at our breakpoint, which is the break statement. So we can always select that to quit out of the debugger, and I'll do that now. You can see the debugger stopped when I did that. Okay, so that was your last for loop challenge and IntelliJ's Java debugger. So now let's move on, and we'll do a quick recap of what we've learned so far about the for statement. I'll see you in that next video. So let's recap what we've learned about the for statement. So on this slide, we are showing a for loop, and we've got the initialization part to start where we initialize variables. Then the condition, which determines when the loop ends. The last part is the increment, also known as the iterator step. So, in other words, one execution of the loop step is known as one iteration. So in the increment part, we could increment by 1 or 5 or decrement by any number. It depends on the situation and specifically what you type in there. So we say that the loop iterates. In other words, it loops or executes a block of code when the condition is true in steps. And those steps are called iterations. And then the loop stops when the condition is false. The block of code is defined by curly braces. In the loop body, we can have multiple statements. Those statements will execute every step, or we can say that they'll execute every iteration. And notice this semicolon after the init and the condition. Those semicolons are required. Alright, so the scenario on this slide is we've got the for loop that just prints out the value of some number, and this number is in the variable named number. The init part is int number equals 1, so we're starting at 1. The condition shown on the screen is number less than 7, and the increment is number plus equals 2. So in other words, we're incrementing the number variable by 2. So this for loop will print out every other number between 1 and 6. So as you can see, the output showing at the bottom of the screen is number equals 1, number equals 3, number equals 5. It just prints those 3 numbers. Note that it didn't print the number 7 because the condition was less than 7. But let's just go through step by step through the loop iterations so it's easy to understand. So on this screen, we've got different numbers showing what the different stages of a loop iteration are. So I'm going to call those stages just to make it clear. So the first one with the red circle, number 1, that's where we initialize the variable number to 1. Next, stage 2 is where we're checking the condition, and the condition we're checking is if number less than 7. Now if the condition is true, and in this case we've got number less than 7 and the number variable is 1, which we set initially in stage 1. So therefore that condition is true since 1 is less than 7. So the loop executes a block of code in this case, and the code we've got in there is a system.out.println, and it prints number equals 1 to the console. So the current output is number equals 1, then it increments the number by 2, in other words, the iteration step executes. And that's our stage 4. And just to be clear, stage 3 there on the screen was where it was actually executing the line in the code block to print out the number. So at the end of the 4th stage, we've added 2 to the number. Since number was 1, we've added 2 to that, so it's now 3. So now the value of number is 3, and we'll start the next iteration. We'll go back to stage 2 to check for that condition. Alright, so here on this slide, we have number now set to 3. This is the second iteration. Again, it's 3 because it was incremented in the previous step. So once more, the condition's checked, and we're checking that in stage 1 there on the screen. And we've got now number less than 7, so we check whether 3 less than 7, so that condition is also true. So it prints number equals 3 to the console. And again in stage 3 on the screen, we're executing the iteration, and that means we're adding 2 to 3, the current value of number. So number now becomes 5. 3 plus 2 is obviously 5. So the number variable is set to 5, and then we actually go through the next iteration of the for loop. Okay, so here we are with the number now being set to 5. So we've had 2 iterations, and again the condition is checked. And we know that 5 is less than 7, so that condition is true. So it prints the number equals 5 to the console. And you can see the output at the bottom of the screen there. And obviously stage 2 is executing that code to print the output. And again in stage 3 of the increment side of things, we're adding 2 to the number variable again. Currently it's 5, so 5 plus 2 is 7, so the value of the number variable after the increment is now 7. Then we move on to the next iteration. Okay, so at this point, we've got the 3 lines of output, number equals 1, number equals 3, number equals 5. And now the number is 7 since it was incremented in the previous step. So again, the condition is checked in stage 1 on the screen, and we've got 7 less than 7, but now that condition is false. So the loop exits at this point, and the code in the code block won't get executed. The code will continue after the closing curly brace, and you can see the arrow pointing to that, and on this slide, we're calling that stage 2, and it jumps to that part of the code. And in this scenario, we don't have any other code after the last curly brace. Alright, so that's one scenario. Now let's look at another for loop. In this case, this for loop will never execute. Can you figure out why it won't execute? So pause the video now and then come back when you're done. And I'll show you the reason why and also show you the output. So how did you go? Did you manage to figure out why this code will never execute? Well, this was a bit tricky, and you can see there's no output at all. So let's move on to the next slide and see why there isn't any output. So firstly, in stage 1, we're initializing the number variable to 1. The condition is then tested in stage 2, and the condition we're testing is number less than 0. But since 1, which is the value of number, is not less than 0, the code block will never execute. So the condition starts out false, and the code jumps out and bypasses the code in the code block. It jumps, as you can see, to the next line after the closing brace, which we're calling stage 3. So you really have to be careful with conditions in a for loop. As you can see, if the condition is wrong, the loop will never execute at all. So to fix this loop, to execute the code block, we have to change the condition. For example, we can change the condition to number less than 5. So in that case, it will then print out the numbers 1 and 3 before closing down and exiting. So here's another for loop, and can you guess what this one will print out? Pause the video now and come back when you're done, and I'll show you the output and explain what will happen. So how did you go? Did you manage to figure that out? Well, this was again a tricky example. So let's see what's happening with this one. It's also pretty easy to set conditions that might cause your loop to increment endlessly or cause an overflow with unexpected results. So here, we're checking the condition is number greater than 0, but we're also incrementing the number. So this condition will be checked the way we have this set up for every number greater than 100 in increments of 10. If you coded this in IntelliJ, you might notice a warning that the loop executes 0 to billions of times. In fact, this loop will loop until number equals integer.max_value, which you'll remember was 2.14 billion or so. Then the increment will cause number to overflow, and then the condition, number greater than 0, will finally result to true, because number, if you remember, will overflow to integer.min_value, a negative number. This is behavior we probably didn't intend. In some cases, poorly thought out conditions may result in endless loops. This can cause programs to block forever or crash when it runs out of memory. So how will we fix this? Because we really don't want this code to run billions of times. Well, what we could do there is, for example, change the condition to check if number is less than 130. So that way we print the numbers 100, 110, and 120 in the console, as you can see in the output on the screen. And that's because we've changed the condition, which was number greater than 0, to now number less than 130. Okay, so that's it for the for loop recap. Alright, so I hope you got a lot out of this video. And just one last thing, there's also another variation of the for loop, which Java calls the enhanced for loop, or popularly called the for each loop. To discuss this variation, we really need to have an understanding of objects, arrays, and collections. When we do get to the course section on arrays, we'll be revisiting looping, and we'll demonstrate the enhanced for loop in that section. So that's it. I'm going to end this video now, and I'll see you in the next one. What if you want to loop until some condition is met that's not associated with a known range of values? In the previous videos, we talked about the for statement, which was a way to come up with a for loop to be able to process a statement or set of statements a set number of times. And in this video, we're going to look at the while and also the do-while statements. The thing is, with looping, sometimes you might want to loop. Instead of a specific number of times, you might just want to continue until a certain expression evaluates to true or false. For this situation, Java has two flavors of the while loop. So, for example, you may not know how many times you want to loop ahead of time. So what you need to do in those scenarios where you don't really know how many times you want to loop is you want to continue looping until some condition is met. In other words, you probably want to use the while statement. The difference between the while loop and the do while loop is that the do while loop will always execute the loop code block at least once. So I've already created a while loop project with the usual main class and main method. And before we look at the while statement, we'll just quickly add a for loop example so we can compare the two statements. This code declares a for loop looping from 1 to 5 and prints those numbers out. We've said it's somewhat common practice in Java and other languages to call the loop iteration variable simply I or j or k, and we'll do that here. For, opening parentheses, int I equals 1, semicolon, I less than or equal to 5, semicolon, I plus plus, closing parentheses, opening curly brace. System.out.println, opening parentheses, I, closing parentheses, semicolon, closing curly brace. So we've also stated several times that the for loop has three declaration parts in the parentheses separated by semicolons. But looking at the while loop in comparison, you can see the while loop simply has the loop expression but doesn't support initialization or the increment code as part of the declaration as does the for statement. So knowing the differences now between the while loop and the for loop, let's write code that does the same thing as our for loop, but we'll use a while loop instead. We'll use the same expression we used from the for loop. While, opening parentheses, j less than or equal to 5, closing parentheses, opening curly brace, closing curly brace. But now you can see IntelliJ is having a problem with the j variable there, and that's because this variable has not been declared. Unlike the for loop, there is no place for the declaration of a temporary variable in the declaration of the while statement. So we have to declare any iteration variables outside of the loop. So we'll do that, and we'll set it to 1 to match what the for loop is doing, and we do this right before the while loop code. Int j equals 1 semicolon. So we still don't want to run this just yet. If we did, the while loop would start executing and never stop. And this is because we're never changing the value of the variable j inside the while loop. This condition is called an infinite loop and generally not something you want to program. We didn't have to include this in the for loop statement block because we already had it in the declaration as the last part of the declaration in parentheses, and then we have j++. So we'll just add that to our loop as well as the system.out.println statement. System.out.println, opening parentheses, j, closing parentheses, semicolon. j++, semicolon. Okay, so the code from lines 9 through 13 using the while loop now emulates what we did with the for loop, and we can run that safely now. And we can confirm we get the exact same output as the for loop. So you can see, in the case of the while statement, there's no variable set up within the loop declaration in parentheses like there is in the for loop declaration. And we also need to increment our variable manually if we're using a variable to determine when to exit the while loop. So that's the difference between the two. Let's edit our code a little bit, changing our loop expression to just be true. Okay, so why would you ever want to do this? Isn't this just another infinite loop? Well, that's true, but you might see while loops used this way and the condition tested elsewhere also within the loop code block. Let's add that. This time we want to terminate the loop if j is greater than 5, and we'll use a break to do it. We talked about using the break statement with the for loop, and the concept is the same here. If this condition is met, then this break statement exits the loop, ending it at this point, skipping all code below it and ending any additional iterations. If, opening parentheses, j greater than 5, closing parentheses, opening curly brace, break, semicolon, closing curly brace. So setting the while loop condition to be true and then using a condition containing a break statement is another common way to program a while loop. And if we run that, we get the same results as before. So let's now look at the do while statement, which is very similar to the while statement we've just been looking at. We've said before that the do while statement will always execute the loop code block at least once, and that's because the loop expression isn't tested until after the loop code block executes. So first, let's see what happens if we just change our while loop code, and instead of while true, we create a variable called isReady, and for now, we'll set it to false, and we'll use it for the loop expression. Boolean isReady equals false, semicolon. And in this instance, the code in the while block won't run at all, and we get no output for the while loop. It's not likely you'd write code like this, but maybe in your loop block, you'd be testing some condition return which will set isReady to true. Obviously, if we never get into the loop, that code wouldn't get executed. But let's just say we always want our code to run once, regardless of the condition, and then keep checking this value. We could use the do while code to make that happen, so let's change our while loop to a do while. This is just changing 2 lines of code. Do, opening curly brace, closing curly brace, while opening parentheses, isReady, closing parentheses, semicolon. So you can see how similar the do while loop is to the while loop. Let's examine these differences really quickly. So noticeably, you can see that we are starting with do before the block of statements, and the while is declared after the code block. This is why the do while always executes at least once. It will enter into this code block, execute whatever statements are in this block, and only then will it check the condition. If the expression evaluates to false, it won't iterate, but if it's true, the loop will continue to execute. Finally, it's important that this statement ends with a semicolon. This is different from the other 2 looping statements. So looking at our code, with these differences in mind, we start with just a do statement, and the do statement doesn't support any condition in parentheses, so it's just followed by an opening curly brace. Then we have all the same code, and this code will always execute because we aren't applying a condition to it the first time. But then you see the while statement, directly after the do code block, and here is the condition. Also, note that we have a semicolon at the end of the while condition. This is required. So this code won't execute a second or third time or more than once unless that condition is ready is true. But we could use this code in some condition to now set is ready to true if we wanted the loop to continue. Let's quickly do that. Let's add another statement after we increment j. Is ready equals opening parentheses j greater than 0 closing parentheses semicolon. So now this code would execute the first time when is ready is false and j is 1, but when j gets increment to 2, is ready is set to true, which means this code will continue to execute until the break condition is met. And if we run that, we see we get the same results we had before. So when would you use a do while and not a while? Well, a good example for a do while loop might be when you need to ask for your user's name and password. You want them to enter it a first time, and if it's incorrect, you want to continue asking for the information up to a certain amount of times, allowing them to hopefully, at some point, remember it. So we've seen examples of all three loop statements, and you've seen that you can use a loop expression to control when the loop terminates. But you can also use a break statement to exit a loop. Okay, so there's another statement that's important to all of these loops, and that is the continue statement. The continue statement, in its simplest form, will stop executing the current iteration of a block of code in a loop and start a new iteration. In some cases, you'll have a loop where the majority of iterations in your loop meet the criteria for which you want to do a lot of work. But you might have a couple of exceptions. So rather than use a big if-then-else statement, you just want to ignore a few iterations and skip the code that would be normally executed, but keep the loop going. So let's try that out. Let's set up an example where it might make sense to use a continue statement in a while loop. First, let's comment out all the other code in the main method so we can just focus on the continue statement. And now let's add a new while loop. We'll create a loop that goes through the numbers 0 to 50, incrementing by 5 at the start of each loop iteration. Then we'll print out those numbers on a single line separated by underscores first. Int number equals 0 semicolon. While opening parentheses number less than 50 closing parentheses opening curly brace. Number plus equals 5 semicolon. System.out.print opening parentheses number plus double quotes underscore closing parentheses semicolon closing curly brace. If we run that, we can see the output. It's printing out all numbers starting with 0, but then all increments of 5 up to and including 50. But let's just say, for some reason, we don't care about any numbers that are evenly divided by 25. In this code, we'll just use the continue statement to skip processing for numbers evenly divided by 25. We add that in with an if statement and then add the continue statement. If opening parentheses number modulo 25 equals 0 closing parentheses opening curly brace. Continue semicolon closing curly brace. And if we run that, you can see our output no longer includes 25 or 50 in this list. So this code continued the loop even after it considered 25, but it didn't process the number 25. In other words, it simply started a new iteration when the number was evenly divided by 25. When it starts a new iteration, any code below the continue statement is skipped, like this system.out.println statement on line 26. Again, a continue statement is a good way to continue to execute iterations of your code, but perhaps skip code for certain elements or only partially execute code in certain cases. In this video, we've compared the for loop statement with the while loop, and we've demonstrated that a do while loop is very similar to the while loop, but always executes the loop code at least once. We've also covered the continue statement. In the next video, I'm going to give you a challenge so you can try out the while loop on your own.
It's break time. Do you like this video? Don't forget to subscribe to get new videos. Share this video to open new premium videos and ebooks. We'll be a star freelancer.
Okay, so it's challenge time again. We're going to look at this challenge in 2 steps. So step 1 is to create a method called isEvenNumber that takes a parameter of type int. Its purpose is to determine if the argument passed to the method is an even number or not. Return true from the method if it's an even number, otherwise return false. Next, use a while loop to test a range of numbers from 5 up to and including 20, but printing out only the even numbers determined by the call to the isEvenNumber method. And to give you a bit of a hint here, you want to look at using the remainder operator. As part of this challenge, create a new project called while loop challenge with a main class and the usual main method as well as this method. Alright, go ahead and try that out and see if you can figure it out. Pause the video now and come back once you've tried it out and to check what I've come up with. Okay, how did you get on? So I've created a new project and I've called it while loop challenge with the usual main class and main method as I'm showing here. So let's go ahead and write that method, placing it at line 7 before the closing brace of the main class. Public static boolean isEvenNumber, opening parentheses, int number, closing parentheses, opening curly brace. If opening parentheses, number, modulo 2, closing parentheses, equals 0, closing parentheses, opening curly brace. Return true, semicolon, closing curly brace, else, opening curly brace. Return false, semicolon, closing curly brace, closing curly brace. So, a simple way to determine whether a number is even or odd is just to use the remainder operator like we've done in this code. So if we try to divide a number by 2 and there is no remainder, which this first if condition is really checking, then that number is divisible by 2, which is the definition of an even number. So we return true, otherwise we return false. Okay, so what we'll do now, we'll add some code that's going to execute that method, and we'll do that in a while loop to test a range of numbers as the challenge specified. So my code here is going to start with an int number with a value of 4. I'll explain why I start with 4 in just a moment, but we want to keep processing numbers until the number variable reaches 20. So I'll set up some variables in the main method on lines 5 and 6. Int number equals 4, semicolon. Int finished number equals 20, semicolon. Alright, so now we need to create our while loop. And we'll execute this while loop while the number variable, which is starting out with a value of 4, is less than or equal to finished number, which we've said is 20. So within this code block, at the start, we're going to increment the number. This means, starting out, we'll actually start with 5, and not 4, which was part of the requirements. So with while loop incrementing, you often want the increment to be the first thing you do because it's easy to end up with an endless loop if it accidentally gets skipped. So in other words, we don't want to accidentally create a loop that never ends. So we're going to do that and make the first statement inside the while code block to be number plus plus. While, opening parentheses, number less than or equal to finished number, closing parentheses, opening curly brace. Number plus plus, semicolon. System.out.println, opening parentheses, double quotes, even number, plus number, closing parentheses, semicolon. Closing curly brace. If we run that now, we'll just get every number printed out because we haven't put in our check yet. So let's do that. We'll check if the number is an even number using our method isEvenNumber. We'll do this with an if statement. If the number's not an even number, we want to continue, meaning skip all the code below, which is just the print statement. If opening parentheses is even number, opening parentheses, number, close both parentheses, opening curly brace. Continue, semicolon, closing curly brace. So what is this code doing? It's going to start at the number 5, or actually number 4, but then that number will be immediately incremented. And again, that's because we've got this code on line 9. And so that then gets increment as the first statement. And it's going to go through and finish up to and including the number 20. Because we've got a less than or equal while test here on line 8. And what we're doing is we're testing to see whether the number is an even number. And if it's not an even number, we're going to do our continue, which is something that's different than break. You'll remember that both break and continue have the effect of interrupting the code. But what happens with continue is that it'll effectively bypass the print statement on line 13. And in case there were other statements or code, these would also be bypassed. So in other words, continue won't do any code any further down. And code execution goes back to the start of the loop instead. So the loop goes back and starts on the next number again. So the first time it goes through the loop, number will get set to 5. 4 plus 1 is 5. And if it's not an even number, which we know it's not, it'll go through and get increment again. So since number is 6, this if clause, this condition is false and the code isn't executed. So in other words, then we'll see that when the value is 6, that value gets printed out here on line 13. But then at 2, we'll go back to the start of the while loop and the number will be incremented yet again. And this will keep looping until this while comparison here on line 8, this test here returns false. So if the number is 21 or higher, then the while loop is going to be terminated and the processing will complete. All right, so let's actually test this and see if it works. We're going to run it. So you can see what's happened there. You can see the output there is even number 6, 8, 10, and so on. So that's what the continue keyword is. So it basically says stop where you are, continue on to the next iteration of the loop. Now, while loop is probably the statement you'll use more often than a do while loop, but they've all got their place. And we'll be giving you many more examples as we progress through the course, and you'll start getting more of an understanding of where to use each and which one to use and which one's best for a particular purpose. All right, so hopefully now that makes sense with what continue does. Let's move on to step 2 of the challenge. So step 2 is to modify the while code. Make it also record the total number of even numbers it has found. Break out of the loop once 5 even numbers are found. Finally, display the total number of odd and even numbers found. Alright, so the challenge is to modify the while code above. So you want to leave the existing functionality as it is, but make it so it also records the total number of even numbers as well as odd numbers that it's found. And once 5 even numbers have been found, break out of the code and display the total number of even numbers, which we know should be 5, but also the number of odd numbers. So print that outside of the while loop. So you don't want to break any existing functionality. We still want the output working as it did previously. We just want to add that extra bit of functionality to the code. All right, so pause the video and go away and give that a try. And once you're ready, come back. We can check out the solution that I've come up with against yours. So pause the video now. Okay, so how did you get on? Did you manage to figure it out? Well, let's go through the solution together, bearing in mind there's always multiple solutions to a problem. All right, so what we need to do first, we need to record the total number of even numbers and the total number of odd numbers that have been found while processing our loop. So we need some sort of count variable for both even numbers and odd numbers. So what we're going to do is add 2 variables, and we'll add them here after line 6. Int even count equals 0 semicolon. Int odd count equals 0 semicolon. We'll initialize or set them both to 0 to start with. And when we find an even number, we'll increment even count, and we'll increment odd count if it's an odd number. So let's add that code, incrementing odd count on line 13 and incrementing even count on line 17. Odd count plus plus, semicolon. Even count plus plus, semicolon. So when we've determined that the number is not an even number, we increment odd count, then we call the continue statement after that. And we can add the increment to even count anywhere below that if statement, because only even numbers will fall through to this code. So let's print out and type total odd numbers found equals with the odd count, and we'll also print out the even count. Let's add this below the while loop on line 20. System.out.println, opening parentheses, double quotes, total odd numbers found equals, plus odd count, closing parentheses, semicolon. System.out.println, opening parentheses, double quotes, total even numbers found equals, plus even count, closing parentheses, semicolon. All right, so let's try running this code and see what happens. You can see that it's correctly identified that there's a total of 9 odd numbers and 8 even numbers found, and our print statements are still printing while the loop is executing. And you can see that matches up with the total here. But of course, that wasn't what the challenge wanted us to do. So why didn't it exit after 5 even numbers were found? Well, the reason for that was we haven't implemented that break yet. So what we need to do is put in an additional test after the even number is found. So basically, after incrementing the even count on line 17, after this line here, we want to put a test there on the next line. The test will be if the even numbers found is greater than or equal to 5, and then break. So let's add that in there on line 18. If opening parentheses even count greater than or equal to 5, closing parentheses, opening curly brace, break, semicolon, closing curly brace. All right, so now we'll run this to test. And you can see now we've got the 5 even numbers from 6 to 14 printing. And we're also printing the odd and even counts, which are both 5. Okay, so that was the while loop challenge. In this challenge, we use both a continue and a break statement. Both the continue and break statements are optional and can be used for ease of use and readability. This code could have been written without either a break or a continue, but the challenge did request that you use at least the break statement. Okay, so that's it for this challenge. In the next video, we'll have another small challenge to keep you exercising your looping skills. So I'll see you in that next video. Okay then, it's time for another challenge. So this is the digit sum challenge. In this challenge, your task is to write a method with the name SumDigits that has a single parameter named number of type int, and it should return an int. The method should only take a number that is a positive number. If a negative number is passed, it should return -1, meaning an invalid value was passed. The method should pass out each digit from the number and sum the digits up. So if 125 is the value passed to the method, the code should sum each digit, in this case 1 plus 2 plus 5, and return 8 as a value. In another example, if the value is 1000, the code should sum each digit 1 plus 0 plus 0 plus 0 and return 1 as a value. If the number is a single digit number, simply return the number itself as the result. So how do you think you'd go about doing this? Well, I think you'd agree you could use a loop, but how would you parse out the digits? And using only things we've learned to date so far in Java. So a hint here is to use n modulo 10 to extract the least significant digit or the rightmost digit, and use n equals n divided by 10 to drop the last digit as you are looping. At this point in time now, go ahead and try this out. Pause the video, and once you've finished, come back. And you can check out my solution, so pause the video now. Alright, so how did you get on? Hopefully you managed to figure it out. So let me talk about how we're going to go about doing this. We'll use the number 1234, which, when we add the 4 digits in that number together, we get 1 plus 2 plus 3 plus 4, which is equal to 10. In reality, we're going to do the maths in reverse, starting with the last or least significant digit, 4, then add that to the next to last digit, 3, and then to 2, and then finally add the 1 at the end. So let's look at what this process is going to look like on paper, and then we'll go about coding it after. At the start of the process, number equals 1234, and our variable sum equals 0. If we use the remainder operator, getting the remainder of the number divided by 10, this will give us the most right digit in the number. 1234 modulo 10 equals 4, and 4 is the last digit or most right digit. Since we'll be working through the digits, from right to left, we'll add this to sum. Sum equals 4. Next, we want to drop the most right digit, 4, and just have the other 3 digits to process. We can do this by dividing by 10. 1234 divided by 10 equals 123. Dividing an integer by 10 has the effect of truncating the number, cutting the most right digit off, if you will. And we are left with 123. If we make a number a double, dividing by 10 would have given us 123.4, and that isn't what we want. So having the parameter, number, be an integer lets us truncate the number when we divide by 10. So in each loop iteration, we'll be effectively dropping that last digit, which we can call the least significant or rightmost digit. So in the second iteration of the loop, number equals 123 and sum equals 4. And again we use the remainder operator, getting the remainder of the number divided by 10, which gives us the rightmost digit. 123 modulo 10 equals 3, and we'll add 3 to sum, which was 4, sum equals 7, and now we divide 123 by 10. 123 divided by 10 equals 12. So in the third iteration of the loop, number equals 12 and sum equals 7. And we again take number mod 10. 12 modulo 10 equals 2. And 2 gets added to sum equals 9. And we again divide now by 10. 12 divided by 10 equals 1. Now our number is a single digit, number less than 10, and here we'll break out of the loop. So in this final step, after we've broken out of the loop, number equals 1 and sum equals 9. Then we can just add this last single digit to sum and we'll have a final sum of 10. Okay, so that's how we plan to process the number passed. Let's hop back into IntelliJ and go through this step by step. You can see here that I've already got my project created, which I'm calling Digit Sum Challenge, and I've got the main class and the main method as usual. So the first thing we'll do is add some test code in the main method. We'll print out some text with our test number and then use the method in the expression, passing it that same number. We'll set up for a test to start, and the test values we'll use are 1234 from our slides, minus 125, 4, and 32123. You can set up any tests you want, but you should try at least one negative number and one single digit number. Remember, the single digit number should just return its own value. I'm going to type out the first print statement and then I'll copy and paste the rest. System.out.println, opening parentheses, double quotes, the sum of the digits in number 1234 is plus some digits, opening parentheses, 1234, close both parentheses, semicolon. Okay, so our test methods are set up and we're getting IntelliJ errors because we haven't coded the method some digits yet, so it's time to do that. We'll add the new method under the main method at line 11 and use the usual public static keywords. We'll start by creating a local variable for sum, initializing it to 0, and then we'll return that variable from the method. Public static int some digits, opening parentheses, int number, closing parentheses, opening curly brace. Int sum equals 0, semicolon. Return sum, semicolon, closing curly brace. So that's the definition for our method. And we're returning sum, which right now will always be 0. So the requirements of the challenge said that we shouldn't accept negative numbers, and if a negative number is passed to the method, we should return -1. So let's code that next. Let's add that before everything else, so if number is less than 0, we'll get return -1 right away. If, opening parentheses, number less than 0, closing parentheses, opening curly brace. Return -1, semicolon, closing curly brace. Okay, now let's actually start coding the loop. And we've talked about what happens in this loop. We'll first use the remainder operator to get the last digit and add that to sum. Then we'll divide number by 10 and start a new loop iteration. Because we don't know how many digits we'll get in the number passed, the easiest way to code this is to use a while loop. We're going to keep processing number while it's greater than 9, in other words, while there is more than one digit to process. So let's add this code starting on line 19. We'll type this in, then discuss it after we've got it coded. While, opening parentheses, number greater than 9, closing parentheses, opening curly brace. Sum plus equals, opening parentheses, number modulo 10, closing parentheses, semicolon. Number equals number divided by 10, semicolon. Closing curly brace. Okay, so we have a while loop with a condition that says we're going to keep looping while number is greater than 9. So this will keep looping while the number still has more than one digit. On line 20, we're getting the remainder value left from dividing by 10, which we've said was the last or rightmost digit. We get this number and simply add it to the existing sum variable all in one statement. We could have split this up into several statements, but here I'm showing it to you in one because I think it's a little easier to read. On line 21, we divide number by 10. And you'll remember why we're doing this. Dividing an integer by 10 effectively drops the most right digit. And then that's it. This loop will keep looping while number is greater than 9. But we still need to add that last digit to sum, and we'll do that outside the loop after the loop closing brace on line 22. Again, we use the compound assignment operator, so that sum is equal to sum plus the remaining number, which we know is less than 10. Sum plus equals number semicolon. Before we run it, consider what happens if number is a single digit. Sum will start out at 0, then we'll get to the loop, but look, the loop will get skipped because number is not greater than 9. So the code falls through to the last lines. Number gets added to sum, which is still 0, and sum is returned. So, in essence, this is almost as good as simply assigning number to sum in this case when the number is less than 10, which means the code is pretty efficient and uniform. We could have added code after the validation code to simply return a single digit number, and that would have been a valid solution too if you did that. So, does this code work? Well, let's run it and see. And you can see that it's correctly summed the digits 41234 and 32123. It's returned -1 when the number was a negative number, and it returned the value 4 when we gave it 4, so that all looks good. So as you can see, the tricky part here was to extract and drop the least significant or rightmost digit in each loop iteration. This is a great example of using the remainder operator to extract digits and the division operator to truncate integers. I hope you got a lot out of this challenge and that you managed to complete it. And I'll see you now in the next video. So, in the past videos, we've walked through some while loop and do while loop examples. In this video, we'll review both the while loop and the do while loop. So let's recap what we've learned about the while, do while loops, continue, and break keywords. On the screen, we've got the while loop syntax. As you can see, it's got the while keyword, and then there's a condition in parentheses. Then we have a code block, and this loop executes if the condition is true. Notice here that there's no semicolons in the parentheses, and there's no semicolon after the closing curly brace. So the while loop just has a condition. If we need to increment a variable, then we have to do it manually inside the loop. If we want to use a variable in the condition, we have to declare that variable outside of the while loop. Now with the for loop, we had the initialization, condition, and iteration in the same line. I'm going to show you a comparison for that, but firstly let's see the do while loop. So here's the do while loop syntax. We've got the do keyword at the top, and right after the do keyword, we've got a code block, the left and right curly braces. Notice again that there's no semicolon after the do keyword. After the block, there's a while condition. In other words, after the right curly brace, there's that while keyword, and then a condition in parentheses, and then a semicolon at the end. The semicolon is required for the do while statement. Keep in mind that do while will execute at least once. The condition is at the bottom. So the code executes once. This is the code in the code block. And then the condition is checked. So this is different from the while loop when the condition was checked at the top before any code at all was declared. So that's the syntax of the do while loop. So let's move on. Alright, so on screen now, we've got the while loop and a for loop that executes very similar code. In other words, both loops have the same logic, ultimately, that's going to be executed. So notice firstly that with the while loop, we have initialization of our variable count outside of the while loop, and the iteration or increment in the while loop block. So in other words, all three parts, the initialization, condition, and the iteration are on different lines. Now compare that to the for loop, where everything, in this case the initialization, the condition, and increment are on the same line. And each is separated by a semicolon. As you can see, we've got the initialization part, then the semicolon, the condition part with another semicolon, and the last one is the increment or the iteration part. But notice that the iteration part, there's no semicolon at the end in the parentheses. So again, this code will actually work the same and give you similar results. So you can see the differences between using a while statement and a for statement. So let's move on and see some steps with continue and break with the while loop. So here we've got some very simple code using the while loop and two if statements. So what the code does, it'll print the numbers from 6 to 10. Now this can be simplified with different conditions and without a break and continue. But it's a good example to see how the continue and break keywords or statements work. So first, we initialize the variable number with a value 0. That's step 1 on the screen. Then the while loop starts and it increments the number. So the number, when the first iteration starts, will get incremented to 1. So the if statement is checking the condition. In our case, this is step 1 on the screen, number less than or equal to 5. So we've now got a test for 1, being the current value of number being less than or equal to 5, which is true. So therefore, the code inside the if statement will execute. So first, it prints skipping number, then the value 1. And then the continue statement bypasses the remaining code in the while loop and continues with the condition of the while loop. So in other words, we could say it jumps back to the start of the while loop. In this case, since the number is 1, it checks 1 less than 15, and that's true as well. And again, the number is increment, so it's now got the value of 2. Now this will be repeated until the if condition is false. So in other words, until the number is greater than 5. So I'm going to skip those steps because they're almost the same, just the number value is getting increment. It's the same code in the if statement executed each time. So we eventually get to the part where the number is exactly 5, so let's move on and see what happens once the number has a value of 5. Alright, so I skipped a couple of iterations as I mentioned in the slides since they'd basically be the same. So now we continue from the time when the number has a value of 5, so this slide number is currently equal to 5. So first, it checks the condition 5 less than 15, which is step 1. And that's still true. The number gets incremented by 1. It's now a value of 6. You can see it's getting incremented in step 2. Then the condition in the if statement is checked. In this case, it's going to be step 3, and it tests if number is less than or equal to 5. So it's effectively testing 6 less than or equal to 5, and that's false. So the code in this if statement will not execute at that point. The code within the code block for the if statement is ignored because that condition isn't true. So next, we have that printing out, so that line is executed. This is step 4. And after that, we've got another if statement. So this if statement checks the condition number greater than or equal to 10. Now our number's got a value of 6 at the moment since it was incremented. And 6 greater than or equal to 10 is false inside this if statement. So the code inside this second if statement is not executed. Now the steps described get repeated until the number gets a value of 9. So let's move on and see what happens once the number has a value of 9. Alright, again we skipped a couple of iterations as I mentioned in the images since they're the same. So we're now continuing when the number has got the value of 9. So then again, firstly, it checks the condition in the while loop, which is 9 less than 15. That's step 1. And that's true, so the while loop block starts executing again. The number is incremented to 10 in step 2 there. The next condition, step 3, we're checking if 10 less than or equal to 5, and that's false, so the code block inside the first if statement is not executed. So therefore the code in step 4 is executed and the number's printed out. Then again we've got a second if statement that checks, in this case, the condition 10 greater than or equal to 10, and that's true, and this is step 5. So this if statement block gets executed, and in this block, step 6, we print the message breaking at 10 since the number has the value of 10. And then there's the break statement that exits the loop. So after this break is executed, the code continues after the closing brace of the while loop. That's how, with continue and break, we can interrupt the loop, and depending on the condition, we can skip parts of the code or break out of the loop. Okay, so let's just move on and see the important things to remember about while and do while. Now firstly, the while loop checks the condition at the start before executing the block. Compare that to the do while loop, where the code is executed at least once and then the condition is checked. So you always guarantee that the code in the code block for a do while loop is executed at least once. When using loops, you want to carefully examine the conditions for terminating or continuing a loop. Check for endless or infinite loops. Check for conditions where a loop will never execute. So be careful with conditions because it's very easy to end up with an endless loop. In other words, a loop that never ends. Or to end up with a loop that never executes. And as a tip there, always check carefully the conditions, the expressions to make sure that doesn't happen. The continue and break statements both interrupt normal loop processing. The continue statement starts a new iteration but continues to iterate through the loop. The break statement exits the loop at the point it's executed and no longer completes any code in the loop and won't continue iterating any longer. And we can interrupt the loop as you saw by using a continue and a break statement. With the continue keyword, the loop will bypass the part of the code that is below it but then continue with the next iteration. But the break keyword will exit the loop depending on the condition that we're checking. So that's it. That's a recap of the while and do while, as well as the continue and break keywords. I hope you got a lot out of that, and I'll see you in the next video. In the past couple of videos, we've looked at many of Java's flow statements, the switch statement, the for statement, the while statement, as well as the do while statement. In previous videos, we covered the if then else statement. All of these statements may, and probably will, have their own code blocks. We've talked about code blocks quite a bit, but we haven't really talked about variables declared locally to many of these code blocks. A local variable is called local because it is available for use by the code block in which it was declared. It is also available to code blocks that are contained by a declaring block. In the example on this slide, we have two variables declared at the start of a code block. We use the first variable in an if-then statement expression and can print the second variable inside of the if statement block. The if block is contained by the method block and has access to the method block's variables as this demonstrates. This accessibility is also known as variable scope. Scope describes the accessibility of a variable. In scope means the variable can be used by an executing block or any nested blocks. Out of scope means the variable is no longer available. Local variables are always in scope in the block they are declared. They are also in scope for any nested blocks or blocks contained within the outer block. So for example, a method block can declare local variables and any flow statements contained in the method block will have access to the method's local variables. This is also true for the method parameters. Any code in the method and any nested blocks have access to the parameters. There's no limit to how deep you can nest code blocks, but generally, for readability and maintainability, consider replacing deeply nested blocks with method calls. Local variables are always out of scope for outer blocks or the containing blocks they are declared in. Let's look at an example. In this example, we've declared a local variable called myCounter inside the if block. This means myCounter will be out of scope for any containing blocks. The method block is the containing block in this instance. You can see that the system.out.print statement outside of the if block can't use a variable declared inside the if block. This line of code will cause a compiler error. IntelliJ shows this error with cannot resolve symbol myCounter. There are some best practices when declaring variables in different blocks, which we'll briefly discuss now. It is considered best practice to declare and initialize variables in the same place if possible, and to declare variables in the narrowest scope possible. It is much clearer to declare and initialize a variable, if possible, in a single statement. There are times when this is not always feasible, but when it is, you should do this. Declaring variables in the narrow scope simply means if your variable is only used in a nested block, declare it there. Another example that we've seen, if you're using a variable only in a loop code block, like the iteration variable, and won't be using it outside of the loop block, declare it in the loop code or in the for loop initialization block. Obviously, this is a practice we can implement with a for loop because of its special declaration support for initialization, but this is harder to do with a while loop. Let's revisit the for statement and look at local variables. In this for statement, as part of the declaration, there is an initialization part, as we've described. In this case, we declared a variable I that isn't accessible outside of the loop. This is because any variables declared in the init section are local to the loop, meaning they exist and are accessible in memory only while the loop is executing and only to the loop code block. This is also true for most flow statements, for example the if statement. Local variables declared in an if statement block are not accessible outside of that block. This also includes other parts of the if statement, like the else if block or the else block. If you tried the code on this slide in a method, you would get an error on the 2 lines indicated. The variable is only in scope for the block declared in the first part of the if statement. However, the switch statement is different from the if then else statement blocks. Consider the code below. So, the left and right braces are optional in a switch statement. The code block is whatever is after one case label and before the next case label, including the break statement. However, the case block has different access for local variables than the if else block. In a switch statement, a variable declared in one case label code block can be accessed in another case label code block, but only if that block is after the declaration and initialization of the variable. As you can see in the example here, in the default code block, we had access to the variable I, and this did not cause an error. Let's look at another example of code blocks and local variables in the switch statement. In the first case label block, the code is trying to use the I variable, but it's not declared until the case 2 block, so we get an error when we try to use it in the case 1 block. However, as previously shown, we don't get an error in blocks declared below the case 2 block. But again, we get an error if we try to use the local variable I outside of the switch block altogether. So that's it for local variables in scope. In addition to local variables, we can set up data to be defined and used as part of a class or an object. In the next video, we'll be discussing the class and its related structure, the object, at a very introductory level for reasons I'll explain in that video, so I'll see you in that video. In the previous video, we talked about local variables in scope. Local variables are a way to store and manipulate temporary data. In addition to local variables, we can set up data to be defined and used as part of a class or an object. We'll be discussing these concepts now at a cursory level for several reasons. First, attributes on classes is another way to store data. Second, I want to introduce you to some static methods on the wrapper classes, which are classes we previously looked at, but we haven't used any methods on these classes yet. These methods will help pass strings into numeric values. And finally, I want to introduce you to a special class for reading input, which we'll be using in the last part of this section to create an interactive program. Before we use that class, it will help if we understand some very basic concepts with classes. A class can be described as a custom data type, a special code block that contains methods. We've already talked about the class a little, both as a custom data type and a special code block that contains methods related to the class. What we haven't talked about is the class's unique role in creating objects in memory. A class is like an empty form. It describes information or placeholders for data that will be filled in when that form is given to a unique individual. The class may have a field for name. The object will have a value in the name field, which will be unique to the object. The class may have a field for address. The object will have values for the address field, and so on. The process of copying that empty form and then delivering it to some process or person to fill in the blanks is a loose analogy to what happens when you create an object. The empty form, the class, is the template for the data to be collected. The populated form, the object, may be completely different each time because of the values used to fill in the data. But the data being collected each time is determined by the class or the form in this analogy. An object is called an instance of a particular class. In this course, we'll often use the word instance interchangeably with object. This means an object is created by instantiating a class. There are multiple ways to do that, and we'll be talking about that more in a bit. This slide shows a class that has 5 objects, or instances, created from it. We call the creation of the object instantiation or instantiating a class. We can use the term object or instance interchangeably. There is no limit to the number of objects you can create from a class. A class is sometimes compared to a cookie cutter, and the cookies are your objects. The class provides a shape or framework that describes the object being created. A template is another word you'll hear used when trying to describe a class's relationship to an object. We're going to cover some very simple basics about classes right now. The most common way to create an object is to use the new keyword. The new keyword creates an instance, and you can sometimes pass data when creating an instance to set up data on that object. The string is special because we can create a string just by using a literal, which we've seen. But we could also use new, Like other data types, you can assign this object's memory location, also called a reference, to a local variable, as we've done with this string. We've assigned to the local variable s an instance of string. All manipulation of the object's data and methods are then done using the local variable name. In both of these statements, we're creating a new object of type string and initializing it with the text hello and assigning it to a string variable named s. The second statement makes this a bit clearer. When we create an object, we can pass initial data to be associated with it in parentheses. We've stated previously that the class can be thought of as a special data type. This is because you can create variables on classes. These are called fields or attributes on the class or object. There are two ways to create fields on classes. One is with the static keyword and one is without the static keyword. When the static keyword is used, it's called a static field on the class. This means the value of that field always stays with the class. It's stored in a special memory location for values that aren't changing constantly, unlike local variables and objects. In our form analogy, this would be a field that is pre-populated on the form and would not change for any of the copied forms. But unlike the form, this type of field in a class doesn't really get copied down to the object. It maintains its single value on the master copy, the class. The field in memory is accessed differently because we can access that field using the class name with dot notation, and we've done that already. When we looked at wrappers, we accessed integer.max_value, integer.min_value, and integer.size, for example. This data was stored on the class and not on an instance of the class. When the static keyword isn't used, it's called an instance field. Until the class is instantiated and an object created, the instance field has no place in memory. These instance fields can have different values for every instance created. This field is accessed using the variable name for the object and the dot notation used with the field name. In the same way that there are static fields and instance fields, there are static methods and instance methods. Again, the static keyword is used to differentiate these two kinds of methods. A static method can be called directly using the class name and dot notation. In other words, you don't need an instance to use this method. An instance method requires an instance exists first and the method be called on that instance. In the example shown on this slide, I'm showing you that a string literal with a value hello is really an object of type string. The string class has many instance methods defined on it, which we can use to manipulate strings. One of these is the toUpperCase method, which simply returns a string with all uppercase letters, so the result of this call would be a new string with the value hello all in capital letters. The most important difference to remember right now is that to use an instance method, you have to create an instance or object first. We've seen lots of examples of static methods since that's all we've used so far in the course. But in the upcoming videos, I'll be introducing you to a special class for reading input. With this class, we'll be using instance methods on a scanner object we create to get input from a user. We'll also be using special static methods on wrapper classes to pass numeric values out of strings. And as always, don't worry if you don't yet grasp all of these concepts. We're going to be going over them in much more detail very shortly. So that's it for classes and objects and the difference between static and instance fields and methods. Let's move on to the next video where we'll be talking about parsing data that's coming in as a string, and then we'll talk about getting some data from the user from the console. I think you'll find the next couple of videos both interactive and fun, so let's go. In the last video, we talked about static and instance fields and methods on the class. We also talked about a concept called instantiating a class, which creates an object or instance. We'll be using both of these features in this video. We're going to create an interactive application where a user will enter their name and year of birth, and then the application will calculate the current age of the user. Before we start though, let's talk about parsing data. When we read data in from either a file or from user input, it's common for the data to be initially a string, which we'll need to convert to a numeric value. Let's review what happens when our numeric data is really a string. You might remember we talked about this previously when we talked about operators in Java. You may remember that the plus symbol means something different for numeric values than it does for strings. You might also remember that most of the other operators aren't applicable to strings. Let's look at a slide we've seen before. You can see from this slide that having our data in string variables means we can't even do basic maths on our data. So let's review what this problem looks like in code. I've created a new project called reading user input and a main class with the main method. In this method, we'll add two variables which will emulate data coming in from a user, either from an input file, a console, or even some user interface. These variables are the current year and the user's date of birth. So now let's say we want to get the user's age from this data. So to get a person's age, we just subtract the user's date of birth from the current year and would be relatively close to their age in years. So let's add a print statement that will print out the age, and we'll just put the equation in the system.out.println statement. String current year equals double quotes 2022 semicolon. String user's date of birth equals double quotes 1999 semicolon. System.out.println opening parentheses double quotes age equals plus opening parentheses current year minus user's date of birth close both parentheses semicolon. Okay, so now we have a problem. And if we hover over the IntelliJ error, we find out that the operator minus cannot be applied to string and string. So let's try the plus operator, since the slide-on operators we just looked at indicated that the plus sign was a valid operator for strings. And the good news is that this compiles. So let's run this code. And you can see we get a number that doesn't look like an age. Well, actually this isn't a number at all, but a string. And what happened was the two strings, user's date of birth and current year, were not added together, they were concatenated together. Okay, hopefully that wasn't a big surprise since we covered this in the operators video. What happens if only one of our variables is a string? So let's make current year an int here and set it to the literal numeric value 2022. And that compiles, but if we run it, we get the same result. So what's our solution here if we really can't do anything about the fact that user's date of birth is given to us as a string? Well, to use our data, we have to parse or transform that string data and extract the numeric value from it. Since this is so common, Java provides ways to parse a string into a number. This is done using the wrapper classes we've seen before. You'll remember we used the wrapper classes to get min and max values. In this case, we're going to use a static method on the wrapper class to let that class do the transformation for us. There are other wrappers, each with its own parsing method, but these are the most common ones you'll probably use. So Java has come to our rescue, and we can use the method parseInt, which is a static method on integer. Let's use this in our code, and then we'll talk about it a bit. First, we'll add the call to the parseInt method on the integer wrapper class. Int date of birth equals integer.parseInt opening parentheses user's date of birth closing parentheses semicolon. Then we'll change the expression in the system.out.println statement. We'll change plus to minus, and we'll change the variable we're using from user's date of birth, which is a string, to date of birth, which is an integer. Okay, so what's this code doing on line 8? Well, you can probably guess what it's doing. It's converting a string with a value of 1999 and returning an integer with the value 1999. But what is this really? Well, we know integer is a class. It's not an object. On this class, there's a static method called parseInt that takes a string and returns an integer. And we just saw, to access static methods on a class, we have to use the class name and the dot notation and the name of the method. So in other words, what we're really doing is we're calling a method on the class named integer. We can only call static methods this way, so parseInt is a static method on the class integer. Let's run this code. And now we have a result that looks right. So that's good. We'll be using this method when we solicit our user's date of birth for our interactive program. Parsing a double is very similar. Let's look at a quick example of that for completeness. We'll add a string variable that represents what a user might enter if they were asked to give their age, but with partial years in the decimal part. We'll use the parseDouble method on the double wrapper and we'll print that out. String user's age with partial year equals double quotes 22.5 semicolon. Double age with partial year equals double dot parse double, opening parentheses, user's age with partial year, closing parentheses, semicolon. System.out.println, opening parentheses, double quotes, the user says his, plus age with partial year, closing parentheses, semicolon. And running that, we get another line that says the user says his 22.5. So this example didn't really use that double in any maths, but because it's a double, all the operators will now work on that parsed data. So now that we've covered dealing with numeric values that are in strings, let's talk about where that input might come from. This is often either in the form of an input file, a console, or some kind of user interface. For this video and the ones immediately following, we're going to be soliciting input from the console. When reading data from the console, we have some different options. Like system.out, Java provides system.in, which can read input from the console or terminal. It's not easy to use for beginners, and lots of code has been built around it to make it easier. System.console is Java's solution for easier support for reading a single line and prompting the user for information. Although this is easy to use, it doesn't work with IDEs because these environments disable it. Command line arguments can be passed in when we execute a Java program from a command line or terminal, and we can specify data directly in that call. This is very commonly used, but doesn't let us create an interactive application in a loop in Java. The scanner class was built to be a common way to read input, either using system.in or a file. For beginners, it's much easier to understand than the bare bones system.in. So let's get back to our code. We'll delete everything except for the local variable that we created for current year. First, we'll be looking at system.console, and I'll show you a way to run the code using IntelliJ's terminal. But for our final objective, and the challenges in following videos, we'll be using the scanner class, which we can run directly in IntelliJ. So next I'm going to set up two methods. We just want to set them up and have them return a dummy value for the moment as we plan out how we'll code the next parts. You'll remember we've done this before. We'll have two methods. The first will use system.console and the second will use scanner. Both will take the current year as a parameter, and both will return the message of how old our user is based on the birth year they enter, which we'll read from the console. Public static string get input from console, opening parentheses, int current year, closing parentheses, opening curly brace. Return double quotes, semicolon, closing curly brace. Public static string get input from scanner, opening parentheses, int current year, closing parentheses, opening curly brace. Return double quotes, semicolon, closing curly brace. You can see we're returning an empty string for now from each method, and we're passing in the current year variable we set up. And we'll next add the call to those methods in the main method. System.out.println, opening parentheses, get input from console, opening parentheses, current year, close both parentheses, semicolon. System.out.println, opening parentheses, get input from scanner, opening parentheses, current year, close both parentheses, semicolon. So the objective of each method is to first ask the user what their name is, then prompt them for their year of birth, and then we'll want to calculate and print out their age in years. So let's start with the get input from console method first. We're going to set up a local variable for the user's name and then call system.console.readLine, which can take, as one of its parameters, a string used for the prompt for user. We'll then print out the name we get from this method. String name equals system.console, opening and closing parentheses, .readLine, opening parentheses, double quotes, hi, comma, what's your name, closing parentheses, semicolon. System.out.println, opening parentheses, double quotes, hi, plus, name, plus, double quotes, comma, thanks for taking the course, closing parentheses, semicolon. Okay, so the first time we run this, we see we get an error. And you'll remember from the slide on ways to get input that we said that system.console can't be used in IntelliJ because IDEs disable the console. So this error is expected. Instead, we'll have to either run this from a command line or terminal session, and because IntelliJ enables us to have a terminal session inside of its application, we can use that. In IntelliJ, you should see at the bottom of the screen where your output is printed that there are the tabs. We want to select terminal, and now we'll type in Java src in main.java. Your main must start with a capital letter. Main.java is the name of our source file, and then we'll hit enter. Now the terminal window is prompting us to enter data. Then I'll type in Marty and press enter. And now the code completes with the message, "Hi Marty, thanks for taking the course." So we have confirmation that we got a name from the user, stored it in a variable, and printed it out later, so that's kind of fun. Our program is having a conversation with a user. Next, let's get the date of birth. We'll do the same thing by using system.console.readline and prompting the user with the information we want. Then we'll calculate the age. In this case, we're going to use integer.parseInt, passing it the string we just read from the console, and we'll actually return our calculation in a formatted string. String date of birth equals system.console opening and closing parentheses .readline opening parentheses double quotes what year were you born closing parentheses semicolon. Int age equals current year minus integer.parseInt opening parentheses date of birth closing parentheses semicolon. Return double quotes so you are plus age plus double quotes years old semicolon. And again we have to run this in the terminal session. Java src in main.java and pressing enter. We see the prompt for name again, and I'll just put Marty back in there, and now we'll get the next prompt. What year were you born? And I'm going to put 1966. And now there's our output, so you're 56 years old. Okay, so we've coded our first interactive program using system.console. So that was kind of fun, but you may be thinking that was kind of a pain to have to test and run it that way, and that's true. So in our next attempt, we're going to use a different approach using the scanner class, which does work inside the IntelliJ IDE. We'll look at this approach in the next video, but first we'll discuss an important concept called exception handling. This is a way to recover from errors that might happen in our code without actually terminating the entire process. We'll start that conversation in the next video, so I'll see you there. In the last video, we used the system.console.readline method to create an interactive program. We were able to run this from an IntelliJ terminal session. But we can't run this code from IntelliJ because IDEs disable the console. Let's try running the code from the last video using IntelliJ again. And we'll look more closely at the error we get. So when we try to run system.console in IntelliJ, it's actually giving us a null value. Normally system.console would return an object that is a wrapper to system.in, but now we get this exception. And unfortunately, we can't get this to work in IntelliJ's IDE. But what we can do is program our code so that we handle this situation. This is done by what's called catching and handling this exception. So what's an exception? An exception is an error that happens in code. Some types of errors can be predicted and named. Null pointer exception, which is the exception we saw when we tried to run our code using system.console in IntelliJ, is an example of a named Java exception. Java has many of these named exceptions, and if you go to the JDK's exception API page, you can see some of them listed here. We'll be getting deeper into exceptions later, but right now we want to try a different approach if we do get this error. We can do this by setting up the code to catch the exception. An exception is caught first by creating a code block around the code that might get the error. This is done with the try statement code block. The try statement actually has two code blocks. The first is declared directly after the try keyword, and this code block ends and is followed by the declaration of the catch keyword. The catch keyword includes the declaration of variables in parentheses and then has its own code block. So the format is the keyword try followed by an opening brace for the code segment. The closing brace is followed by the keyword catch in parentheses where a declaration is required. The declaration includes the type of error and a variable name. In this code, we show the type to be exception and the variable name, which can be any valid name, is just here right now. This is followed by another code segment, which is the code to handle or react to the exception or error that could be predicted. It's easy to talk about exception handling in code. So let's add the try and catch statement around our toSystem.out.println statements in the main method, then we'll talk about it. Try, opening curly brace, closing curly brace, catch, opening parentheses, null pointer exception, closing parentheses, opening curly brace. Closing curly brace. So here we have the start of the try statement before the method call that we know throws a null pointer exception when we run it in IntelliJ. We finish the code block after that statement and then add the catch keyword, which is required. This expects a declaration of the exception type, which we just said was null pointer exception. We also need to include a variable name. It's common practice to set this to E initially, but we can name this variable anything we want. And this needs to be a code block, and in that code block, we're just going to call the other method, which of course, we haven't yet implemented or built out. But now, if we run this from IntelliJ, we don't get any output because our second method doesn't yet run anything, but it runs in IntelliJ. This will still work calling the system.console method from your terminal session. So now we're ready to code the second method and use the scanner class. The scanner class is described as a simple text scanner which can pass primitive types and strings. To use the scanner class, we have to create an instance of scanner. You'll remember this means we're creating an object of type scanner. We'll use the keyword new to do it. The new keyword is used in what Java calls a class instance creation expression. In its simplest form, it's the word new followed by the class name and empty parentheses. And often in many cases, we can pass parameters in the parentheses as we saw with methods. And we saw that we could do this with the string class passing the text in the parentheses. For reading input from the console or terminal, we instantiate a scanner object using new followed by the scanner class name and passing in system.in in the parentheses. For reading input from a file, we instantiate a scanner object using new, again with the scanner class name, but pass in a file object in the parentheses. File is another class provided by Java for reading and writing files. We'll talk about file input later. Right now, let's build that second method, get input from scanner. And I'm going to make sure that I'm importing this java.util.scanner before I declare my class here. So if you get prompted for multiple options, make sure the java.util.scanner is the one you choose. We haven't talked about the import statement yet, but this statement lets us use classes from other people's code. In this case, Java provides a library of code which includes the scanner class in a library called java.util. Way back in section 4, when we configured IntelliJ with a number of different settings, I recommend that you enable these two options in the auto import menu. Add unambiguous imports on the fly and optimize imports on the fly. If you enable these options, then IntelliJ will automatically add and or remove import statements as required. Let's go back to the code so I can show you what I mean. Import java.util.scanner semicolon. So this import line we just typed is what IntelliJ will add or remove for you as needed if you enable those options I just showed you. I'm all for automation, and my suggestion is to leave those two options on, but the choice is yours. Right, moving on. Back to our method. Scanner equals new scanner, opening parentheses, system.in, closing parentheses, semicolon. It's common practice, as we've done here, to use a variable name which has the same name as the class, but uses lower camel case instead of upper camel case, which is used for class names. Now you've seen system.out before, and that dumps text to the console. In other words, it outputs information. And in fact, we've actually used that all the time in pretty much every project that we've worked on. So system.in, on the other hand, is the opposite, in that it allows you to type input into the console, which then gets returned back to the program. So that's what we're doing here when we're defining a variable of type scanner. So as mentioned previously, the case here is very important. So scanner is one of Java's built-in classes, and it allows us to read user input. So in other words, we can pass primitive types and strings using methods from this scanner. And notice also there's this new keyword that I'm using here as well, again on line 29. We use that to create what's called an instance of scanner, meaning that we are creating a new object of type scanner. Now, so far we've been using primitive types, or the string, which we've said Java lets us use like a literal. So we haven't needed to use the new keyword before this. Alright, so we've defined our scanner variable and set it to a new scanner object. Now I'm going to cut and paste the code from the getInputFromConsole method. So the scanner class has a method called nextLine, but unlike system.console.readLine, it doesn't support a prompt being passed in. So in this case, we need to split the prompt from the reading of the data when using the scanner, so let's do that now. System.out.println, opening parentheses, double quotes, hi, comma, what's your name, closing parentheses, semicolon. String name equals scanner.nextLine, opening and closing parentheses, semicolon. System.out.println, opening parentheses, double quotes, what year were you born, closing parentheses, semicolon. String date of birth equals scanner.nextLine, opening and closing parentheses, semicolon. Okay, so let's look at that first call to a scanner method. In this case, you see that we're calling a nextLine method not on the class spelled capital S scanner, but on our object, lower scanner. This is our local variable named scanner that we can use to execute instance methods on. In this case, the nextLine method is an instance method on scanner, and it doesn't take any parameters. We do the same with date of birth. And like we did before, we use integer.parseInt to transform the string the user will type in at the console with the date of birth in it to an actual integer data type so we can do some maths on it. Now the scanner has other methods on it that are similar to the integer.parseInt method, but for this example, I'm going to stick with this method to get data from the user. It actually makes the scanner code a bit less complicated. So let's run this code from IntelliJ. And now you can see it does run from IntelliJ and we get the same behavior as before. So now I'll enter Marty and 1966 again. Marty. 1966. So that's kind of fun, I think. But let's see what happens if our user isn't very good at typing and enters a year in the future or a year far in the past or even a negative number. So let's run it again. We'll enter Marty, then hit enter. Marty. Then we'll enter the year 2070 and hit enter. 2070. You can see we get, so you're minus 48 years old, which is probably not a good thing. And let's run it again. And this time we'll still put Marty in there, but now let's put in a birth date that's also not possible, like 1500. Marty. 1500. And we get, so you're 522 years old. So again, that's probably something we don't want a user to enter. In fact, if you Google how old the oldest living human is, it's about 120 years right now. Okay, let's do one more test. This time, again, we'll use Marty for the name, but now I'm going to enter a negative number and hit enter. Marty. Minus 1000. So, if we want to make this code more robust, we probably want to restrict the user to a range of values. But how do we do that? Well, for the console or terminal, we can't really do more than test the values, then prompt them to try again. And keep trying until they get it right. So what statement can we use to do something and then keep trying until they get it right? Did you guess the do-while loop? So you'll remember the do-while statement does something once and then tests a condition to see if it should continue looping. We'll end this video here and continue in the next video where we'll make our interactive program a bit more robust. So I'll see you in that next video.
It's break time. Do you like this video? Don't forget to subscribe to get new videos. Share this video to open new premium videos and ebooks. We'll be a Starfreelancer.
So in the last video, we left it where we had two methods implemented. The first used system.console and the second used the scanner class. We just tested the second method from IntelliJ with several variations of invalid data and confirmed our second method isn't very robust. It allows the user to enter a year of birth, which can't be correct. We're going to continue with our class and testing the scanner method to read input, but we'll first write a validation method. This method should make sure that the date of birth the user enters should not be any later than the current year, which we have set to 2022. We should also make sure that the year that's entered is greater than the current year minus 125 years, because we'll assume the oldest living human won't be older than 125 years old. This validation naturally addresses negative years as well. So let's create a new method called checkData. We'll pass it the current year we've set up in the main method and the date of birth the user entered. In this method, we'll pass that information with integer.parseInt. So the method is public static int checkData opening parentheses int current year, comma, string, date of birth, closing parentheses, opening curly brace. Int dob equals integer.parseInt, opening parentheses, date of birth, closing parentheses, semicolon. Int minimum year equals current year minus 125, semicolon. If opening parentheses, dob less than minimum year, closing parentheses, logical or operator, opening parentheses, dob greater than current year, close both parentheses, opening curly brace. Return -1, semicolon, closing curly brace. Return, opening parentheses, current year, minus, dob, closing parentheses, semicolon, closing curly brace. So, if the date of birth that's entered is less than the minimum year, which we set up to be the current year minus 125, or it's greater than the current year, we're going to pass back a value of -1. Otherwise, we'll pass back the age. The value -1 is used quite often to describe an invalid value, especially in the case of a method that should only have positive value results. So this method, if it returns -1, means the user entered some bad data. When the user enters bad data, we want to go through the process again, asking them to enter another year they were born. So our do-while loop will be after the prompt, what year were you born? But first, I'll create a Boolean variable called validDob and set it to false. This is going to be set to true only when the user enters a valid date of birth. We're going to create a local variable for age that we'll declare outside of the do block because we want to use it in the print statement after the looping ends. Inside the do block, we're going to prompt the user again that the year of birth needs to be between the range we specified. So for each instance the user enters a bad date, this prompt will be reprinted. Boolean validDob equals false, semicolon. Int age equals 0, semicolon. Do, opening curly brace. System.out.println, opening parentheses, double quotes, enter a year of birth greater than or equal to plus. Opening parentheses, current year minus 125, closing parentheses, plus, double quotes, and less than or equal to plus, opening parentheses, current year, close both parentheses, semicolon. Closing curly brace, while opening parentheses, validDob, closing parentheses, semicolon. So reviewing this code, we have a Boolean variable that is false and will be looping until that condition in the while parentheses becomes false. We start out with validDob false and that never changes. So if we run this now, we'll be in an infinite loop prompting the user indefinitely to enter the year they were born. So let's add the validation code. Where we get age, we'll replace that expression with a call to our validation method. I'm going to replace the two lines with the one that calls the new validation method. Instead of using a local variable to store date of birth, we'll just pass the result of scanner.nextLine as an argument directly to our validation method. Age equals check data, opening parentheses, current year, comma, scanner.next line, opening and closing parentheses, semicolon. Valid DOB equals age less than 0, false, colon, true, semicolon. Okay, so let's run that. I'm going to enter Marty as before, and now you see that we have an extra prompt. Enter a year of birth greater than or equal to 1897 and less than or equal to 2022. So let's run through the same numbers we did before. First, I'll enter 2070, a date in the future, and hit enter. And you can see that we are right back at that prompt asking for a year between 1897 and 2022. So the next one we tried was the year 1500, which would make our user a lot older than 125 years old. And we are back at the prompt, meaning the date entered wasn't very good. And next we'll try a negative date of birth and put in -1000 and hit enter. And we're still in the loop. We still have yet to give the program a valid date of birth. So finally, let's put in 1966. And sure enough, the loop ends and gives us the result, so you are 56 years old. So that all worked, and now we've successfully created a program that will continually prompt a user for a valid year, but we still have one more problem. What happens if the user enters in a non-numeric value? So let's run this code and see what happens. We'll enter Marty and hit enter, and then at the next prompt, we'll enter the value 196C and pretend like we just made a typo. And you can see that our application sort of crashes with an error, another exception called number format exception. We have no checks in place for this kind of bad data. So let's add that, but this time, let's try another example of the try statement. Try, opening curly brace. Closing curly brace, catch, opening parentheses, number format exception, bad user data, closing parentheses, opening curly brace. System.out.println, opening parentheses, double quotes, characters not allowed. Try again, closing parentheses, semicolon, closing curly brace. So here, we're catching the exception, which we just saw was number format exception. Now the reason you create a variable in the parentheses of the catch phrase is if you wanted to access information about the exception, you could use that variable. We'll explore that more later when we cover exceptions much more thoroughly, but it's required to set up a variable this way even if we aren't going to use it. In this case, all we're going to do is print an extra statement that they entered characters, so let's try running this again. It's always good to retest your code with previous scenarios when you edit the code, so we'll run through all of our test scenarios again. First we'll enter Marty and get the prompt for date of birth, and then I'll enter 2070 as I did before. Then the prompt again. So our next test case was 1500, so let me type that in and press enter. And we're still in the loop because that date was invalid. So next was -1000. I'll enter that in there. And there's our prompt again, and now we'll try out our new test case. If you remember, that was 196C. And we have an extra message there. You can see characters not allowed, try again, and then the usual prompt. So now finally, let's put a valid birth date in the year, the same as before, 1966. And now the code executes cleanly and gives the result, so you are 56 years old. So in the past two videos, we learnt two different ways to get user input. We transformed string data to integer data so we could do some calculations. We learnt that system.console doesn't work in IntelliJ, but Scanner does. We saw that we can use exception handling to check which way will work, and the code will execute a different method if run in IntelliJ or on the command line or terminal. We also added validation to our second method, as well as a do-while statement to keep trying to get a valid date of birth from the user. In the next video, I'm going to give you a challenge so you can try both the scanner and some loop statements on your own to meet the requirements of the challenge. So I'll see you in that next video. Alright, so we've covered a lot of ground in the last few videos, and now it's time for a challenge. This is the Reading User Input Challenge. So the challenge goes like this. In this challenge, you'll read 5 valid numbers from the console entered by the user and print the sum of those 5 numbers. You'll want to check that the numbers entered are valid integers. If not, print out the message invalid number to the console, but continue looping until you do have 5 valid numbers. Before the user enters each number, prompt them with the message enter number #x, where x represents the count, 1, 2, 3, etc. And as an example there, the first message would look something like enter number #1, the next enter number #2, and so on. And so, the hints for doing this are, firstly, use a while loop or a do while loop. Use a scanner object and the next line method to read input as a string. Use integer.parseInt as we did in the previous videos. You'll need some local variables to keep track of the count of valid integers as well as the sum of the integers. So that's it. See if you can figure it out. Pause the video now and try out that challenge. And once you're ready to see my version of the code, come back and we'll go through it. So pause the video now. Okay, welcome back. Hopefully you managed to get it working. So let's break down this challenge into smaller pieces. I've already created a project called Read User Input Challenge and have the main class ready with the main method. So first, let's set up some variables. We know we need to read 5 numbers from the console as well as count them and in addition, calculate their sum. And we know we want to use a scanner instance. So let's add those local variables to start with to the main method. Import java.util.scanner semicolon. Scanner equals new scanner opening parentheses system.in closing parentheses semicolon. Int counter equals 1 semicolon. Int sum equals 0 semicolon. So first, we've created an instance of the scanner class, meaning an object, a scanner object. And we've used a new keyword and passed in system.in to the parentheses after the class name. You remember, this is how we can create a scanner object. We can assign that back to a variable called scanner, all in lowercase, of type scanner, which again is the class name with an uppercase S. And we also have a counter variable. We can initialize that to 1 and simply use that when we prompt the user. And we have sum where we'll be summing up all the numbers the user entered. So now let's add the while loop. First, counter is a little misleading. It's supposed to count the number of integers the user entered, and we're starting out with 1, even though the user hasn't entered any. We could have just as easily started with 0, so if you did that, that would also be fine. So starting with the loop, because we started with 1 in counter, we'll check for the condition that counter is less than or equal to 5, and keep looping if it is. While opening parentheses, counter less than or equal to 5, closing parentheses, opening curly brace. System.out.println, opening parentheses, double quotes, enter number hash plus counter plus, double quotes, colon, closing parentheses, semicolon. String, next number, equals scanner.nextLine, opening and closing parentheses, semicolon. Counter plus plus, semicolon, closing curly brace. Okay, so here we prompt the user to enter a number and we include the counter. Since we're starting with 1, we can just put the counter variable there in line 13. Next, we use scanner.nextLine to get data from the console as a string. And we'll return that to a string variable called nextNumber. And then we increment counter. This code is assuming the user entered valid data and doesn't actually do any validation or calculations yet. It's just asking the user to enter 5 pieces of information and hoping the user enters integers. So if we run that, we'll get prompted 5 times, but we can pretty much enter whatever we want each time. 1. ABC. 3.5. 3. 10,000. So we're getting there, but now we really do want to check to see if the user entered a valid number. You might remember we did that in a previous video with exception handling. And we'll do that here. We'll add a try-catch block. We'll try to parse the string they entered using integer.parseInt. If that gives an error, then we'll handle it. And you'll remember the challenge wanted us to print invalid number. And then we'd ignore this entry for both the counter and the summation part. So let's code that now. We start with a try statement on line 15, then on the next line we'll try to parse the value the user entered using the wrapper class integer and the method parseInt. Let's type this in and talk about it once we have it all in there. Try, opening curly brace, int number equals integer.parseInt, opening parentheses, next number, closing parentheses, semicolon. Sum plus equals number, semicolon. Closing curly brace, catch, opening parentheses, number format exception, NFE, closing parentheses, opening curly brace. System.out.println, opening parentheses, double quotes, invalid number, closing parentheses, semicolon. Closing curly brace. Okay, so we're using a try-catch block because we think an exception might happen when we go to try to use integer.parseInt on the data the user entered if they entered bad data. So that's why that call to the method is in the try block. If an exception does happen, and that exception is a number format exception, like we saw before, then we want to catch it. So we have the catch statement, and it's got the parameter with a type of number format exception and a parameter name of NFE, which could be any name you want. In that catch block, we print invalid number. So coming up here to line 16, if that throws an exception, anything else in that try block is skipped, so lines 17 and 18 are skipped. You can see I've added line 18 to add the valid number to sum. If the code gets to line 18, we know the number is valid because it was successfully parsed. So we can add it to sum this way. So the only thing we haven't done yet is print out that sum variable. And we'll do that after the while loop and before the end of the main method. System.out.println, opening parentheses, double quotes, the sum of the 5 numbers equals plus sum, closing parentheses, semicolon. So let's run this and see what happens if we try to enter some bad data. I'll try 4.0 first. And we get invalid number, so that's good, and the counter is still 1 in the next prompt. So let me try 4.5, and again invalid number. So next I'll type 2, and that takes us to the second number. You can see that in the prompt. And this time I'll try letters, so I'll type 8, and we get invalid number again. So the same message, and next I'll try the letter B, and same thing. Okay, so our validation and counting code is working, so I'll just finish off these other iterations and type in 2 each time. And that finishes the loop, and we get a sum of 10. So there you have it. We've done what the challenge asked us to do. But how would you code it if you wanted to allow the user to enter decimal numbers? Do you know how you do that? Let's just change the code and show you that for that scenario, we change the types of a few variables and would also use the double wrapper. You remember that a decimal number can be either a double or a float, and we've stated in previous videos that double is the preferred type in Java, so let's rewrite our code to use doubles. I know this wasn't part of the challenge, but I do like to show you variations when I can, and this is a good one, I think. So in this case, we just have to make a couple of changes to let the user enter in either whole numbers or decimal numbers to consider them valid. So we'll change the sum variable to a double. And we can still initialize it to 0 as before. We'll comment out the code for integer.parseInt on line 16, and we'll instead insert a line that uses the double wrapper and the parse double method. That gets assigned to a variable called number like before, but this time number is a double. Double number equals double.parseDouble, opening parentheses, next number, closing parentheses, semicolon. Okay, so we've made a few changes to the code, and now if we run it, we'll see what happens as we enter different kinds of data. I'm going to start with the letter A to make sure we still get a number format exception, and our code is still handling this type of bad input. And you can see that it does. And next, I'll enter some decimal numbers, first 1.1, then 2.22, then just plain 3. So we're throwing in an integer value here for testing, and then we'll finish with some more decimal numbers. And now we've got code that adds up 5 numbers either whole numbers or decimals, or a combination, and gives us a decimal value as the result. Okay, so I also said you could do this with a do-while loop. So let me show you that in case you did use a do-while loop. And this again is a pretty easy change. So first, we change the keyword while to do at the start, and we get rid of the condition there. And then on line 23, after the closing brace, we add the while counter less than or equal to 5, and we can't forget the semicolon. IntelliJ is pretty good at reminding us about that. And that's it. We've now coded it with a do-while loop and not a while loop. And again, we can run that like before. This time I'll put in the string ABCD. And then we have the message invalid number, and now I'll enter a mix of integers. 1, 2. Now I'll type in some decimal numbers. 3.0, 4.5, 5.9, and there you have it. The code sums up all 5 numbers. Okay, so I hope that was a good challenge for you and you had some fun with it. You can see, with a little bit of code, you can have a conversation with your user and produce some kind of output for them based solely on their input. You can guide them to appropriate responses and continue to loop until they've entered all the data needed to complete the job. So we've got one more challenge for you, and again this will give you an opportunity to create an interactive program. We'll be giving you that challenge in the next video and walking through the solution together. So I'll see you in that next video. Alright, so it's time for your next challenge. This is the minimum and maximum challenge. So this challenge is similar to the last one in some ways. You'll be using an endless loop which prompts the user to enter a number or any character to quit. Validates if the user entered data really is a number. You can choose either an integer or double validation method. If the user entered data is not a number, quit the loop. Keep track of the minimum number entered. Keep track of the maximum number entered. If the user has previously entered a set of numbers or even just one, display the minimum and maximum number which the user entered. So you want to create a loop that continues to process until the user enters non-numeric data. You'll prompt the user to enter a number or type a character to quit each iteration. After the user enters some data, you'll read the input as a string and then test if it can be parsed to a number. You can decide if you want to solicit integers or decimal numbers from the user. If the user entered a valid number, you'll want to see if it is less than what you have for a minimum number, and if it is, you'll set that to the current number. You'll do the same check for maximum number. For example, after one valid numeric entry, minimum and maximum numbers should be the same number. So that's it. See if you can figure out that challenge. Pause the video now and try it out. And once you're ready to see my version of the code, come back and we'll go through it. So pause the video now. Okay, welcome back. Hopefully you managed to get that working. So let's get started. I've created a project called MinMax Challenge with a main class and main method. First thing we need to do is create our scanner, so let's do that as we've been doing in recent videos. We'll import the class from java.util and we'll create a variable named scanner, which will be of type scanner. We create a new instance with the new keyword and the class name scanner passing system.in in the parentheses. Import java.util.scanner semicolon. Scanner equals new scanner opening parentheses system.in closing parentheses semicolon. Next, we'll set up some variables, one for the maximum number, one for the minimum number. I'm going to use doubles, letting the user enter decimal numbers, but maybe you just used integers, and that's fine. And here, we'll also create a variable for the number of times the loop executes and call that loop count. We'll set up the endless loop, and you'll remember we can do this just by putting true in the loop expression. Double max equals 0 semicolon. Double min equals 0 semicolon. Int loop count equals 0 semicolon. While opening parentheses true closing parentheses opening curly brace. Closing curly brace. Okay, so obviously we're not ready to run this yet because our loop would start, do nothing, but hang our system. So now we'll prompt the user to enter some data, and we'll read that data using scanner.nextLine. And here, we'll set up the try-catch statements we'll use. In the try, we'll be using the double wrappers pass double method to pass the value entered by the user. If that throws an exception, and you'll remember it will be a number format exception, then the catch block will break out of the loop. So let's start adding this code. System.out.println, opening parentheses, double quotes, enter a number, comma, or any character to exit, colon, closing parentheses, semicolon. String, next entry, equals, scanner.nextLine, opening and closing parentheses, semicolon. Try, opening curly brace. Double dot pass double, opening parentheses, next entry, closing parentheses, semicolon. Closing curly brace, catch, opening parentheses, number format exception, NFE, closing parentheses, opening curly brace. Break, semicolon, closing curly brace. Okay, so we're almost there. And we could run that, and the code will keep prompting us for data until we enter a character or string or any non-numeric value. I'll enter 15.5, a decimal value, and then 1, a whole number, and then Q, and yes, the loop breaks when I enter Q. So that's all good, but next we need to add the code that figures out the min and max number. We'll do all that in the try block after we pass the entry. Double valid num equals. If opening parentheses loop count equals 0 logical or operator, valid num less than min, closing parentheses, opening curly brace. Min equals valid num semicolon, closing curly brace. If opening parentheses loop count equals 0 logical or operator, valid num greater than max, closing parentheses, opening curly brace. Max equals valid num semicolon, closing curly brace. Loop count plus plus semicolon. Okay, so looking at this code, we want to assign the pass string on line 17 to a local variable of type double, and we're calling it valid num. Next, we want to set min and max to be the first value we get from the user, so if loop count is 0, we set min here on line 19. And we do the same thing for max on line 22. Since we're using loop count, we have to remember to increment loop count, and we do that on line 24. When it's not the first iteration of the loop, meaning loop count is greater than 0, we still want to set the min value. Meaning, we want to set min value if the value entered by the user is less than our current minimum value. So we use a conditional OR on line 18 and again on line 21 for the max value. Either one of those conditions on line 18 will result in min getting set to the value just entered by the user. And that's true too on line 21, where we're checking if the new value just entered by the user is greater than max, the current value we have in the max variable. We could run that now, but we haven't yet coded the final results. So let's add a couple more statements. These will get printed after the while loop terminates. So if the user never enters any good data, this means loop count will still be 0. So if loop count is greater than 0, we print the min and max, but otherwise we just print that no valid data was entered by the user. If opening parentheses, loop count greater than 0, closing parentheses, opening curly brace. System.out.println, opening parentheses, double quotes, min equals plus min plus double quotes, comma, max equals plus max, closing parentheses, semicolon. Closing curly brace, else opening curly brace. System.out.println, opening parentheses, double quotes, no valid data entered, closing parentheses, semicolon. Closing curly brace. And running that, first we'll try just entering Q to start. And we get our message that no valid data is entered. And now let's run it and enter some data. I'm going to enter a combination of whole numbers and decimals and include a negative number too. 101.1, 5, minus 65.2, minus 75, 3333.33. And now let's call it done and enter Q. And so our code successfully figured out from that set of data we provided that the minimum number entered was minus 75 and the max number entered was 3333.33. All right, so that's it. That's one solution to the challenge. Your solution could have used any type of loop statement. And maybe you only let them enter integer values and you used integer.parseInt. You may have also come up with a different way to initialize the min and max values and then compare those values rather than just set those values on the first iteration of the loop. And maybe you validated your code only allowing positive numbers or some range of numbers. And this is what makes coding so interesting, because we didn't specify every detail like which loop to use or what type of numeric variable to create, and we left some of the questions about the requirements to be decided by you. I hope you tried to be creative with your own solution, and I hope you enjoyed this challenge and learnt a lot from it. This completes our section on flow statements in Java. But don't worry, you'll be seeing them for the rest of the course because they are intrinsic to programming with Java. The next section starts our object-oriented programming part of the course, which means we'll be getting introduced to one of Java's biggest benefits. So let's get started. I'll see you in the next video. Welcome to section 7 of this course. Tim Buchaka here, and this is part 1 of a 2-part section detailing or dealing with object-oriented programming. So part 1, you're going to learn about the fundamentals of object-oriented programming, starting first with the structures we'll be using, specifically classes, objects, and constructors. Along with these structures, we'll be learning about some fundamental features of object-oriented programming. These are inheritance, encapsulation, polymorphism, and composition. In part 1, we'll cover inheritance, and in part 2, we'll go over the other 3 features. So let's make a start on this and get you up to speed with object-oriented programming. In this video, we're going to start talking about object-oriented programming. What is object-oriented programming? Object-oriented programming is a way to model real-world objects as software objects which contain both data and code. OOP is a common acronym for object-oriented programming. And in particular, we'll be talking about classes, which is a fundamental component of object-oriented programming in Java and other languages for that matter. It's sometimes called class-based programming. Class-based programming starts with classes, which become the blueprints for objects. But what does this really mean? So, to start, we need to understand what objects are. They're really the key to understanding this object-oriented terminology. So what I'd like you to do is just have a look around in the area you're sitting in right now. And if you do that, you'll find that there's many examples of real-world objects. For example, I'm sitting here and I can see a computer, I can see a keyboard, I can see a microphone, I can see shelves on the wall, I can see a door. All of these are examples of real-world objects. Now, real-world objects have 2 major components, state and behavior. So state, in terms of a computer object, might be the amount of RAM it has, the operating system it's running, the hard drive size, the size of the monitor. These are characteristics about the item that can describe it. We could also describe animate objects like people or animals, or even insects like an ant. For an ant, the state might be the age, the number of legs, the conscious state, whether the ant is sleeping or is awake. In addition to state, objects may also have behavior or actions that can be performed by the object or upon the object. Behavior for a computer might be things like booting up, shutting down, beeping, or outputting some form of sound, drawing something on the screen, and so on. All of these could be described as behaviors for a computer. For an ant, behavior might be eating, drinking, fighting, carrying food, those types of things. So modeling real-world objects as software objects is a fundamental part of object-oriented programming. Now, a software object stores its state in fields, which can also be called variables or attributes. And objects expose their behavior with methods, which we've talked about before. So where does a class fit in? Well, think of a class as a template or a blueprint for creating objects. Let's take another look at the class. The class describes the data, fields, and the behavior, methods that are relevant to the real-world object we want to describe. These are called class members. A class member can be a field or a method or some other type of dependent element. If a field is static, there is only one copy in memory, and this value is associated with the class or template itself. If a field is not static, it's called an instance field, and each object may have a different value stored for this field. A static method can't be dependent on any one object state, so it can't reference any instance members. In other words, any method that operates on instance fields needs to be non-static. So these class or member fields can be thought of as variables, though it's more common to call them fields or attributes. In this video, we'll be looking at instance fields to describe our objects. We'll be describing static members in greater detail later in this section's videos. So as it turns out, you've been using classes all along. And I'm sure that you've seen the keywords public and class in the code we've completed to date. And you can actually see it on the screen right now, public class main. So what that is, that's actually a statement which describes a class in Java. So a question that might come up at this point is, why do we need to bother about classes? Or what benefit do classes give us in our everyday programming? Well, think back to the basic data types that we've worked on, the primitive data types that we've explored so far, such as int, short, and those types of things. They are all basic data types, but they are fairly limiting. There's only so much you can do with them. So, a case could be made here that a class could be thought of as a powerful user-defined data type. That's not really correct in the true meaning, but it gives you an idea of what classes are. They really enable you to have sort of a powerful user-defined type, like a regular data type on steroids, if you will. So, to take this a little bit further, let's create our first real class. As you can see on the screen, every time we create a new project, and here we've created a project called Classes Part 1, we've been creating a new class, usually one called main, with capital M, and we generally add a method called main, which I've already done here. So now, let's create another class. First, we'll expand the project panel. You recall, I usually work with it closed, but now I'll expand it by clicking on the Project Vertical tab on the left. So then, we'll click down where it's got SRC for source. Click on that and right-click. Select New, select Java class, and we're going to create a class with the name of car. CAR, making sure the first letter is capitalized as we've recommended previously. When you're creating classes in Java, the first letter should be an uppercase letter. So, first thing what I want you to notice is this public class car. So, that's actually the statement to create a new class with the name car. Now, the public keyword is an access modifier. This lets us determine what access others will have to this new class that we're creating. We haven't talked about how classes are organized, so let's just look at that briefly before we talk about access. Classes can be organized into logical groupings, which are called packages. You declare a package name in the class using the package statement. If you don't declare a package, the class implicitly belongs to the default package. The default package is all we've used so far because we haven't yet introduced the package statement. We're not going to get too deep into packages just yet, there's more on them later in this section. But you do need to understand that classes are grouped into packages to understand access modifiers. A class is said to be a top-level class if it is defined in the source code file and not enclosed in the code block of another class, type, or method. A top-level class has only two valid access modifier options, public or none. So the word public gives unrestricted access to a class. Any code, anywhere, has access. When we get to Java's modules, you'll see that we can refine this further, but for now, public means any code can access this class. Now usually, at least initially anyway, we're going to be using the public modifier on the classes we create. And when there is no modifier specified at all, Java by default implicitly allows package private access. This means that classes grouped into the same package can access the class. So that's our class defined. But at the moment, it's not very useful because it doesn't actually do anything. Literally, we've created a shell. It's like creating a new blueprint. So remember that a class is a blueprint for an object that we're going to be creating. And in this case, it's like virtually starting out on a brand new blueprint and we haven't done anything yet. We've called the blueprint car, but we haven't described anything else about what we're building at this stage. So what we need to do is create some variables that are part of this class. Now to date, you've seen variables used inside a method or code block. And these were called local variables because they were local to or actually belonged to that method or code block. But we couldn't access those local variables outside of the method or block we declared them. Classes allow us to create variables that can be seen or accessible by any code block within that class. But we can also allow access from outside the class itself. When we're designing our class, there are some things we want the public to know and some things that aren't necessary for the public to know. And we can have a public interface. This is only the information the outside world needs to know to use our class. But we'll also have a non-public interface. This is information we may want to share, but not always, and not with everyone. We may need to share some information with our own company and other departments, while other data might need to be shared with our manufacturers and dealers, but not with the public. Java gives us the ability to have this kind of control by specifying different access modifiers for each member in a class. An access modifier at the member level allows granular control over class members. The valid access modifiers are shown in this table from the least restrictive to the most restrictive. Here, you can see that public is still an option for class members like it was for the class, and this means there is unrestricted access to the member. We also still have no modifier, which means package or package private by default, so that any class in the same package can access this member. We could also use private, which is basically the opposite of public, and that's where no code outside the class can use this field or method. And finally, there's the protected modifier. This one also allows package access, but it also permits subclasses to access this member. As a general rule, all your fields should be private, unlike the class where we usually use public. So why do we want to make all the fields on a class private? Doesn't this mean that nobody can access them? This practice has a name, encapsulation, and it's a key fundamental rule of object-oriented programming. Encapsulation in object-oriented programming usually has two meanings. One is the bundling of behavior and attributes on a single object. The other is the practice of hiding fields and some methods from public access. In general, when we talk about encapsulation, we're talking about information hiding or hiding the internal workings of a particular object. When we make our attributes private, we can then create methods to access the data, each with different degrees of access allowed as needed. So what we're going to do first is we're going to create some fields for our class. This is going to look familiar to you and is a lot like the way we've created local variables previously. We'll add some fields which are characteristics of the car. So what kind of things might you be interested in when describing a car? Maybe things like the make or manufacturer, the model, its colour, how many doors does it have, is it a convertible? So let's add these fields, then we'll talk a little about them. Private string make semicolon. Private string model semicolon. Private string colour semicolon. Private int doors semicolon. Private boolean convertible semicolon. So here we've created 5 fields. These are fields because they are defined in the class's code block or the body of the class and not in a method. When we create an object from this class, then the values we assign to these fields represent the state of the object. Unlike local variables, class variables should have some type of access modifier declared for it. If you don't declare one, Java declares the default one, package private, implicitly. So here, we've set the access modifier to be private in all cases, which we've said will help us encapsulate this class. We'll want to control access to these fields, and this starts by making them private. Later we'll add the methods to access them. The other thing you might have noticed is that we're not actually assigning any values yet. This is because, at this point, we don't know what these values might be, and they'll likely be different for each instance anyway. If we were creating a real application, we'd likely have a lot more fields, but we'll keep this simple to start with. Let's add a method now that will print out this information about the car object. We'll call this method describeCar and make the method public. This method is not static because we're accessing instance fields on the class. Methods, unlike fields, will often be public because we want to give users a way to interact with the object. Public void describe car, opening and closing parentheses, opening curly brace. System.out.println, opening parentheses, doors plus, double quotes, door plus. Color plus, double quotes, plus. Make plus, double quotes, plus. Model plus, double quotes, plus. Opening parentheses, convertible, double quotes, convertible, colon, double quotes, close both parentheses, semicolon. Closing curly brace. Okay, so we've created our first real template class called car, and we've set up some attributes on car. This feels like a good place to end this video. In the next video, we'll be using this template to create an object of type car. So I'll see you in that next video. Okay, in the last video, we created a car class in the Classes Part 1 project, and we declared several private fields on it, as well as a method called describeCar. So the next thing we need to do is we need to create an object from this class, because if you recall, the class is just a template. We need to create an object which will sort of take that blueprint, that definition that we've defined in the class, and instantiate or create an object that we can then start using. So to do that, what we need to do is go back to the main class we started out with, and I'll just click the tab that says main.java. And what we can do in here is we can actually build an object and base it on that car class. So what we now need to do is create that object. So how do we do that? Did you guess that you'd use the new keyword? So let's do that. First, we'll declare a variable of type car, calling the variable simply car, and then we'll assign it a new instance of the car class. Car equals new, car, opening and closing parentheses, semicolon. Car.describe car, opening and closing parentheses, semicolon. Okay, so now what happens? And if we run that, we get zero door null, null, null. So what's happening here? Why did we get null when we were expecting color, make, and model? Null is a special keyword in Java, meaning the variable or attribute has a type, but no reference to an object. This means that no instance or object is assigned to the variable or field. Fields with primitive data types are never null. So what is the color, make, and model of the car null? Well, all of these fields were declared with a string data type, and we haven't assigned values to them. We know from previous lectures that strings are really objects, not primitive data types, so Java assigned each a null reference. The other thing I want you to notice about the output we got was that doors was printed with the value 0 here, and that the word convertible wasn't printed in the output. So how is that possible? We didn't set doors or convertible to any values in our class, but we didn't get any errors when running this code. And now we're seeing another difference between local variables and fields declared on a class. And this is that a field with a primitive data type will get assigned a default value by Java. Fields on classes are assigned default values intrinsically by Java, if not assigned explicitly. So, because we didn't assign any values to our fields, Java assigns some values for us by default. Java will set any numeric primitive type to a 0. For doubles and floats, the numeric literal which is implicitly assigned is the decimal number 0.0. A Boolean field is assigned false by default, and any other type will be null. So now, let's assign some of our own default values to these attributes. This means that every object that's instantiated will get assigned the default values we declared here instead of Java's implicit values. And now, running our code in main.java. We get two-door grey Tesla Model X convertible. So every car object we create will have these values by default. But that's not what we really want either. How do we get and set the make, model, and colour of our car each time we create a car object? Since we made these fields private, we can't use the dot notation with the variable name to set the value. Let me show you what I mean. Let's try accessing these fields directly in the main method. Car.make equals double quotes Porsche semicolon. Car.model equals double quotes Carrera semicolon. Car.color equals double quotes red semicolon. You can see when we try this, we get errors on all three of those lines. We've defined these fields as private on the car class, and because of that, we can't set the values on any car object we create this way. So let's comment this code out for a moment. We also can't access those values directly in an expression. For example, we couldn't just print that data out in the main method of this main class. System.out.println, opening parentheses, double quotes, make equals, plus, car.make, closing parentheses, semicolon. System.out.println, opening parentheses, double quotes, model equals, plus, car.model, closing parentheses, semicolon. Again, we get compiler errors saying that these fields have private access and our main class isn't allowed to access them. So other than the describe car method, how does outside code get access to this data? We could make all of these fields public or package, but we've said this is bad practice, so we're not going to do that. What we're going to do is allow access to this data, either to set it or get it, through methods on this class. These are a special set of methods called getters and setters. So what are getters and setters? A getter is a method on a class that retrieves the value of a private field and returns it. A setter is a method on a class that sets the value of a private field. The purpose of these methods is to control and protect access to private fields. Another important aspect is that the getter and setter method signatures are part of car's public interface, but the attribute names and types aren't. This means that we can change things internally, like the name or type of an attribute, but as long as we use the same getter and setter method, these changes should have no effect on code that uses our class. Our internal changes are hidden from our users. The getter method usually just returns the value of a private attribute. It's usual to name a getter method with a get prefix, followed by the field name in lower camel case, but this is not required. You could have getter methods for attributes that are not really declared on your class, but that are derived in some way. A setter method may simply just assign the argument passed to the attribute, but it often contains code to validate data, check additional security requirements, ensure immutability of the field value, or any other code required to protect and validate an object state. It's usual to name a setter method with a set prefix, followed by the field name, in lower camel case, but again, this is matter of form. There may be many cases where we won't have any setter methods for some of our private fields. Maybe this is data only needed within the class itself and doesn't need to be exposed to the outside world. So let's first add a getter method. Going back to the car class, we'll add a method on line 9, which will get the make on car using a method. Public string get make, opening and closing parentheses, opening curly brace. Return make semicolon, closing curly brace. Okay, so this method is public, but notice we don't use the word static here. When writing methods that use non-static fields, your method can't be declared static. And the getter will usually return the type that the field is, so string in this case. And then we just return the field name, make. Even though make is declared on the class, we can refer to it from code in our method as we are showing here. To create the other getter methods, we could copy and paste this code 4 times and change the name and the attribute returned in each instance. But in general, you won't really be manually typing in the code for your getter methods. IntelliJ has features to generate code for you, including one to create a set of getter methods, so let's do that for the next 4 attributes. I'll set my cursor under that first getter method, and then I'll select the code menu item and generate, and if you click on that, you'll see there's a lot of options. We'll select getter. Now all the attributes are listed here that don't already have getters, so I'll select the remaining 4 by holding Shift and pressing the down arrow key. And now we have 4 new public methods, getModel, getColor, getDoors, and finally, isConvertible, a method that has the prefix is and not get, which is a naming standard for a getter for a Boolean field. So let's use these getters in our main method. In each println statement, I'll change the code to use the corresponding getter method. When I delete the field name in IntelliJ, I can pick the getter method from the list displayed. And you can see we've eliminated our errors in the main method. Let's run this now. And you can see we can now use the make and model data in our own output string. We're also still calling the describe car method that gives us all the information in a single line. So since this video is getting a bit long, we'll stop it here. In this video, we've talked about encapsulation, getters and setters, and we added getters for our 5 private fields, both manually, as well as using IntelliJ's generation feature. In the next video, we'll be adding setter methods and talk more about some reasons to use setters. So I'll see you in the next video. So in the last video, we set up getter methods for all of the private attributes on our car class. We talked about best practices for fields, that in general, fields on classes should be private and a getter method should be created to access those fields. This provides encapsulation of the internals of our class and supports maintenance of a public interface that doesn't have to change, even though our class might. In this video, we're going to be setting up and talking about setter methods, which set data on the objects. We'll end this video by creating more objects out of the car class and talking more about that process. We'll be using the code from the last video where we ended it with the main and car classes in the classes part 1 project. So now let's add a setter method in the car class. I'm going to set this up, then we'll talk about it. Public, void, setMake, opening parentheses, string, make, closing parentheses, opening curly brace. Make equals make semicolon, closing curly brace. So we have a public method that doesn't return anything. It's void because remember, the setter methods set data, they don't retrieve it. And the parameter is going to be string because that's what we're setting. The field make is a string and we'll use string as our parameter type. And what we want to do is assign the field on our object, make in this case, to the value passed as an argument to the method. But is that what this is doing? You'll notice that IntelliJ has underlined make in every instance here. If we hover over each of these, IntelliJ is giving us a different warning. Hovering over the parameter, we get reassign parameter. Hovering over the first make, we get the warning the value make assigned to make is never used. And finally, hovering over the second make in that statement, we get yet another warning message variable make is assigned to itself. That introduces another problem. Now, the problem here is we've got 2 different types of variables. If you think about it, we've got the field named make that we have defined up here, but we've also got another one in here called make. Now obviously, this one here is a parameter that's been passed to this method. In the code, as we've written it, we're not really setting the field named make to the parameter named make. What we're really doing here is assigning the parameter make to itself. So how do we distinguish between the two? Because as far as IntelliJ or Java is concerned, we need to be specific to say which one we want to update. What we want to do here is we want to actually update this field, private string make, with the contents of the parameter that was passed to us and updated in here. So how do we do that? Well, it turns out there's a way to do that, and that's with a keyword we haven't yet seen before called this. This is a special keyword in Java. What it really refers to is the instance that was created when the object was instantiated. So this is a special reference name for the object or instance which it can use to describe itself. And we can use this to access fields on the class. So because we're trying to setMake the field here on the left side of the assignment operator, we want to specify that the make field we want to use to assign a value to is the make field on the object and not the make method parameter. So let's add the keyword this to our code. This.make equals make semicolon. And now all the warnings are gone. So what that's done now is it said, update this variable here, private string make, with the contents of the parameter make that was passed to us. So that's a way of updating the make attribute on car using a method instead of trying to access it directly. We'll go back to the main method and replace that first commented line with code that calls this new setter method on car. Car.setMake, opening parentheses, double quotes, Porsche, closing parentheses, semicolon. And now if we run this, we can see that our car isn't using the default make, but is using the make we set it to, Porsche, in both of these cases. So again, we don't really want to manually code all of these setters, like we did this first one. We'll use IntelliJ code generation to create the rest of the setters for us. We'll set our cursor after the last method, setMake, but before the describeCar method, and then select code from the toolbar items, then generate, then we'll select setter. Now we can pick our 4 remaining attributes as we did previously with the getters. And now IntelliJ has added 4 new methods to our class, setModel, setColor, setDoors, and this time setConvertible. So just to show you how that would work, we'll go back to our main class again. I'm going to delete the 2 lines of code that are commented out and we'll add calls to these new setters. And now everywhere we set an attribute, we'll call the setter method instead. car.setModel, opening parentheses, double quotes, Curera, closing parentheses, semicolon. car.setDoors, opening parentheses, to, closing parentheses, semicolon. car.setConvertible, opening parentheses, true, closing parentheses, semicolon. car.setColor, opening parentheses, double quotes, black, closing parentheses, semicolon. And running that. Now we get the values we set on the car and not the defaults. So let's talk about the concept of why we'd want to use getters and setters. So while we're doing this setMake, what is the advantage of that? What that means, by using the .setMake, what we could do is, for example, we could go back to our car.java. We can have a look at this setMake method, our setter, and we could do some validation. Let's add some validation to this method. If opening parentheses make equals null, closing parentheses make equals double quotes unknown semicolon. String lowercase make equals make dot to lowercase opening and closing parentheses semicolon. Switch opening parentheses lowercase make closing parentheses opening curly brace. Case double quotes Holden comma double quotes Porsche comma double quotes Tesla return type this dot make equals make semicolon. Default return type opening curly brace. This dot make equals double quotes unsupported semicolon. Closing curly brace. Closing curly brace. So first in this code, we check if the argument being passed is null. If it is, we set the make to unknown. Next, we're using a method on string to test the argument being passed. So now this expression shouldn't be completely unfamiliar to you. We know that the make parameter is a string, or more correctly, it's an object of type string, and because of that, we have access to many methods on instances of string. One of these methods is this one, to lowercase, which returns a new string that's all lowercase. We'll use the switch statement on this variable and test if it's one of the 3 makes we support. These are Holden, Porsche, and Tesla. If the make matches one of those, we'll set the make field to the argument passed. But if it doesn't, we use the default case and set the make field to unsupported. So now we've built a rule that we're supporting only 3 manufacturers. And we'll enforce that rule so that if anything else is passed, we set make to unsupported. But if the argument is null, we set it to unknown. So let's test this. Go back to main.java, we'll change the make from Porsche to Maserati. car.setMake, opening parentheses, double quotes, Maserati, closing parentheses, semicolon. And running that. We see that make becomes unsupported and not Maserati. So you can see how it's very useful to have this type of functionality, the validation. So what you can do with the setter methods is you can set up all the rules related to that class, what is valid and what is not valid. You can have all that functionality set up within the car class itself so that these rules are in place as we're creating the object. What that means is the code that's creating objects can't make invalid objects, so to speak. In other words, it can't assign a make that we haven't defined as being valid in our car class. So that's the reason, and that's really the whole concept of encapsulation, is that we're not allowing people to access the field directly. We force them to go through a controlled way of setting up the data on the object. Using a setter method, we can really make sure that the data in our objects is valid data. Let's revert that last line for the setMake method from passing Maserati back to passing Porsche. So we've covered setter and getter methods and why you might want to use them. Now, let's just talk a little bit about declaring variables using classes. I want to show you what happens if we don't do this first line here, car equals new car. If I comment that second bit out there, equals new car, so we've just got a variable. So comment that out and just define the variable. We haven't initialized it. We haven't included the equals new car part. Already, IntelliJ is saying variable car may not have been initialized on line 6 when we are attempting to call the setter method on the car variable. You can't use an uninitialized variable which carries because we haven't assigned any object reference to it. But now, consider what happens if we instead assign null to car. So IntelliJ is not showing any errors when we do this, but let's try running it. We actually get an exception, null pointer exception, and the additional information that we can't call a method or invoke a method, an instance method, on a null instance. And what that essentially means is we've defined a variable called car, but it doesn't have a reference to a valid instance of a car. So we can't run a method on null, and we couldn't set or get attributes on null. So there's a distinction here I want to point out between an uninitialized variable and a variable with a null reference. An uninitialized variable, as we saw in the first instance, causes a compile time error. But a variable with a null reference can be used in code without compiler errors, but will throw an exception at runtime. So in both of these scenarios, we haven't created an object from the car template, which of course is the class. So that's why you need to make sure that new is always executed. The bottom line I'm trying to say here is that make sure when you're creating objects, you always use the keyword new and then include the name of the class and then follow it with the parentheses. You need to initialize it with the new keyword as we did earlier. So let's revert that code back so that we're assigning new car to the car variable. So you can see how this concept of a user-defined data type is coming back because we've introduced really a super data type of type car that has 5 fields: make, model, color, doors, and convertible. But we've also assigned some methods to it as well. So both the state and the behavior are part of the class. This is very powerful, as you can see. So before we end this video, let's create a second instance of car or another car object. Car targa equals new car opening and closing parentheses semicolon. And now let's copy and paste the code we used to set attributes on the car object and edit that code to set some of the attributes on targa. We'll change the model to be targa and the color to be red and set convertible to false, but leave everything else. And we'll print that out using the describeCar method on the car class. Targa.describeCar opening and closing parentheses semicolon. And if we run that, we can see we have different attributes or state on that second car object, which we called targa. But you have to admit this code is ugly. There's a lot of duplication of code, and it's somewhat painful to set data one attribute at a time on each car object we create. And we've only got 5 fields set up on it, so imagine if you had many more. We'll be looking at a better way to set data on an object, but in the next video, we'll give you a challenge so you can put into practice some of what we've covered, the basics of class and objects. Then after that, we'll talk about another way to set data on an object, and this will occur when we create the object. When we use the new keyword, we've said that creates the object and is called instantiation. But another term you'll hear for this process is constructing the object. But first, the challenge, so we'll see you in that next video, and after that we'll talk about this construction phase.
It's break time. Do you like this video? Don't forget to subscribe to get new videos. Share this video to open new premium videos and ebooks. We'll be a star freelancer.
So in the previous videos, we've been talking about classes. So it's challenge time. I want to challenge your understanding of the previous videos. So here's what I want you to do. Create a new class for a bank account. Create fields for account characteristics like account number, account balance, customer name, email, and phone number. Create getters and setters for each field. Create 2 additional methods, one for depositing funds into the account and one for withdrawing funds from the account. A customer should not be allowed to withdraw funds if that withdrawal takes their balance negative. Create a new project called Classes Challenge with the usual main class with the usual main method. You'll create an instance of an account class and then test your withdraw and deposit methods. You'll print information to the console that confirms what the balance is after the methods are called. So, the challenge here is to create the bank account blueprint that has 5 instance fields. You want to make this class encapsulated, so you'll make all your attributes private and set up getter and setter methods for your attributes. In addition, you'll have 2 behavioral methods for depositing funds and withdrawing funds. In addition to this class, you'll set up a main class with a main method that creates at least 1 instance of the bank account class and simulates depositing and withdrawing money from the account. And you may also want to add some system.out.println statements to the 2 methods above as well to confirm how much was deposited or withdrawn. So pause the video and try that out, and when you're ready to see my solution, come back and we'll go through it. How did you get on? Did you figure it out? Let me show you my solution. So I've created a new project called Classes Challenge with our usual main class and main method. So what we're going to do is create firstly a new class. I'll show the project panel, right-click on the SRC folder and select New. And we'll call this Java class account. Now we'll add our fields. We've said we want 5 of them and we'll make them all private. Private string number semicolon. Private double balance semicolon. Private string customer name semicolon. Private string custom email semicolon. Private string customer phone semicolon. You may have made the account number numeric, maybe an integer or long, but we've made it a string here. Either way is fine for this exercise. But for balance, we want that to be a real number to support both dollars and cents, so here we've used a double. Okay, next we want to create getters and setters. In the previous videos, we used IntelliJ's code generation tools to first create getters, then later we generated setters. But you can also generate both getters and setters all at once. We need to make sure our cursor is within the class's code block and position where we want the getters and setters to be inserted. I'm going to set my cursor at line 9, inserting an extra line before line 9. So we'll go into the code menu and click on Generate, where you can see on my computer an Alt+ insert does the same thing. So click on Generate, and you can click on either getter or setter as we did before, but this time we really want the option that says getter and setter. Next, we need to select which fields we want getters and setters for. We can select one or more, and you can see the F indicates that these are fields, and the lock means the field is private. Let's select all 5 of our fields and hit OK. So that's a pretty cool way to very quickly get getters and setters created. So make sure you check that out. We'll be referring to that for other types of code generation later. So that's all our getters and setters created. Next, we need to create 2 methods, a deposit and a withdrawal method. So let's start out with the deposit method. It's going to be a void method and we'll call it deposit funds. I prefer to insert functional methods before the getter and setter methods, so I'll insert the code for this method, starting on line 9 again. Public, void, deposit funds, opening parentheses, double, deposit amount, closing parentheses, opening curly brace. Balance plus equals deposit amount semicolon. System.out.println, opening parentheses, double quotes, deposit of dollar plus deposit amount plus double quotes made. New balance is dollar plus balance, closing parentheses, semicolon, closing curly brace. So this code takes the value in deposit amount and adds it to the current balance on the account using the compound plus assignment operator. You can see here that we're not using the keyword with this .balance, but simply using balance with no other qualifier. We could have included this qualifier with the dot notation to reference the field balance in both instances. So I'll add it to the one in the print statement, but it's unnecessary here because we aren't passing a parameter named balance and we haven't declared any local variables named balance. So the use of this keyword and dot notation is optional. Opinions differ on whether including it improves readability, but whichever way you decide to go, you should try to be consistent. In this class, if we don't need to use it outside of a setter, then we'll just omit it. Now let's add the withdrawal method on line 16. Again, the return type is void, and here let's call it withdraw funds with a parameter that is the withdrawal amount, the amount that should be withdrawn from the account. Public, void, withdraw funds, opening parentheses, double, withdrawal amount, closing parentheses, opening curly brace. If opening parentheses, balance, minus, withdrawal amount, less than 0, closing parentheses, opening curly brace. System.out.println, opening parentheses, double quotes, insufficient funds. You only have dollar, plus, balance, plus. Double quotes, in your account, closing parentheses, semicolon. Closing curly brace, else, opening curly brace. Balance, minus equals, withdrawal amount, semicolon. System.out.println, opening parentheses, double quotes, withdrawal of dollar, plus, withdrawal amount, plus. Double quotes, processed, comma, remaining balance equals dollar, plus, balance, closing parentheses, semicolon. Closing curly brace. Closing curly brace. So we first check if subtracting the withdrawal amount is going to take the balance negative. If it is, we won't allow it and we'll print a message to that effect. Otherwise, we use the minus compound operator, subtracting the value in withdrawal amount from the balance and printing a message with the updated balance. Okay, so that's our functionality for our account class. So let's test if it works. We'll go back to the main class and we'll create a new account, assigning it a variable we'll call Bob's account. Account, Bob's account equals new account, opening and closing parentheses, semicolon. Bob's account dot withdraw funds, opening parentheses, 100.0, closing parentheses, semicolon. Let's try running that and see what happens. And sure enough, we get insufficient funds. You only have $0 in your account. So that's good. It's doing what it should be doing. It's not allowing us to withdraw more funds than we actually have. And remember, when we created this account, we didn't actually set the balance to anything, so we were assigned Java's default value, or 0. So let's put some money in there and test withdrawing some funds. Bob's account.deposit funds, opening parentheses, 250, closing parentheses, semicolon. Bob's account.withdraw funds, opening parentheses, 50, closing parentheses, semicolon. Let's try running that. And you can see that we've done a deposit, adding $250 to the account, which left us with a balance of $250. Then we withdrew $50, and you can see that was okay, and we now have $200 left. So let's see if we can withdraw every dollar and cent from the account. Bob's account.withdraw funds, opening parentheses, 200, closing parentheses, semicolon. And running that. We get the last line that says we were successful at taking all of the money out. Let's try one more test using a few cents in there. Bob's account.deposit funds, opening parentheses, 100, closing parentheses, semicolon. Bob's account.withdraw funds, opening parentheses, 45.55, closing parentheses, semicolon. Bob's account.withdraw funds, opening parentheses, 54.46, closing parentheses, semicolon. And running this code. We're able to withdraw the first amount, $45.55 from the account. But the last attempt to withdraw the funds shows that there isn't enough money in there. We tried to withdraw $54.46, but we're a penny over, and therefore the withdrawal doesn't happen. If we add one more withdrawal, this time in the exact amount. Bob's account.withdraw funds, opening parentheses, 54.45, closing parentheses, semicolon. And running that. We see that the last withdrawal worked, letting us again withdraw the exact amount in the account. So that's it. That's the challenge. Hopefully you got something along those lines. And you've now really created your own class for the first time, which is fantastic. Now, of course, we didn't actually set any other values there. So let's do that. bobsaccount.setNumber, opening parentheses, double quotes, 12,345, closing parentheses, semicolon. bobsaccount.setBalance, opening parentheses, 1,000.00, closing parentheses, semicolon. bobsaccount.setCustomerName, opening parentheses, double quotes, Bob Brown, closing parentheses, semicolon. bobsaccount.setCustomerEmail, opening parentheses, double quotes, myemail@bob.com, closing parentheses, semicolon. bobsaccount.setCustomerPhone, opening parentheses, double quotes, opening parentheses, 087, closing parentheses, 1234567, closing parentheses, semicolon. So you can see there's lots of typing there if we wanted to set the field values for the first time. And I've mentioned if we had 10 or 20 or 30 fields, it would be really tedious to set the data in this way. There's another way of doing this when you're creating an object for the first time using a class, and that's using constructors. So we'll be talking about this in the next video. In the last video, we had you do a challenge, and we ended it by setting attributes on an instance of the account class, which we referred to as Bob's account. And we talked about how this is a little tedious to call the setter method for each field. Another option is to pass this data to something called a constructor. A constructor is used in the creation of an object that's an instance of a class. It is a special type of code block that has a specific name and parameters, much like a method. It has the same name as the class itself, and it doesn't return any values. You never include a return type from a constructor, not even void. You can, and should, specify an appropriate access modifier to control who should be able to create new instances of the class. So what you can do with a constructor is you can essentially do all the statements we've done here to set the initial parameters or the initial values of the fields. And you can include any other initialization code you want to perform in the constructor. So let's see whether we can replace all this code. First, we'll edit our account.java class and add a constructor. Well, firstly, it turns out that a constructor is actually created for you implicitly by Java. When we say things are implicit in Java, we mean you can't see the code in the source, but it's in the bytecode generated during the compilation process. So when you actually type new and the name of the class and then parentheses, this is actually calling the constructor. We didn't explicitly create a constructor in the account class, so Java created one for us. This is called the default constructor. If a class contains no constructor declarations, then a default constructor is implicitly declared. This constructor has no parameters and is often called the no arguments constructor. If a class contains any other constructor declarations, then a default constructor is not implicitly declared. There are the rules for the default constructor, which we'll talk about as we get more familiar with more advanced topics. For now, it's important to just understand that a constructor exists, whether you explicitly declare one or not. This is why creating an object with a new keyword and passing no arguments in the parentheses is supported in nearly all cases. So this code is actually calling that special method that creates the class. So its purpose is to physically create the object from the class for us. So let's create our own constructor in the account class next. Public account, opening and closing parentheses, opening curly brace. System.out.println, opening parentheses, double quotes, empty constructor called, closing parentheses, semicolon, closing curly brace. So again, the rules for a constructor are 1. That its name has to be the same as the class, and 2. That it has no return type, not even void. And we also use an access modifier. Here we use public. We'll talk about when you want to use other access modifiers later in this section and the next. So we've done nothing else here, we've just added this constructor. This is normally created for you automatically, but here we've physically typed it in and added the system.out.println statement. So what will happen is when we go to compile this, Java will look at that and go, okay, you're creating your own constructor, I won't try and override it. So if we run this now, what we should see at the top, before any other output, is the message we put in the constructor, empty constructor called. So when we type new account with parentheses and no parameters, that actually was Java's cue to call the constructor that we just added. This is an explicit constructor without any parameters or arguments, and we've added functionality, which is just printing that statement. So the purpose of the constructor is to essentially initialize the object that we're creating and do whatever else we need to happen while the object is being instantiated. So it's only ever called once at the start when we're creating the object. A class can have one or many constructors, one of which can be a no-args constructor. So now we'll add another constructor, and this time we'll declare some parameters. Doing this will let us pass values to the constructor. We can then use these values to assign data to our fields instead of calling a whole bunch of setters. Okay, so just below the first no-args constructor, let's add a second one. This time, it will have 5 parameters, one for each of the fields on the account class. We'll include a system.out.println statement in this one too. Public, account, opening parentheses, string, number, comma, double, balance, comma, string, customer name, comma, string, email, comma. String, phone, closing parentheses, opening curly brace. System.out.println, opening parentheses, double quotes, account constructor with parameters called, closing parentheses, semicolon. This dot number equals number, semicolon. This dot balance equals balance, semicolon. This dot customer name equals customer name, semicolon. Customer email equals email, semicolon. Customer phone equals phone, semicolon. Closing curly brace. Okay, so I just want to point out a few things with this constructor. First, we're passing 2 parameters, email and phone, where the parameter name doesn't match the field name. It's common practice to make the parameter names the same as the field names, but it's not required. If you do make them the same, using the this and dot notation is required, just like it was in the setter methods. So here you can see we're setting this dot number equals number. This means we're assigning the number attribute on the instance that's being created, known as this, to the argument value passed in the number parameter. But we don't need this with the dot notation for customer email or customer phone because these field names are different than the parameter names. So if we go back to main.java, we can now change the way we instantiate Bob's account, passing all the values to the call to the new keyword. I'm also going to comment out all the setter methods to show they're not needed anymore. They're being replaced with a single statement. Account, Bob's account equals new account, opening parentheses, double quotes, 12345, comma, 1000.00, comma. Double quotes, Bob Brown, comma, double quotes, myemail@bob.com, comma. Double quotes, opening parentheses, 087, closing parentheses, 1234567, closing parentheses, semicolon. And running this, we can confirm that we executed the new constructor. You can see the first statement, account constructor with parameters called. You can also tell we're starting with a balance of $1,000, which is the amount we passed to the constructor. Let's change that amount in the constructor, then print out some information before we execute any withdraw or deposit statements. System.out.println, opening parentheses, Bob's account.getNumber, opening and closing parentheses, semicolon. System.out.println, opening parentheses, Bob's account.getBalance, opening and closing parentheses, semicolon. And running that. We see the account number printed as well as the initial deposit amount, which we changed to $500. So having multiple constructors as we've done here is called constructor overloading. It looks a lot like method overloading, doesn't it? Constructor overloading is declaring multiple constructors with different formal parameters. The number of parameters can be different between constructors. Or if the number of parameters is the same between 2 constructors, their types or order of the types must differ. Let's end the video here. In the next video, we're going to continue looking at constructor overloading, and we'll talk about when and where you can call these overloaded constructors. So let's move on to that video. In the last video, we talked about constructors, including the default constructor, which can be explicitly declared, and the rules for when it is implicitly declared by Java. We talked about declaring constructors with parameters and passing arguments to the new keyword to set fields on the object being created. We talked about constructor overloading, which is similar to method overloading, where you can declare multiple constructors with different parameters. So in this video, we'll start with the concept of constructor chaining, which is the process of calling one overloaded constructor from another. Constructor chaining is when one constructor explicitly calls another overloaded constructor. You can call a constructor only from another constructor. You must use the special statement this to execute another constructor, passing it arguments if required. And this must be the first executable statement if it's used from another constructor. So we looked at constructor overloading already. Let's go back to the code we were looking at in the last video in the Classes Challenge project. Let's look at another example, and this time we'll use constructor chaining, which we've said is calling one constructor from another constructor. That may sound a little bit confusing, but we'll cover some reasons why you would want to do this next. First, we use the default constructor to instantiate an object and pass it some default values. In other words, from the constructor with no parameters, we'll call the one with 5 parameters and pass in literal values. So to do that, we type this followed by parentheses. Which constructor is called is determined by the values we pass. So we'll add a call to this in the noargs constructor, and we'll just pass some literals as arguments. The type and number of arguments we pass must match one of our constructors. Since we only have one other constructor declared, and it only has 5 parameters, we'll pass 5 arguments. But the types must match the order of the types that were declared in the constructor. So all of our parameters in the second constructor are strings, except the second parameter, which we called balance, and that's a double. This opening parentheses, double quotes, 56789, comma, 2.50, comma, double quotes, default name, comma. Double quotes, default address, comma, double quotes, default phone, closing parentheses, semicolon. So what we're doing then with this is a special use of this, which you won't see used anywhere else. This is calling another constructor within a constructor. So what we're saying here is, look, if you try and create an object from this class and you don't give me any parameters, set this new object up with these values by calling this other constructor. Constructor chaining is optional, meaning it's not something you have to do, but there can be situations where you want to do this. Now, one other thing to keep in mind is using this to call another constructor is that you have to be sure that it's the very first line that's executed. In other words, we couldn't have system.out.println as the first line in the constructor. Now, we have a compiler error. Call to this must be the first statement in constructor body. So the rules are pretty strict, using that this statement with parameters can only be called in a constructor, and it has to be the very first line that's called. Let's revert that change so it compiles. And we'll go back to our main class, and we'll change the code to just call the empty constructor. I'll comment out the one with 5 parameters and add the noargs call. Account, Bob's account, equals new account, opening and closing parentheses, semicolon. And running that, you can see that we get the system.out.println statement from both constructors. So they're actually both called, as you can see there. The reason why you see it in that order makes sense if you think about it. If you come back here to the account.java, you see the very first line of the no arguments account constructor called the other constructor with 5 arguments. So the statement in the 5 argument constructor was printed first. The fields were set to the values passed, and then the code returned to the noargs constructor. It then executed the line following the call to this, which printed out empty constructor called. So as you can see, 56,789 and 2.5 were actually passed, and these are printed out. So it's obviously working. The default constructor is making a call to the 5 argument constructor, which sets the fields to the values we specified. Let's look again at this constructor with many parameters. You may have noticed, looking at this code, is that we've actually updated the fields directly. We didn't call the setter methods from the constructors. So there's an alternative. What we could have done is we actually could have done something like set number, number. Set number, opening parentheses, number, closing parentheses, semicolon. If we had some validation in that setter that was testing for valid numbers and those types of things, we could actually execute that code as well. Now in Java, there are conflicting opinions as to which is the best approach. Because you'll find out in following videos, when we start talking about inheritance and creating subclasses, these calls to setter methods might not work. So the general rule of thumb is, it's always better to assign the values directly to the field rather than calling the setter in a constructor. Because as you'll see in the next video, there can be scenarios where this code that's in this setter isn't executed. So by going back and actually coding it directly, in other words, going back and setting it to this and whatever the field name is, you're guaranteed that the field values will be initialized. So my general rule of thumb is, with constructors, don't call setters or any other method other than another constructor within those constructors. And the other reason for that is, this is the point in the code where the object is being created. So consequently, some aspects of the initialization may not have been finished while you're in the constructor. And that's the other reason that there's an opinion out there that suggests that you shouldn't be calling other methods or even the setters within the constructor code. But we can talk more about that later if needed. For now, go with what I've suggested, which is just saving the field values directly rather than calling setters or any other method. Now the other thing I want to show you is another shortcut that IntelliJ's got. Let's just assume that we wanted to create another constructor, and for this one, we only want to pass the customer name, email address, and phone number. So we could do that by creating another constructor by cutting and pasting and editing an existing constructor. But IntelliJ gives us yet another code generation tool, this one for constructors. So let's position our cursor after the second constructor on line 25 after a couple of additional empty lines. Next, we'll click on Code on the menu and select Generate as the menu option. Then we'll select the first option, which is Constructor, and it asks which field do you want to include in the constructor. So which ones are we going to have passed to us? In other words, which fields do we want the constructor to set? Let's pick the three we talked about: customer name, email address, and the phone number. When we hit OK, we get a new constructor generated for us, setting the instance fields to the parameters passed. So there's our third constructor. And you can see it's only setting 3 of the 5 instance fields. So that's one way of doing it, but of course, the disadvantage here is that our account number and our balance aren't included. But we could call the 5-argument constructor and pass a couple of default values, so let's do that. We'll also comment out the initialization code because we'll be initializing them in the constructor with 5 parameters. This, opening parentheses, double quotes, 99999, comma, 100.55, comma, customer name, comma, customer email, comma, customer phone, closing parentheses, semicolon. So you can see what we've done there is we've defaulted 2 parameters, the account number to be 99999 and the default balance to $100.55. So we've come up with what the default is because they weren't specified. And we've still gone back and called our major constructor. This is the one that actually updates all the fields. So you'll find as you start creating and writing more complex code, it's not unusual to see multiple constructors like this. And in that situation, often you do all your initialization in the one constructor, like you can see here. All other constructors can call that major constructor, passing default values or null references as arguments. That's a good way of doing things, and it often leads to really good coding because you're not having to duplicate code or duplicating initialization in more than one place. So how do we call this new constructor when creating an account? We would call that very much the same as we've been doing before. Let's create a new object here using this 3-argument constructor. So going back to the main class and main.java and adding our code just before the last bracket of the main method block. Account, Tim's account, equals new account, opening parentheses, double quotes, Tim, comma. Double quotes, tim@email.com, comma, double quotes, 12,345, closing parentheses, semicolon. System.out.println, opening parentheses, double quotes, account no, colon, plus, Tim's account.getNumber, opening and closing parentheses, plus. Double quotes, semicolon, name, plus, Tim's account.getCustomer name, opening and closing parentheses, closing parentheses, semicolon. Let's just run that to make sure that it's working. And you can see the last line in the output is from our new account, Tim's account. 99999 was the default account number that we used in the 3-argument constructor in the account class, as you can see. And the name was Tim, which of course was what we passed here. So that's constructors. You'll see those used extensively in Java. And of course, we'll be using them a lot in this course as we move forward because they're a very important part of creating objects from classes. Okay, so it's time for a challenge on constructors in the next video to test what you've learnt, so I'll see you there. In this video, I'm going to give you a challenge to review what you learned about constructors so far. So for this challenge, you want to create a new class called customer with 3 fields, name, credit limit, and email address. Create the getter methods only for each field. You don't need to create the setters. Create 3 constructors for this class. First, create a constructor for all 3 fields which should assign the arguments directly to the instance fields. Second, create a no-ask constructor that calls another constructor, passing some literal values for each argument. And lastly, create a constructor with just the name and email parameters, which also calls another constructor. Okay, so that's your challenge. And of course, then test and confirm it works by writing code in the usual main class and main method. So pause the video now, go away and give that a go. And when you're ready to see what my solution is, come back and we'll take it from there. Okay, how did you get on? Did you figure it out? So now let's get started. So I've already created a project called Constructor Challenge with the usual main class and the main method, which I'm showing here. I'll show the project panel here on the left, and then I'll right-click on the SRC folder because I want to select New from the menu options, then Java class. And we want to call this new class Customer. And next, we'll add the 3 fields, making them all private, which supports encapsulation of our data. Private string, name, semicolon. Private double, credit limit, semicolon. Private string, email, semicolon. Okay, so we have our fields, but we can't access them. And you'll remember the way to do that is the best practice way is to use getters. So let's add those next. For this, we can use IntelliJ's code generation features, which I've shown you before. So let's position the cursor on line 7 and we'll select code and then generate. And then we can select getter and select all 3 of our fields. And now IntelliJ adds all 3 of our getters to the code, get name, get credit limit, and get email, as you can see. Okay, so far so good. Next, we need to create the constructors, starting with a constructor that takes all 3 parameters, 1 for each of our fields. Let's use IntelliJ's code generation again for this first one. With our cursor set again on line 7, we use the code menu, then generate. Then we select constructor and again select all 3 of our fields. And clicking OK, IntelliJ inserts the constructor, as you can see, public customer with 3 parameters. And by default, IntelliJ has set this up to use this keyword and the dot notation here in the generated constructor. You'll remember we need to use this special qualifier when our parameter names are the same as our field names, which is how IntelliJ generates this code. So now that we have a constructor, let's test it out. First, we need to write some test code in the main.java class. Customer equals new customer, opening parentheses, double quotes, Tim, comma, 1000, comma. Double quotes, tim@email.com, closing parentheses, semicolon. System.out.println, opening parentheses, customer.getName, opening and closing parentheses, semicolon. System.out.println, opening parentheses, customer.getCreditLimit, opening and closing parentheses, semicolon. System.out.println, opening parentheses, customer.getEmail, opening and closing parentheses, semicolon. So we created a new object of type customer and at the same time passed data to the constructor, the name, the credit limit, and the email. And then we print out all three fields using the getters. And running that, we get the values back that we passed to the constructor. The values were Tim, 1000, and the email, tim@email.com. So we've confirmed the three-parameter constructor is working. Let's just see what happens if we try to create a customer using the default constructor. Customer, second customer, equals new customer, opening and closing parentheses, semicolon. And you can see this code doesn't compile. I wanted to show this to you for a reason. That is to remind you that the default constructor, the no arguments or empty constructor, as it's sometimes called, won't get implicitly created. It won't get implicitly created if we create any other kind of constructor in our class. So we can't use it this way to create a new customer object until we create that constructor manually now. Let's just comment that line of code out for the moment. Okay, so let's add the next two constructors. Going back to the customer class, I'm going to again use the IntelliJ generator to create a constructor. And again, I'll set my cursor on line 7 where I want the constructor to be inserted. So now select code and then generate. Next, we select constructor, and from the list of fields, we just want to pick name and email. And now we have this next constructor generated for us. So this constructor, I wanted you to see that IntelliJ doesn't use constructor chaining. It will generate the code, setting the attributes this way for each parameter. But that's not what the challenge asked us to do. The challenge said we should call another constructor. It didn't really tell us which one, but here we'll change the code to call the three-parameter constructor. So I'm going to delete these two lines of code on line 8 and line 9. And now we want to call another constructor. Hopefully you remember there's only one way to do this, and that's with the call to this statement. This opening parentheses, name, comma, 1000, comma, email, closing parentheses, semicolon. So we're passing along the parameters, name and email, and those values, but we're hard coding the credit limit to 1000 here, making 1000 the default. In other words, 1000 is the default value for customer objects that are created and don't specify an amount. And before we test this, we'll first add the final constructor, the noargs constructor. Again, at line 7, I'm going to insert this new constructor. I personally like to organize my constructors from the least amount of parameters to the most, but this is a matter of personal style and not a rule. Public customer, opening and closing parentheses, opening curly brace. This opening parentheses, double quotes, nobody, comma, double quotes, nobody at nowhere.com, closing parentheses, semicolon, closing curly brace. Okay, so what's with this one? Why are we only passing two parameters in this one? Well, this one is calling the constructor that takes two parameters and sets the default credit limit to 1000. So we're chaining two constructors really. We could have simply called the three-parameter constructor, like so. But if for some reason the default credit limit changed, we'd need to change it in two places. So I'm going to revert that back. Okay, so let's test these constructors out. Going back to main.java, we'll first uncomment out that line we added previously. And we can see that compiles now. We'll also add some print statements for the second customer variable. I'm just going to copy and paste lines 6 to 8 and change customer to second customer. And running the code. You can see the no arguments constructor was executed. So I passed the values nobody and nobody at nowhere.com to the two-parameter constructor. That constructor then passed those values and the 1000 credit limit as the default value to the three parameters constructor. So this is constructor chaining. And just for good measure, let's add a third customer that uses our two-parameter constructor directly. So we'll add a third customer variable to the code and then copy and paste the println statements as we did previously. Customer, third customer, equals new customer, opening parentheses, double quotes, Joe, comma, double quotes, joe@email.com, closing parentheses, semicolon. And running that now prints out Joe's information, but also with a 1,000 credit limit. So we've used all three of our constructors in this code. In addition, two of our constructors in turn leverage code in other constructors by chaining them using the special this call to do it. Okay, so that was the challenge. Hopefully you got a lot out of that. In the next couple of videos, we're going to review some terminology topics to hopefully answer any questions you might have about a class, an object, an instance, and a reference. And we'll look more at static and instance fields and methods. So I'll see you in the next video. In this video, we're going to go over and talk about and hopefully clear up any confusion about references versus objects versus instances versus classes. By now, you've probably noticed that we use the words reference, object, instance, and class quite a lot when talking about Java code. These new concepts may well be confusing at first. So in this video, I'm going to try and go through the process and show you exactly what each of these words means in the context of Java programming. You might remember in an earlier section of the course, we showed you this slide. We said that object and instance are interchangeable and that we create an instance or object using a class. These new concepts may well be confusing at first, so let's talk about them. Let's use the analogy of building a house to understand classes. Now, a class is basically a blueprint for the house. Using the blueprint, we can build as many houses as we like based on those plans. So thinking back to the physical world, we use the plans for the house to build many houses that have the same floor plan. Each house we build, in other words, going back to programming terms, each house we instantiate using the new operator is an object. This object can also be known as an instance. Often we'll say it's an instance of the class. So we would have an instance of house in this example. Getting back to the physical world, each house we build has an address. It's built at a physical location. In other words, if we want to tell someone where we live, we give them our address, perhaps written on a piece of paper. So that piece of paper with the address on it, this is known as a reference. Now we can copy that reference as many times as we like, but there is still just one house that we're referring to. In other words, we're copying the paper that has the address on it, not the house itself. Or we're writing that address on another piece of paper. Now back to programming terms. We can pass references as parameters to constructors and methods. Let's now just go a bit deeper to make this a little bit more clearer. Alright, so we've got some code on the screen now. Now on the left-hand side, we've got the class house with an instance variable, also known as a field called color. Now on the right-hand side, we have the main class with the main method. Now this code in the main method is creating instances of the house class, changing the color, and printing out the result. So let's actually go through line by line and see what happens when this code is executed. Alright, so looking at this first line that I've got highlighted in red on the right-hand side. The house blue house equals new house blue in parentheses and double quotes. This code creates a new instance of the house class. So remember, house is a blueprint and we're assigning it to the blue house variable. So in other words, it's a reference to the object in memory. And you can see that hopefully on the left-hand side, and then it makes a bit more sense there. Blue house is the variable. We're creating a new instance of the house class and assigning it the color blue. Alright, so this next line that I've got highlighted, house another house equals blue house. Well, that creates another reference to the same object in memory. So what we've got now is two references pointing to the same object in memory. So there is still one house, but two references to that one object. So in other words, we've got two pieces of paper with the physical address of where the house is built written down if we came back to a real-world example to make that clearer. So next on the right-hand side, I've got two println statements highlighted. So they print the value of the color variable for blue house and also another house. Now in this scenario, both will actually print blue, and that's because again, we've got two references to the same object. And again, you can see that on the left-hand side there. Hopefully that image showing both references to the same house, which is blue, makes that clearer as to how this is actually working. Alright, so this next line I've highlighted here, another house.setColor yellow, well that's calling the method setColor and setting the color to yellow. Now to the left, you can see that both blue house and another house now have the same color. So why is that? Well, remember that we've got two references that point to the same object in memory. Now once we change the color of one, both references still point to the same object. So consequently, they've both got the same value of yellow in this example. Now in a real-world example, there's still just one physical house at that one address, even though we've written the same address on two pieces of paper. So if we went ahead and painted the house yellow, then obviously both references to the physical house still point to a house that is now yellow. Alright, so we've got a couple more println statements here, which I've highlighted. So these two println statements are printing the same color. Both are printing yellow because, again, we've got two references that point to the same object in memory. And again, you can see that defined with the arrow on the left-hand side of the image, one instance pointed to by two objects. Okay, so moving on. What we're doing now is, with that next line that's highlighted on this slide, house greenhouse equals new house green. Well, we're creating another new instance of the house class, this time with the color set to green. So now we've got two objects in memory, but we've got three references. And those references are blue house, another house, and our new greenhouse. Now the variable or reference greenhouse points to a different object in memory, and that's the one we just instantiated using the new keyword here. But blue house and another house point to the same object in memory, the previous house we created at this point. Alright, so I've highlighted this statement, another house equals greenhouse. So what we're doing here is we're assigning greenhouse to another house. So in other words, we're really dereferencing another house. And it will now point to a different object in memory. Now previously, it was pointing to a house that had the yellow color, but now it's pointing to a house that's got the green color. So in this scenario, we still have three references and two objects in memory, but blue house points to one object, while another house and greenhouse now point to the same object, which has the color green in memory. And finally, we've got those last three print line statements. The first will print yellow since the blue house variable or reference points to the object in memory that has the yellow color. Or the next two lines will print green, and that's because another house and greenhouse point to the same object in memory. So keep in mind that in Java, you always have a reference to an object in memory. There's no way to access an object directly, everything is done using that reference. Finally, consider the code on this slide for a moment. On the first line, we create a new house and make it red. But we aren't assigning this to any variable. This compiles fine, and you can do this. This object is created in memory, but after that statement completes, our code has no way to access it. The object exists in memory, but we can't communicate with it after that statement is executed. That's because we didn't create a reference to it. On the second line, we do create a reference to the house object we created. Our reference, the variable we call myHouse, lets us access that beige house as long as our variable myHouse stays in scope or until it gets reassigned to reference a different object. On the third line, we're creating a red house again, but this is a different object altogether from the red house we created on line 1. This third statement is creating yet another house object in memory which has no relationship to the one we created on the first line. So this code has three instances of house, but only two references. That first object will stay in memory with no reference to it until Java's automatic process, appropriately called garbage collection, figures out there is no running code with a reference to that object and deletes it. In fact, that first object is said to be eligible for garbage collection immediately after that first statement. It's useless to the code because it's no longer accessible. There are times we might want to instantiate an object and immediately call a method on it and not assign the object to a variable reference, and we'll show you some reasons later on in the course. But 99% of the time, we'll want to reference the objects we create, so we'll immediately assign our new instance to a variable, creating a reference to communicate with it. Alright, so hopefully that now made it a little bit clearer. Let's move on to the next video. Let's discuss the differences now between static variables and instance variables. So firstly, a static variable is declared by using the keyword static. Static variables are also known as static member variables. Every instance of the class shares the same static variable. So if changes are made to that variable all other instances of that class will see the effect of that change. It is considered best practice to use the class name and not a reference variable to access a static variable. This makes it clearer that the variable is associated with the class and therefore shared, and the value is not stored with the instance. An instance isn't required to exist to access the value of a static variable. Static variables aren't used very often, but can sometimes be very useful. They can be used for storing counters, generating unique IDs, storing a constant value that doesn't change, like pi for example, creating and controlling access to a shared resource. Some examples of shared resources might include a log file, a database, or some other type of input or output stream. In this example, we've got a class called dog, and it's got a static variable called name. Now, there's a constructor that sets the static variable to the parameter value passed to the constructor. And we've got a method there called printName, which isn't static. So that's a pretty simple class, and inside main, we're creating two instances of the dog class with the line dogRex equals new dog Rex. We're creating an instance of the dog class, and then we're passing the string Rex as a parameter, and that'll be the name of the dog. In the next line, we've got a similar situation, just passing the parameter, which will be used as the name Fluffy. So then we call the printName method on both of the instances. So they're just regular instance methods because they aren't defined using static. So both method calls will print Fluffy. You might be wondering, why is that the case? Why would both methods here print Fluffy? Well, remember that static variables are shared between instances. So in other words, once we change the static variable, all instances will see that change we made. So when we called the constructor with parameter Fluffy, it modified the static variable name because both instances are sharing that variable. That's why it prints Fluffy twice. So you could also say that all dogs have the same name, but that's logically incorrect. So hopefully now you can see how static variables can be used inappropriately sometimes, as in this example. Probably you were assuming that the dog's name would be associated with each instance of the dog, and therefore would be different for each one. One dog would be named Fluffy, and the other would be Rex. So this is a scenario where using a static variable probably wouldn't be a good idea, and using a regular instance variable would make a lot more sense in this particular example. Alright, so let's move on now to instance variables. So firstly, they don't use the static keyword when you're defining them. They're also known as fields or member variables. Unlike a static variable, instance variables belong to a specific instance of a class. Each instance has its own copy of an instance variable. Every instance can have a different value. Instance variables represent the state of a specific instance of a class. Let's see an example using instance variables. So in this example, we've again got very similar code to what we looked at earlier in the video, but this time the variable name in the dog class isn't static. So it's just a regular instance variable. So once again, the constructor is setting the value from the parameter passed to that instance variable. But now the code will print Rex, and on the next line Fluffy, and that's because we're using instance variables. Each instance of the class has its own state or its own values for any variables that have been defined. So in other words, now every dog has got its own copy of the name field. We can also say that it's basically not shared like it was before in the earlier example, which was using a static variable. So in most cases, you'd probably want to use instance variables, but there will be scenarios when it can be useful to use a static variable like in the earlier examples. So that's instance and static variables. Let's move on now to the next video. Static versus instance methods. In the last video, we talked about the difference between static and instance variables. So now let's discuss the differences between static methods and instance methods. So firstly, static methods. Static methods are declared using a static modifier. Static methods can't access instance methods and instant variables directly. They are usually used for operations that don't require any data from an instance of the class from this, in other words. If you remember that this keyword is the current instance of a class. So inside a static method, we can't use this keyword. Whenever you see a method that doesn't use instance variables, that method should probably be declared as a static method. For example, Main is a static method and it's called by the Java virtual machine when it starts the Java application. In this example on screen, we've got a class called calculator with a static method called printSum, and it just prints the sum of two integer numbers. Then we've got the main class with two static methods, main and printHello. Now inside main, we're calling the method printSum from the calculator class. So as you can see, to call the printSum method, we just need to type the class name, in this case, calculator, and then the method name, printSum. Or in the second example, in the case of printHello, we can just type the method name with parentheses, which will automatically call the printHello static method because it's being invoked from a static method itself. So static methods don't require an instance to be created. We can just type the class name and use the dot notation with the method name to access them. Let's move on now to instance methods. Instance methods belong to an instance, a specific instance of a class. To use an instance method, we have to instantiate the class first, usually by using the new keyword. Instance methods can access instance methods and instance variables directly. Instance methods can also access static methods and static variables directly. What I mean by directly is that we don't usually have to use the keyword this with the dot notation to use them. And we don't have to use the class name with the dot notation to access static variables, though that can help with clarity. So in this example, we've got a class called dog with a method bark. So notice here how the method bark is not using the static keyword this time. So in other words, that method is just a standard instance method. Then we've got our main class with a method main. Now inside main, the main method, we first need to create an instance of the dog class, and that's done with the line dogrex equals new dog. As you can see, we're using the new keyword to create an instance of that class. After we've got the instance, we can call the instance method bark, in this case, by typing rex.bark. So the hard part here could be deciding when to create an instance or when to create a static method. So let's see some basic rules that should help you decide. So here we've got a small diagram that should help us decide whether we need an instance or a static method. Now instance methods are created more often than static methods, but let's see how to follow this diagram. So the first question we'd ask ourselves is, should the method be static? After that question, the next question would be, does it use any fields? Instance variables, in other words, or instance methods of this object. And remember, we're asking these questions about the proposed method we plan to write, so if that's true, in other words, it does use some fields and or instance methods, then we want to make it an instance method. In the other scenario, if the method doesn't use or is not proposed to use any instance variables or instance methods, in that case, then we'd probably consider writing it as a static method. So generally speaking, if we're not using any fields or instance methods with the new proposed method, we should consider making that method static instead of a regular instance method. So that's the main differences between static and instance methods. In the last couple of videos, we've reviewed some very important terms. Hopefully, now you have a clear understanding of what an instance, object and reference are, as well as the differences between static and instance members of a class. In the next video, we're going to talk about a class that usually only has fields to store data. This is called the plain old Java object, and then we'll introduce you to a fairly new type in Java, the record. See you in the next video. A plain old Java object, whose acronym is POJO, P-O-J-O, is a class that generally only has instance fields. It's used to house data and pass data between functional classes. It usually has few, if any, methods other than getters and setters. Many database frameworks use POJOs to read data from or to write data to databases, files or streams. You remember, I've said several times that a class can be thought of as a super data type. A POJO is really just that. It lets you extend and combine your definition of data types. A POJO also might be called a bean or a Java bean. Maybe you've heard the term Java bean. A Java bean is just a POJO with some extra rules applied to it. These rules are in place so that Java frameworks have a standard way to manipulate and manage these objects. A POJO is sometimes called an entity because it mirrors database entities. Another acronym is DTO for Data Transfer Object. It's a description of an object that can be modeled as just data. There are many generation tools that will turn a data model into generated POJOs or Java beans. You've seen an example of similar code generation in IntelliJ, which allowed us to generate getters, setters, and constructors in a uniform way based on our class's fields. Let's look at an example of a POJO in code. I've created a project called Record Project and created the usual main class with the main method. Now, let's say we want to read data out of a database that has a table of student records. So we can see from this that we need 4 fields: ID, name, date of birth, and class list. We're going to make all of these strings for this exercise. Later in the course, we'll make this a lot more interesting with dates, arrays, and custom types. So open the project panel and select the SRC folder. We'll create a new class and we'll call it student. We'll add the 4 fields we talked about as strings: private string ID semicolon, private string name semicolon, private string date of birth semicolon, private string class list semicolon. So now let's make this a plain old Java object. A POJO in its simplest form requires a way to populate data, and we can do this with a constructor. We'll use IntelliJ's code generation tool to create a constructor first with all of these fields. Place the cursor on line 8, then select Code from menu. Select Generate Next and select Constructor and select all the fields, then press OK. So this class, even without getters and setters, lets us create and populate new student objects using just this constructor. And let's really do that now in the main method of the main class. Let's have some fun with this exercise and put some of the Java skills we've learned to date to work. We'll create 5 students in a loop. We'll use the loop variable to create a unique ID. At first, we'll hardcode the name as Mary, as well as set date of birth and class list to some literal values. For, opening parentheses, int I equals 1, semicolon, I less than or equal to 5, semicolon, I plus plus, closing parentheses, opening curly brace. Student s equals new student, opening parentheses, double quotes, s92300 plus I, comma. Double quotes, Mary, comma. Double quotes, the 5th of November 1985, comma. Double quotes, Java Masterclass, closing parentheses, semicolon. Closing curly brace. Okay, so here we create 5 student objects. We pass an ID that starts with S92300, then appends the loop index I, so each student has a different ID and the rest of the values are literals. Let's now replace Mary. We're going to put a switch expression that'll give us a different name based on the value of the loop index I. Switch, opening parentheses, I, closing parentheses, opening curly brace. Case 1, return type, double quotes, Mary, semicolon. Case 2, return type, double quotes, Carol, semicolon. Case 3, return type, double quotes, Tim, semicolon. Case 4, return type, double quotes, Harry, semicolon. Case 5, return type, double quotes, Lisa, semicolon. Default, return type, double quotes, anonymous, semicolon. Closing curly brace, comma. So we're using a switch expression as a parameter to a constructor, which is pretty neat, you have to admit. Maybe you notice that I have a default case label defined, although in this loop it won't ever be true. This is actually a requirement for the switch expression when it's used with a numeric switch value. It requires that all possible values be resolved, and with a numeric switch value, the only way to really do this is to use a default label like we did here. The last 2 parameters are simply hard-coded to the same birth date and the class name Java Masterclass. So we can run this, but since there's no output, it's not terribly interesting. I want to show you another generation option on IntelliJ, this one to print out data. When we get to inheritance, I'll explain how this method actually works, but for now, let's just use it because it really makes life a lot easier. So back to our student Pojo, put your cursor before the last closing brace of the class. We'll pick code and generate, and now look for the option that says to string and select that. Select all fields, then press OK. And now you see we have the code on lines 16 to 23, the method called toString, which will print out all the attributes in our class in a nicely formatted way. So the toString method is a special method in Java. We can implement this method in any class we create, and doing this lets us print out the current state of our object. IntelliJ, when it generates this code, adds a special statement, as you can see here, at override displayed above the method. Anytime you see a statement like this, which starts with an @ symbol, this is called an annotation. Annotations are a type of metadata, and metadata is a way of formally describing additional information about our code. Annotations are more structured and have more meaning than comments. This is because they can be used by the compiler or other types of preprocessing functions to get information about the code. And don't worry, we'll be covering annotations in a later section of the course, as well as introducing you to the most commonly used. Now, metadata doesn't affect how the code runs, so this code will still run with or without the annotation. And this particular annotation we see in our code, an override, is one of the most common annotations in Java that you'll use. It tells the compiler that this is a special type of method in Java, an overridden method. We talked about overloaded methods quite a bit. An overridden method is not the same thing as an overloaded method. An overridden method is a special method in Java that other classes can implement if they use a specified method signature. So it's similar to how we create the main method, with its special signature, we have to create the toString method a certain way. When we do that, we have access to special Java processing, which I'll show you next. Popping back over to the main class and main method, we can simply print out each one of our student objects using the system.out.println statement. System.out.println, opening parentheses, s, closing parentheses, semicolon. You might notice that we didn't actually even call the toString method on the student, the s variable in this loop, in the system.out.println statement. We didn't have to. This is another built-in feature from Java. Every object, when passed to system.out.println, will have the toString method implicitly executed if you've created such a method on your class. And now, running this code, we get output, and we can see the data in our 5 student objects or records. That's another pretty handy code generation tool to know we can use. So this was a contrived example, but you can imagine if you were reading data from a database or a comma delimited file, how you could create a whole set of Pojos to collect all the data elements in all your records. Once you have all this information in the Pojo, you can pass these objects to whatever code would process it that would need to do something with it, perhaps generate a mailing list or whatever. So, for good measure, let's add the setters and getters to the Pojo. Going back to the student class, we'll generate these. I think you know how by now, selecting code, then generate and getters and setters. And now our code has all we need to manipulate data, setting, updating, and retrieving data. So we're lucky we have IntelliJ's code generation tool to do so much of this work for us. This kind of code has a name. It's called boilerplate code. It's code that's repetitive and follows a pattern, which is why code generation tools can create it for us. But it's still a lot of code to look at, and we only have 4 fields in our Pojo. Wouldn't it be nice if we had a type that did all this for us, and we didn't have to put all this code in our class? Well, we do. Java introduced a new type called the record, which officially became part of Java in JDK 16. We'll talk about the record in our next video. So let's move on to that next video.
It's break time. Do you like this video? Don't forget to subscribe to get new videos. Share this video to open new premium videos and ebooks. We'll be a Starfreelancer.
In the last video, we talked about the plain old Java object, and we showed you how it comes with a lot of what we call boilerplate code. It's code that's repetitive and follows certain rules. In our case, we had a constructor with parameters for every field on our class, as well as getters and setters for each field. We also set up a toString method on this class, so we could print out all the fields on our class in a nicely formatted way. This is code that's repeated over and over for every Pojo or for every Java Bean if you're using Java Beans to leverage Java frameworks that use them. Once created, this code is rarely looked at or modified. In fact, there are tools that'll just regenerate all of this code if your underlying data or domain model changes. Even better though, Java introduced a new type, the record, which became part of the official language in JDK 16. The record was introduced in JDK 14 and became officially part of Java in JDK 16. Its purpose is to replace the boilerplate code of the Pojo, but to be more restrictive. Java calls them plain data carriers. The word carrier is an important term because it means the record has more rules built in than a Pojo would. The record is a special class that contains data that's not meant to be altered. In other words, it seeks to achieve immutability for the data in its members. It contains only the most fundamental methods, such as constructors and accessors or getters. Best of all, you, the developer, don't have to write or generate any of this code. We're back in our record project from the last video. In that video, we created a student class with a constructor and some getters and setters, then we used a for loop to create 5 students. If you didn't watch that video, you can get the code from the resources section. I want you to be able to review the student class next to the record we'll be creating, so please try to have the code in front of you from where we left off in the last video. Now, I'll expand the project panel and highlight SRC because I want to add a new Java class. But this time, I'm going to pick record instead of the default class we've been using all along up until now. You'll see there are others, like interface, enum, and annotation, but don't worry, we'll be talking about those eventually. Right now, we care about the record type. And I'll give it a name, LPA Student. LPA stands for my own company name, Learn Programming Academy, and then Student. Now you can see, this looks a lot like a class. It starts with a public access modifier, but instead of the class keyword, it's using the record keyword. Where's the magic, you ask? It's hard to see at first. But different from a class, you'll notice that in this code, there are set of parentheses after the name of this record, LPA Student. Similar to a constructor, we can set up some parameters within those parentheses, so let's set some up so that the parameters are the same as our student class parameters. In fact, let me just copy that parameter list from the student class constructor. I'll pop over to student.java, copy the parameter list I've set up in that first constructor. Then I'll come back over to LPA student.java and paste those parameters in the parentheses. And that's it. We're ready to use this record now in our code. It's really that simple. Let's go to main.java and show you. Before we make any changes, let's run the main code as it is. And you'll remember we get the output from the toString method we generated in the student class. Now, let's use our new record. I'm simply going to use LPA Student in place of student in the code here. Where I have student, I'll modify it to be LPA Student, the name of our record. I'll use LPA Student as the variable or reference type on line 6. And on that same line, I'll use LPA Student after the new keyword instead of student. This code compiles, and if we run it, we get output that's very similar to the output we got before. The bracket type is different. Let's look at these two source files side by side. We've replaced the 56 lines of code that we have in student.java with these 2 lines of code in LPA student.java. Now, the truth is, the record LPA student doesn't have or support set of methods, but the other functionality, calling the constructor with 4 parameters and printing the data out, is implicitly part of the record. What's really happening here? What does Java tell us about what is implicitly created when we declare a record as we did in this code? First, it's important to understand that the part that's in parentheses, this entire part, is called the record header. The record header consists of record components, a comma delimited list of components. For each component in the header, Java generates a field with the same name and declared type as the record component. So for example, it sets up fields for us as we have them in the parentheses. These become the fields of the record. The field is declared private and final. We'll be talking about final more later, but simply put, it means the field can't be modified. The field is sometimes referred to as a component field. Java generates a toString method that prints out each attribute in a formatted string. In addition to creating a private final field for each component, Java generates a public accessor method for each component. This method has the same name and type of the component, but it doesn't have any kind of special prefix, no get or is, for example. The accessor method for ID in this example is simply ID, open and close parentheses. This is easy to show you in the code. First, I'll drag lpa_student.java back over into the other window and get rid of that side-by-side view, and I'll open the main.java code. Now, let's add some extra code after our for loop. Let's create two students, one will use our Pojo class and one will use our record. Let me set that up. Student, Pojo student equals new student, opening parentheses, double quotes, S923006, comma, double quotes, and comma. Double quotes, the 5th of November 1985, comma, double quotes, Java Master Class, closing parentheses, semicolon. LPA student, record student equals new LPA student, opening parentheses, double quotes, S923007, comma, double quotes, Bill, comma. Double quotes, the 5th of November 1985, comma, double quotes, Java Master Class, closing parentheses, semicolon. Okay, so now let's print some information out about each of these students. System.out.println, opening parentheses, Pojo student, closing parentheses, semicolon. System.out.println, opening parentheses, record student, closing parentheses, semicolon. And if we run that, we can see our two new students at the end of the output and notice the minor differences in the output. This shows us that like IntelliJ's generated method toString, the record is printing information out similarly, though it doesn't include single quotes around strings and the brackets are different. Now let's just print out a couple of the attributes ourselves using the accessor or getter methods. We'll do this first for our Pojo student. System.out.println, opening parentheses, Pojo student.getName, opening and closing parentheses, plus, double quotes, is taking, plus. Pojo student.getClassList, opening and closing parentheses, semicolon. And I'll copy and paste that line, replacing Pojo student with record student in both cases. Now, you can see we have compiler errors for getName and getClassList on that new line of code. We stated in the slide that Java's implicit code doesn't include the prefix get and simply uses the same name as the component or field. Let's remove the prefix and change the case of name and class list to use lower camel case. And now we can run that. And we get the output and is taking Java Master Class and Bill is taking Java Master Class. That's how we use accessor methods, which we've called getters up until now, because traditionally the prefix get was used for the accessor method. And finally, let's see what happens if we try to set data on these two types of students. Let's say they've both added a class or a Java HinXcmOax88 course, for example. Pojo student.setClassList, opening parentheses, Pojo student.getClassList, opening and closing parentheses, plus, double quotes, comma, Java HinXcmOax89, closing parentheses, semicolon. Record student.setClassList, opening parentheses, record student.ClassList, opening and closing parentheses, plus, double quotes, comma, Java HinXcmOax89, closing parentheses, semicolon. And here you can see the line for record student doesn't compile. It doesn't have a setter named setClassList. In fact, it doesn't have a setter at all. There is no way to set the class list other than by passing the value in on the record header or through the use of constructors. This is by design because a record's goal is to be immutable. Let's comment out that last line of code and run our main.java class again. And here you can see, for our Pojo student, we could modify the class list. Why is the record built to be immutable? There are more use cases for immutable data transfer objects and keeping them well encapsulated. You want to protect the data from unintended mutations. If you want to modify data on your class, you won't be using the record. You can use the code generation options for the Pojo, as we showed in the earlier video. But if you're reading a whole lot of records from a database or file source and simply passing this data around, then the record is a big improvement. We've only touched on some of the features of the record to give you an introduction. When we do talk more about the final keyword and immutability of data, especially as it may be affected by concurrent threads, we'll be revisiting this type. We'll also be showing it to you in action when we get to the database and IS sections of this course. In this section of the course, up until now, we've introduced you to the class as the building block for object-oriented programming, and we've talked a bit about encapsulation. In the next set of videos, we're going to cover another key feature of Java support for IO programming, and that's inheritance. In the previous videos, we started working with objects and classes. You got up to speed with that? It's now time to talk about inheritance, what that is, and how that applies to objects. What is inheritance, and why is it so powerful? We can look at inheritance as a form of code reuse. It's a way to organize classes into a parent-child hierarchy, which lets the child inherit, in other words, reuse, fields and methods from its parent. The animal kingdom, with its many classifications, is a pretty good place to start looking at hierarchical relationships. On this slide, we show a small part of the animal classification chart. Each box on this diagram represents a class. The most generic, or base class, starts at the top of the hierarchy. Every class below it is a subclass. So animal is the base class. All the other classes can be said to be subclasses of animal. A parent can have multiple children, as we see with mammal, which is the parent of dog and cat. The child can only have one direct parent in Java, but it will inherit from its parent class's parent, and so on. Let's actually start working through some scenarios in code so that I can show you what inheritance looks like in Java. I've created a project called Inheritance and created the main class and main method. First, let's start with an animal example. We'll create the animal-based class and define all the attributes and behaviors that animals have in common. We know that any animal would have characteristics like size and weight. And animals move and make noise. Though animals move and make noise in very unique ways, we declare the methods on the base class. Let's see what this class might look like on a class diagram. This is just a drawing of the class showing its fields first and methods or behaviors in the section below that. A class diagram allows us to design our classes before we build them. This diagram shows the animal class with the attributes we think that every kind of animal has. All animals have a type, what kind of animal it is. All animals have a size and a weight. Below the fields, we have the behavior that animals have in common, move and make noise. The move method will include a speed, fast or slow, as an argument. Let's create this animal class now. From the SRC folder, I'll right-click and choose New, then Java Class, and name the class Animal. After we have the class in the editor, we'll add the fields from our diagram. Private, string, type, semicolon. Private, string, size, semicolon. Private, double, weight, semicolon. Okay, those are the fields, so now let's add a constructor. We'll use IntelliJ's code generation tool to do this. I'll put my cursor below the last field and select code on the menu, then generate, then constructor. Let's select all the fields and hit OK. Now we've got our first constructor, you can see, on lines 7 through 11. Let's keep this code simple, so we'll leave the getters and setters out. But we do want a method to print the fields out, so again using IntelliJ's generation tool, we'll pick code, generate, and this time we'll select a string. And again, pick all the fields and hit OK. And there's our toString method with all the fields in it. Okay, so we have attributes, a constructor, and a way to print out information about the animal, but we haven't implemented any behavior on animal. Now we'll have the two methods on animal, move and make noise. For move, we'll take a speed, which will just be a string for fast or slow, and then we'll print the animal type and the speed at which it's moving. Public void move, opening parentheses, string, speed, closing parentheses, opening curly brace. System.out.println, opening parentheses, type, plus, double quotes, moves, plus, speed, closing parentheses, semicolon, closing curly brace. And now we'll have make noise that doesn't have any parameters. Public void make noise, opening and closing parentheses, opening curly brace. System.out.println, opening parentheses, type, plus, double quotes, make some kind of noise, closing parentheses, semicolon, closing curly brace. There you have it. We have our base class, the animal, with its attributes, type, size, and weight, and we have three methods on this class to string as well as move and make noise. Next, we want to create a more specific type of animal, and for this, we're going to create a dog class. Let's look at a class diagram that includes the dog class. So, here we show a dog class below, but connected to animal. This means dog inherits from animal. And we can also say dog is a type of animal. When we create a dog object, it'll inherit type, size, and weight fields from the animal class. These don't have to be explicitly declared in dog. This is also true for the methods move and make noise. We can specialize the dog class with its own fields and behavior. We do this here with his shape and tail shape because dogs have ears and tails whose shape is unique to their breeds. We're also saying dogs have behaviors like bark, run, walk, and wag tail. How do we build this in Java and make dog inherit from animal? Let's create a dog class first. To specify we want this class to inherit from animal, we use another Java keyword, extends. Using extends specifies the superclass or the parent class of the class we're declaring. We can say dog is a subclass or child class of animal. We can say animal is a parent or superclass of dog. A class can specify one and only one class in its extends clause. Let's add that clause to our dog class. It goes right after the class name and before the opening curly brace. Extends animal. Now you notice straight away that we've got an error. The error that's on the screen is saying there's no default constructor available in the animal class. And that's true, we never did create one, meaning we never created a constructor with no arguments on animal. But why does this matter to the dog class? Well, right now we haven't declared any constructor for dog, but maybe you'll remember that Java will declare one implicitly if we don't explicitly declare one. And just to see that, let's add a constructor to dog which mirrors the implicit constructor Java creates for us. Public dog, opening and closing parentheses, opening curly brace. Super, opening and closing parentheses, semicolon, closing curly brace. This is what the implicit constructor looks like, and now our error is on line 4. The reason it isn't working is that statement on line 4, super parentheses. Okay, so maybe you're asking the question, what's super parentheses? You remember we used the keyword this, followed by parentheses and parameters as a way to call another constructor in the same class. Well, super parentheses is similar to that. It's a way to call the constructor on the parent class or super class. Here, we're calling animals constructor by using the keyword super and then parentheses, which calls the default constructor on animal. Super with parentheses is a lot like this with parentheses. It's a way to call a constructor on the super class directly from the subclass's constructor. Like this, it has to be the first statement of the constructor. Because of that rule, this and super can never be called from the same constructor. If you don't make a call to super, then Java makes it for you using super's default constructor. If your super class doesn't have a default constructor, then you must explicitly call super in all of your constructors, passing the right arguments to that constructor. Those are a lot of rules, but don't worry if that's confusing right now. We'll be reviewing these rules coming up and in future videos. But for now, we have a compiler error on dog because animal doesn't have a default or no arguments constructor declared for it. Let's go back to animal and add that in. Public animal, opening and closing parentheses, opening curly brace, closing curly brace. And now we've got everything compiling, so that's a good thing. Before we do anything else with dog, let's go back to the main class. Before we create any instances, I want to create a method on the main class that will take any animal object and execute its three methods. We'll call it doAnimalStuff and pass it an animal object and the speed we want this animal to move. And then we'll have animal make noise, move, and then we'll print out all the attributes on animal. Public static void doAnimalStuff opening parentheses animal animal comma string speed closing parentheses opening curly brace. Animal.makeNoise opening and closing parentheses semicolon. Animal.move opening parentheses speed closing parentheses semicolon. System.out.println opening parentheses animal closing parentheses semicolon. System.out.println opening parentheses double quotes underscore 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 closing parentheses semicolon closing curly brace. This method is static because we want to call it from the main method. The last line is just to separate the data so reading the output is easier. Let's create an instance of animal first and then pass that to this method. Animal equals new animal opening parentheses double quotes generic animal comma double quotes huge comma 400 closing parentheses semicolon. doAnimalStuff opening parentheses animal comma double quotes slow closing parentheses semicolon. We created an animal object, gave it the type generic animal and the size huge as well as a weight of 400. And running that, we get generic animal makes some kind of noise and generic animal moves slow. And then we get the data from our toString method, which prints out all the attributes, starting with the class name of the object. Okay, so that's a generic animal. Let's create a dog this time. Dog equals new dog opening and closing parentheses semicolon. doAnimalStuff opening parentheses dog comma double quotes fast closing parentheses semicolon. Before we run this, do you notice what we're doing here? We're passing a dog object as the method argument when the type was declared as an animal. Why is this okay? It works because dog inherits from animal. It's a type of animal, as we've said, and where that becomes really important is in code like this. We can pass a dog instance to any method that takes an animal. And running that, the code compiles and runs and we get output. Null makes some kind of noise and null moves fast. We created a dog with a default constructor, no arguments passed, so nothing got set on this class, but you can see dog has inherited all of animal's attributes on that last line. The values have the default values for their type because we didn't create a way to pass any data to these fields on dog. So far, all we've done with dog is extend animal. Next, let's change our default constructor in dog, and this time, when we call super, we'll pass values to animal's 3-parameter constructor. We'll pass the type of dog, which here we'll call it a mutt, then the size, big, and 50 for the weight. Super, opening parentheses, double quotes, mutt, comma, double quotes, big, comma, 50, closing parentheses, semicolon. And we can rerun our main method. And now, the output has our mutt's attributes, so it prints out that mutt makes some kind of noise, mutt moves fast, and then it shows the other attributes on mutt. What I want you to see here is, look at the dog class. It's 6 lines of code, including the opening and closing braces and white space. But this code can now execute 3 methods and has 3 attributes we can set, all inherited from animal. And better yet, we can treat this dog like any animal for any code that uses the animal class. Our doAnimalStuff method in the main class didn't have to change at all, even though we introduced a new class. Up until this point, we haven't specialized anything for the dog. Since this video is getting long, let's end it here. In the next video, we'll add the fields and methods that make the dog class special. I'll see you in that next video. In the last video, we introduced you to the concept of inheritance and showed you how to implement it in Java using the extends keyword. We talked about using the statement super to call the constructor on the super class. In the last video, we created dog as a subclass of animal and demonstrated that dog inherited all of animal's fields and that it can be passed to methods that are declared with the type animal. In this video, we want to make dog different from animal by declaring the fields and methods that are specific to it. Let's look at the class diagram for just dog at the moment. We want to add the attributes isShape and tailShape as shown here in our class diagram. And we'll implement the methods bark, run, walk, and wag tail. Going back to the dog.java file, we'll add isShape and tailShape. Private string isShape semicolon. Private string tailShape semicolon. Those are our dog-specific fields. Let's create a more specific dog constructor than the one we have. With the cursor on line 10, before the class's closing brace, I'll select code, generate, then constructor. This time, we have an additional choice, and that's which parent constructor we should use. Let's pick the one with parameters. And then, we pick both of our dog attributes and hit OK. Let's actually change this constructor so it's easier to create a dog object. We'll remove size as a parameter and instead write code to derive it, passing that to the super call. Weight less than 15, question mark, double quotes, small, colon, opening parentheses, weight less than 35, question mark, double quotes, medium, colon, double quotes, large, closing parentheses, comma. This constructor has a combination of the dog and the animal fields in its argument list. We can pass at the top of the dog's weight, and the isShape and tailShape. We're calling the super constructor to set some of our fields, the animal-specific fields. And here, we're deriving the size of the dog from the weight, small, medium, or large. To do this, we use a nested ternary operator, which is passed directly to the super constructor. We couldn't do this operation before the call to super because super must be the first statement. But we can do it directly like this as an expression in the argument list. This is one way to perform calculations in your constructor and pass the result to the super call. After the call to the super constructor, we set some of the dog-specific attributes, the isShape and tailShape, that were passed to us. Before we do anything else, let's generate a toString method for the dog class. Again, with the cursor before the closing bracket of the class, select code and generate and the toString method option, but pause here a minute. We have other options we can use to generate this method. You can see it says template and defaults to string concat plus, but we can pick other options. Let's pick the one right after the default one that includes and super.toString. And we'll select our two dog attributes and then OK. And now you can see the code that was generated. You can see the two new fields there, plus a call to super.toString. Now this super is different than the super parentheses call. It's a lot like using this keyword with the dot notation to access a field on the current instance. This code lets us call a super class's method. We'll talk about this a lot more in upcoming videos. I want to add one more constructor after the first one before we test this. Public dog, opening parentheses, string, type, comma, double, weight, closing parentheses, opening curly brace. This opening parentheses, type, comma, weight, comma, double quotes, perky, comma, double quotes, curled, closing parentheses, semicolon, closing curly brace. This constructor makes it even simpler to create a dog object for the majority of dogs if there is a perky and their tails are curled. It calls the other dog constructor that has 4 parameters, which in turn calls the animal constructor. We're using constructor chaining to make this work. Let's go back to main.java and create some more dogs, calling the do animal stuff for each one. Dog, Yorkie equals new, dog, opening parentheses, double quotes, your key, comma, 15, closing parentheses, semicolon. Do animal stuff, opening parentheses, your key, comma, double quotes, fast, closing parentheses, semicolon. Dog, retriever equals new, dog, opening parentheses, double quotes, Labrador retriever, comma, 65, comma. Double quotes, floppy, comma, double quotes, swimmer, closing parentheses, semicolon. Do animal stuff, opening parentheses, retriever, comma, double quotes, slow, closing parentheses, semicolon. Dogs have over 20 ear types and more than 9 tail types, one of which is a swimmer tail type, which we use here. And now, check out what gets printed for both of these dog objects when we run this code. We get all the fields that are specific for dog and the fields that are more general to the animal. That's because our toString method printed out the dog fields, then made a call to super.toString, which was animal's toString method. We were also able to calculate the size of the dog based on its weight, and we created constructors for dog that targeted more dog-like features and passed default values for animal's more general fields. Let's talk a little bit about the behavior of animal and dog next. Up to now, we called methods on animal and were able to access the functionality that's part and parcel of the animal class, and we're able to use methods on and through dog that were defined on animal. And even more importantly, we're doing this from a method that really doesn't even know anything about the dog class. Dog can use methods on animal and print out its own object's values. In this case, both the move and make noise methods printed the type field. You can see why inheritance promotes code reuse. All subclasses can execute methods even though the code is declared on the parent class. The code doesn't have to be duplicated in each subclass, but it does even get better than that. We can use code out of the box from the parent as we did in this example, or we can change that code for the subclass. We did this with the toString method. The toString method that was called in the doAnimalStuff method of the main class didn't actually call the animal toString method. It called the dog toString method when animal is an instance of a dog. I want you to really understand that because it's so important. And really, it's one of the best parts about this inheritance feature. We told this method that we were dealing with an animal class, and we called the toString method, which is declared as a method on animal. At runtime, Java figures out the animal object is even more specific than animal. It's really a dog, and it actually calls the toString method on dog if one exists on dog. If the toString method doesn't exist on dog, that's no problem, because then it just uses the toString method on animal. This is good stuff, so let's explore this a little bit more. Let's create a make noise method on dog next, and this method has the same signature as make noise on animal. Public void make noise, opening and closing parentheses, opening curly brace, closing curly brace. And now what happens if we run our code? The last time we ran this code, we had statements that said the Yorkie and Labrador made noise. But now we don't see anything like that. This method, make noise on dog, which doesn't do anything, was called and not the make noise method on animal. What have we really done here? Well, we've overridden animal's make noise method. Overriding a method is when you create a method on a subclass which has the same signature as a method on a superclass. Remember that a method signature consists of the method name and the number and types of parameters. You override a parent class method when you want the child class to show different behavior for that method. So notice in IntelliJ that it has a special icon next to this make noise method, the little o with an arrow. This is IntelliJ telling us this method is overriding a parent class's method. Another option is to use IntelliJ's code generation tool to override methods. Let's use that way now to override the move method on animal. Select code from the menu, but let's select override methods this time. And IntelliJ is showing us all the methods we could override, starting with animals, but it's also showing us methods on java.lang.object. I'll be talking about java.lang.object in just a bit. Let's pick the move method on animal and hit the OK button. Now look at the difference between the code we created manually, the make noise method, and this one the move method that IntelliJ created for us. IntelliJ's generation tool has this override symbol, and that's to remind us that we're overriding a method that's in the superclass. In this case, it's in the animal class. And notice too that the automatically generated code simply makes a call to the parent class's method move using the keyword super and .move. What that means is we're calling the move method on the parent class the animal class. This code kind of does the same thing as not having that overridden method at all. It simply executes the animal class's move method, which would have happened if we didn't create this method at all. Why would we do this? Well, most likely we'll want to change or extend the code here. We changed the make noise method by having a method with no code at all. This changed the behavior of make noise for all dog objects. It made all our dogs silent for the moment. Next, let's extend the functionality for the move method. This means we'll do what the animal class does, but we'll do additional stuff as well. We'll leave the super.move statement there, but we'll add more code. Here, we'll just print out another statement that dogs walk and run and wag their tail. System.out.println, opening parentheses, double quotes, dogs walk, comma, run and wag their tail, closing parentheses, semicolon. And running the code now. We can see from the output that when we called the move method, we did what animal had us do with that statement, you can move fast, but we added another line of text to the output, dogs walk, run, and wag their tail. We extended the functional behavior of animal for dogs. We used what was there with the call to super.move, but then added our own code to it. I think this is a good place to end this video. In this video, we created methods on a superclass, then called them from a subclass directly, showing you that methods can be inherited as well as fields. We also showed you that a subclass can override a superclass's methods. The overridden method can do one of three things. It can implement completely different behavior, overriding the behavior of the parent. It can simply call the parent class's method, which is somewhat redundant to do. This is the default behavior of an inherited method. Or the method can call the parent class's method and include other code to run, so it can extend the functionality for the dog for that behavior. In the next video, we'll implement methods unique to dog. In other words, the behavior we think only makes sense for dogs. We'll see you in that next video. In the last video, we were working off of a simple class diagram to create two classes, animal and dog, where dog inherited from animal. Let's continue with this example by adding other methods that are really specific to dog. Let's bring up that dog's class diagram again real quick. And we can see there the methods on dog are bark, run, walk, and wag tail. Let's add these, starting with the bark method. I'm going to make this method private because I'm going to call it from the move method. This is a reminder that not all methods need to be exposed, especially if you only intend them to be called internally from the current class. Private, void, bark, opening and closing parentheses, opening curly brace. System.out.print, opening parentheses, double quotes, with closing parentheses, semicolon, closing curly brace. Let's copy and paste that to create the run method, changing the name of the method to run, and instead of off, we'll change that text to dog running. And we'll do the same for walk, again changing the name to walk and the text to say dog walking. And finally for wagtail, change the name from bark to wagtail and the text that's printed to tail wagging. Okay, so those are our dog behaviors, so let's use some of these methods from dog's move method. We'll comment out the system.out.println statement first, then just add some dog movements by calling some of our dog methods based on whether the dog moves fast or slow. If opening parentheses, speed equals, double quotes, slow, closing parentheses, opening curly brace. Walk, opening and closing parentheses, semicolon. Wagtail, opening and closing parentheses, semicolon. Closing curly brace, else, opening curly brace. Run, opening and closing parentheses, semicolon. Bark, opening and closing parentheses, semicolon. Closing curly brace. System.out.println, opening and closing parentheses, semicolon. Now, if we run that, the output shows our dogs moving. First the Yorker moves fast, and then it prints dog running, woof. Then we have Labrador Retriever moves slow, and that's now also printing dog walking, tail wagging. And again, nothing in the do animal stuff method had to change for this new functionality to be called. I hope you're starting to get a little glimpse at how powerful a feature this is. And lastly, we can call the bark method in the overridden method, make noise, which right now has no code in it. Here, we're not calling animals make noise method, and we don't want to. We want the dog to have behavior that the animal doesn't have. Bark, opening and closing parentheses, semicolon. System.out.println, opening and closing parentheses, semicolon. Let's run that. And now you can see that we get woof for both types of dogs when we call the make noise method in the main class. We've overridden the make noise method with code unique to the dog, which in this case makes a call to the bark method. And that's how you do it. You can separate the functionality that's just for a dog and only include it in the dog class. Let's try to change our make noise method again. This time, if the type of the dog is a wolf, let's have the dog howl and bark. If opening parentheses, type equals, double quotes, wolf, closing parentheses, opening curly brace. System.out.print, opening parentheses, double quotes, alwoo, closing parentheses, semicolon, closing curly brace. Now, in this case, where we're referencing type, we get a compiler error. This is because type has private access in animal, but type is one of the fields inherited by dog. Yes, but because type is private on animal, no other classes, not even subclasses, can access or use this field in its own methods. We've said there's a modifier that allows access for subclasses, and that's the protected modifier. Let's go to the animal class and change the modifier from private to protected for the type field. What this modifier says is that any class that is a subclass access this field. This is conditional encapsulation. We're allowing some limited access to our internal fields, and that's to subclasses. Protected access also means that any classes in the same package will also have access. And changing that modifier means our code compiles successfully. Let's look at that code in dog again. Notice here that we just simply reference type here. We didn't add any other qualifier, not this or super, and we didn't have to call type from a different instance of dog. This is another advantage of inheritance for fields and methods that are private. They can be accessed directly as if they really were declared on the subclass itself. Java first looks on the subclass for a method or a field with that name, then it'll go up the inheritance tree looking for a match. Let's quickly test this by creating a wolf in the main method of the main class. Dog, wolf equals new, dog, opening parentheses, double quotes, wolf, comma, 40, closing parentheses, semicolon. Do animal stuff, opening parentheses, wolf, comma, double quotes, slow, closing parentheses, semicolon. And now, running this code, we can see all the information about our wolf, and we can also see the output that our wolf is howling as well as barking. That was the dog class. Let's add another subclass so you can get used to this inheritance concept and the idea of extending another class. Let's add the fish class to our hierarchy. What are some unique characteristics of a fish? Well, let's go with a couple like gills and fins. And instead of a generic move method, we might have more specific methods like move muscles and move back fins. Let's look at our class diagram that includes this new fish class. It's quite a bit different from dog, but it's still an animal. This diagram shows a new class named fish that extends animal. It has two fields and two methods specific to its own type. Let's build that fish class. We'll open the project panel and highlight the SRC folder and select new Java class and give it the name fish. Then we want to add extends animal as part of the class declaration. Then we'll add the two fields we showed, gills and fins. Private int gills semicolon. Private int fins semicolon. And then we'll add the constructor. We'll use IntelliJ to generate that for us. So again, code generate constructor. Then we pick the animal constructor with parameters and then our two fields for fish. And like we did with dog, let's remove size, and this time we'll just change size to be hard-coded to small for simplicity. This constructor is a lot like dogs. We're calling the super constructor the constructor on animal, and we pass the type, the size, and this time we'll make all fish small. And finally, we pass the weight. Then we have the assignments for fish's more specialized fields, gills and fins. So very similar to the dog class. But in this case, we've created a new fish class that inherits from the animal class, and we've defined some unique characteristics for the fish, namely gills and fins. Let's next add fish's custom behavior and add the method move muscles first, and we'll just print out a statement for that. And we'll make this method private because we only want the move method to call it. We won't expose this behavior, in other words, for any outside code to call it directly. Private, void, move muscles, opening and closing parentheses, opening curly brace. System.out.print, opening parentheses, double quotes, muscles moving, closing parentheses, semicolon, closing curly brace. And rather than type in the second method, let's copy and paste the move muscles method and just change the name to move backfin and change the text to say backfin moving. And now we'll override the move method from animal so that our fish moves or swims. With our cursor right before the closing brace of the fish class, we'll start typing public void, and you'll see IntelliJ pops up a list of methods, and from that we'll select move. And now we have the overridden move method generated for us. Like we did with the dog class, let's extend this behavior for a fish. We'll have our fish move its muscles regardless of the speed, but use its backfin if it wants to go fast. Move muscles, opening and closing parentheses, semicolon. If opening parentheses, speed equals, double quotes, fast, closing parentheses, opening curly brace. Move backfin, opening and closing parentheses, semicolon, closing curly brace. System.out.println, opening and closing parentheses, semicolon. That would be one way to model the fish moving or swimming. It moves its muscles and it moves the back fin, which the net result of that is it actually propels itself or moves. Let's add a code generated to string method for fish, like we did for dog, that prints both fish's fields as well as animals. Selecting code and generate, then pick to string method. And that's it. We've built the fish class, so let's create an instance of fish and call our doAnimalStuff method. And we can call that method with fish without changing that method at all, because fish is another type of animal. Fish, Goldie, equals new fish, opening parentheses, double quotes, goldfish, comma, 0.25, comma, 2, comma, 3, closing parentheses, semicolon. doAnimalStuff, opening parentheses, Goldie, comma, double quotes, fast, closing parentheses, semicolon. And running that, we can see the output from this additional code. Goldfish makes some kind of noise, goldfish moves fast, and then we have muscles moving, backfin moving. Again, we used animals fields and behaviors, the ones we wanted to use, and then added some more specific elements to the fish class. And we passed fish to a method that never even had to know a fish class existed. We're going to be coming back to this particular feature a lot because it has a special name, polymorphism. Polymorphism simply means many forms. In this video, we showed that animal can take multiple forms, the base class animal or a dog or a fish. And as you've seen, some advantages of polymorphism are, it makes code simpler. We can write code once using the base class or superclass as we did with our doAnimalStuff method. We wrote that code without ever having to know about subclass types. We didn't have to write code to check the type of the object and then decide what method to call. Java did all that at runtime. It encourages code extensibility. It's very easy to subclass and override or extend the method that'll be called as we demonstrate it. We have a whole video on polymorphism in the next section where we cover this powerful object-oriented concept as well as others. Okay, so we've covered a lot of ground in the last 3 videos introducing you to some key concepts of inheritance. What you may not have realized is that we've been using inheritance all along, even when we didn't think we were. That's because in Java, all classes, and that includes any we create, implicitly inherit from a single built-in Java class. Let's talk about that in the next video. In the last couple of videos, we introduced you to inheritance and how it works with a class hierarchy. We talked about the base class, also called the superclass, and subclasses. We demonstrated overriding methods, and we gave you a quick look at how inheritance plays into polymorphism in Java. Maybe you're thinking that inheritance looks kind of interesting, but when will we really use it? Well, it turns out in Java, we've been using inheritance all along without even knowing it. This is because every class you create in Java intrinsically extends a special Java class. This class is named Object, and it's in the java.lang package. Okay, that's confusing, a class called Object. Let's see what Java has to say about this class. We used a link to Java's Application Programming Interface API for this class, which you can find in the Resources section of this video. There it is. This is a class called Object. Class object is the root of the class hierarchy. Every class has object as a superclass. All objects, including arrays, implement the methods of this class. Whether you knew it or not, your classes were extending this class object. They all inherit from object. And what that means is all of your classes have functionality built in that you can use or override the minute you create them. Let's explore the methods on java.lang.object. We can select the method tab from the summary list. And here you can see some of the methods on object like clone and equals. And also here is one we just showed in the last couple of videos, the toString method. Every class we create or use is automatically inheriting from this Java supplied class called the object class. Let's get back to some code in IntelliJ and see what this means and how it works. For this video, I've created a project called the object class and created the main class with main method. We've said every class inherits from object, and this actually includes the main class. How can we tell? We can use the code generation tools, and you can see that by opening up your generate command if you go to override methods. You can see when I've done that, select methods to override or to implement. And you can see these are all methods. The M stands for method. And these are all methods that are inherited from java.lang.object, which is a class that classes you create automatically extend. That's equivalent, essentially, to typing extends object, java.lang.object, so let's do that in our main class. Extends java.lang.object. We could also just omit the package name, java.lang, and just say our class extends object. At the end of this section of the lecture, we'll be talking more about packages. Let me do that. For now, I'll just say that Java has a way of implicitly doing things that make our jobs easier. One of these is to include all objects from its core libraries automatically, so we can refer to them like we do here as simply object, for example. The other is to implicitly have all classes extend this object class that do not explicitly extend from another class. Just to be clear, we can show this on a class diagram. This slide shows that our main class inherits from, or is a subclass of object that's also a string, a class we are pretty familiar with already. This slide shows the methods on object, main, and just a few of the methods on string. The string class has over 60 methods. In alphabetical order, these methods start with one called chowat and end with one called valueof. The string class overrides several methods on object, two of which are equals, which we'll be discussing in our lecture on all things string, and toString, which we used in the previous lectures. All objects, including arrays, inherit the methods of the object class. That's really important to know this happens automatically. Now, let's double-click Object in the code and right-click the mouse to bring up options. We can select Go To and then Declarations and Usage. This is the Control-B key combination for Windows users. This displays the actual source code of the class, in this case object.java, which is inherited automatically when you create any class. You can see as we scroll down that we'll go through some of these methods. We see hash code and the equals method, which compares one type of object to another. This has a lot of detail about the implementation of each of these methods. In general, there are very specific times you'll be overriding these methods, and we'll be showing you examples as we proceed through the course. There's also toString, which it says is just a way to return a string representation of a specific object. Let's explore toString a little more using main.java. We'll close object.java first. Let's add a new class in main.java itself, and we'll call it student. Remember, only one class in a Java source file can be public, and since we've already made main public, we won't make student public. Class student, opening curly brace. Private string, name, semicolon. Private int, age, semicolon. Closing curly brace. That's a simple class named student with a name and an age. Let's add a constructor so we can quickly pass data to the class when we create it. Student, opening parentheses, string, name, comma, int, age, closing parentheses, opening curly brace. This dot name equals name, semicolon. This dot age equals age, semicolon. Closing curly brace. Now, let's create an instance of student in our main method and print student out. Student max equals new student, opening parentheses, double quotes, max, comma, 21, closing parentheses, semicolon. System.out.println, opening parentheses, maximum to string, opening and closing parentheses, semicolon. And running the code, we get student at 65AB7765. You might get something different, but that's fine, and I'll explain it soon. What is that? Well, the code in the toString method in the object class prints out the class name, which in our case is student, followed by an @ sign, then the hash code of the object. A hash code is an integer that is unique to an instance in the currently executing code. When an instance is created, it's assigned a hash code, and that hash code is what can tell us if our multiple references are pointing to a single instance. It's a mechanism for comparison, in other words. This really is like an address for a house, which we talked about in our examples to explain the difference between references and objects or instances. Anyway, this isn't what we want printed out. We really want to print out the name and age of our student. And we've done this before, but now I hope it's becoming clear what we're doing. We're overriding the toString method on object. Let's do that on student. First, let's just type public and then to in lowercase, and notice IntelliJ has popped up choices we could select. Let's pick that first option. And now we have a toString method that simply calls super.toString. Do you think that does anything different? Maybe you'll remember we've said that calling a method on super like this without doing anything else is kind of redundant. Let's confirm that by running the code. And we get the same result. We've really just explicitly called the code that Java would have implicitly done for us. Let's comment that code out and try the other option next. Again, we'll type public and 2, then pick the second option, which has generate via wizard in it. And this should look familiar. This brings up IntelliJ's code generation window for the toString method. And we'll select both fields and hit OK. We've done this before. We're simply specifying for this class what we want to print out. Running this code now gives us the student class name still, but now in brackets. We can see this object has name equals max and age equals 21. Let's change this and just simplify it. We don't really care that the class name is student. We'll comment out the default generated code and simply return the student name and say how old they are. Return name plus double quotes is plus age semicolon. And now if we run that, we get max is 21. You make this code be whatever you want it to be when the toString method is called on your class. You may also remember that I told you Java implicitly calls the toString method on an object if you simply pass your object to system.out.println. Let's confirm that by changing system.out.println and removing the .toString. Here, we simply pass the max student object to the println method on system.out. And if we run that, we can confirm that this code is really calling the toString method on student and max is 21 is still printed out. And what happens if we now have another class that extends student? Let's create a primary school student class, which would be a student who is age 5 to 12, for example, in the elementary or primary school, and this student will have a parent name associated with it. For the sake of simplicity, we'll just include one parent. Let's look at a class diagram. We've already built student, which inherits from object implicitly. Next, we'll build primary school student, which will inherit from student. Let's add this new class. Class primary school student extends student opening curly brace. Private string parent name semicolon. Primary school student opening parentheses string name comma int age comma string parent name closing parentheses opening curly brace. Super opening parentheses name comma age closing parentheses semicolon. This dot parent name equals parent name semicolon. Closing curly brace. Closing curly brace. Hopefully you understand what we're doing here with this code. We've created a primary school student class that extends student. We've added an attribute specific to a primary school student and called it parent name. And we've set up a constructor with 3 fields, the 2 fields we had for student, name and age, and now parent's name as well. We call super with name and age in parentheses to call student's constructor. And we set the parent name to the argument with the same name. Let's create a primary school student in the main class. We'll name him Jimmy and his parent will be Carol. Primary school student Jimmy equals new primary school student opening parentheses double quotes Jimmy comma 8 comma double quotes Carol closing parentheses semicolon. System.out.println opening parentheses Jimmy closing parentheses semicolon. And running that, we see that we get Jimmy's 8 as the output for this code. This code inherited students to string method code, and now we can overwrite to string again, this time on primary school student. Here, we'll return the parent name and then call the toString method on student with the super keyword. Parent name plus double quotes skid comma plus. And when we run that, we get the output, Carol's kid, Jimmy's 8. In this case, super.toString didn't call objects to string method, it called students. But it still inherits objects' other functionality indirectly through student. Java only supports one class in the extends class. For example, we couldn't type student, then object. This is a compile error. The inheritance tree is cumulative, meaning that primary school student inherits both student members and object members. Object members are accessible as long as student doesn't override them. Because student overrode toString, we no longer can simply call the toString implementation on object from primary school student. Let's revert that last change and we'll end the video here. In this video, we learnt that all classes which do not explicitly extend another class will implicitly extend a class named object. Object is the base class or root class of every class in Java, which means all classes can use or override objects' methods. Next, I want to give you a challenge on inheritance. I'll see you in that next video.
It's break time. Do you like this video? Don't forget to subscribe to get new videos. Share this video to open new premium videos and ebooks. We'll be a star freelancer.
In the previous videos, we introduced you to inheritance and the way Java supports inheritance with the use of the extends keyword. Now it's time for a challenge to solidify your understanding of what inheritance is. For this challenge, I'm going to show you a class diagram like we worked with in the previous videos. This describes a lot of the challenge in a picture. This diagram starts with worker at the top of the hierarchy. This is the base or super class. It shows one subclass, employee, but you could imagine other types of workers, perhaps contractors, and interns, for example. From employee, we have 2 subclasses. These are salaried employee and hourly employee. Your challenge is to create the worker class, the employee class, and either the salaried employee or the hourly employee class. You don't have to do both, but if you want to, go right ahead. For each class, create the attributes and methods shown on this diagram. Note that employee has no methods of its own. Create a main method that will create either a salaried employee or hourly employee and call the methods getAge, collectPay, and the methods shown for the specific type of class you decide to implement. So if you implement salaried employee, then execute retire. If you implement hourly employee, then execute get double pay. Have a go at doing that challenge. This will really help your understanding of what inheritance is. And pause the video now, go away and do that, and once you've had enough, or once you've got a solution, and you want to compare the solution to what I've come up with, come back and we'll go through it together. Okay, how did you get on? Did you figure it out? And bearing in mind, there isn't only one answer to this. There's quite a few different ways to implement this. I created an inheritance challenge project already, and I have the main class with a main method. Logically, we'd start at the top of the hierarchy, which is our most generic class or base class. This is our superclass, and in this case, that's the worker class. I'll expand the project panel and highlight the SRC folder and create a new Java class and call that worker. Our diagram identified at least 3 attributes that a worker might have: name, birth date, and end date, which would be the employment end date. Private string, name, semicolon. Private string, birth date, semicolon. Protected string, end date, semicolon. I made these attributes private except for end date. The end date will get set by a method either on this class or a subclass, so making it protected will give a subclass the flexibility to operate on it. Next, we'll create at least one constructor. Let's use IntelliJ's code generation for this, so I'll position my cursor where I want the constructor to go, line 7 here, and select code, generate, and constructor, and pick just name and birth date. It's unlikely if when we create a new worker, we'd know the end date, so I'm not going to include it here. And now you can see lines 7 through 10, the first constructor that takes name and birth date. We also want to add a default constructor on worker, which gives our subclasses a little more flexibility. Again at line 7, this time I'll just type in the no arguments constructor. Public worker, opening and closing parentheses, opening curly brace. Closing curly brace. We could add getters and setters at this point, but we don't really need them for this challenge. Next, let's add the methods and generate a toString method for this class. Taking another look at the worker class, we can see the methods are getAge, collectPay, and terminate. Starting with getAge. This should return an int that represents the age of the person using the current year and the birth date, which is a string. Public int getAge, opening and closing parentheses, opening curly brace. Int current year equals 2025, semicolon. Int birth year equals integer.parseInt, opening parentheses, birthdate.substring, opening parentheses, 6, close both parentheses, semicolon. Return, opening parentheses, current year minus birth year, closing parentheses, semicolon. Closing curly brace. This code starts out by creating a local variable for the current year, which we arbitrarily set to 2025. We're going to assume dates, birth date, hire date, and end date will be in the format mm/dd/YYY. We'll use a method on string called substring to get the birth year and birth date. String has over 60 methods on it, and it's not really feasible to cover them in any single video, but eventually you'll see almost all of them as we progress through the course. Later in this section, though, we'll be looking at many of the most common ones when we cover strings and text blocks. For this method, substring, we pass the start position of the string we want to extract, and since indices start with 0, the birth year starts at position 6. If we only pass the start position and not the end position, the string return will be whatever is from the start position to the end of the string. Then we use the integer wrappers parseInt method to turn a string into an integer, which we've done before. Lastly, we return the difference between the current year and the birth year to estimate age. That's the getAge method. Let's add the collectPay method. This will just return a double representing pay that will be received for a work period. We'll just return 0.0 for workers collectPay method. public double collect pay, opening and closing parentheses, opening curly brace. Return 0.0 semicolon, closing curly brace. This method is one which should be overridden by subclasses that can figure out the right pay to return based on the type of worker, etc. And now let's add the last method, terminate, which is terminate employment, really. This will take a date and set the end date to that day. Public void terminate, opening parentheses, string, end date, closing parentheses, opening curly brace. This dot end date equals end date, semicolon, closing curly brace. This looks like a setter, doesn't it? We could have just created a setter, but creating a terminate method is a bit clearer for the business logic. And subclasses might want to override it and add additional code that's specific to terminating employment of a certain type of worker. Finally, let's generate the toString method for worker, so we'll pick code from the menu, generate, then toString, and all the fields. Okay, so that's our superclass. Now let's create the employee. Let's look at that class again. For this class, we have specific employee attributes, employee ID, and hire date. For simplicity's sake, we haven't included any methods specific to an employee. But you could probably think of some, like get a job review or take a vacation, for example. Let's build this. We'll click New, Java class, and call it employee. When we create a new class, the cursor is positioned between the class name and the opening bracket, so we can just type in extends worker. And so we have a subclass. You'll notice this time we don't get a compiler error like we did in a previous video the first time we used the extends keyword. This was because we created the default constructor for worker, so Java can create a default constructor for employee with its own implied call to the empty constructor. Let's add our employee fields next. Private, long, employee ID, semicolon. Private, string, hire date, semicolon. Let's generate the constructor with all fields. You'll notice this time that we can pick which constructor on the superclass will get called from this constructor. Let's pick the one with two fields. And we get the code shown on lines 6 through 10. You can see the call to superconstructor as the first statement in this constructor. You'll remember this has to be the first statement, otherwise we'll get a compiler error. This constructor has 4 fields, 2 fields that were declared by the worker class and 2 fields declared on the employee class. Let's add toString next. Remember to include the superclass toString method as well if it's not selected by default. And now let's test the code we have so far. We'll open up the main.java file and add some code to the main method. Employee Tim equals new employee opening parentheses double quotes Tim comma double quotes the 11th of November 1985 comma 77001 comma double quotes the 1st of January 2020 closing parentheses semicolon. System.out.println opening parentheses Tim closing parentheses semicolon. System.out.println opening parentheses double quotes age equals plus tim.getAge opening and closing parentheses semicolon. System.out.println opening parentheses double quotes pay equals plus tim.collectPay opening and closing parentheses semicolon. And running this code, we get Tim's information all printed out when we pass Tim to system.out.println. And then we've printed out age, which was calculated to be 40 if the year is 2025 and the pay is 0. This is all good, but let's not pass employee ID on the constructor. Let's generate it. We can do this by setting a static field called employee number on employee. Let's set that to 1, so our first employee is employee 1. Private static int employee number equals 1 semicolon. And now let's simplify our constructor, removing the employee ID argument. And we'll set employee ID here, but use that static employee number field we just created. This .employee ID equals employee.employee_no++, semicolon. Using the class name when using a static field helps people reading this code understand what's occurring. Notice here that we're using the post increment operator. And now we've caused an error in the main method, so let's go back to that, and we don't have to pass that 77001 now because our constructor is going to build an employee ID for us. Let's remove that, and if we run it, we get the same output, except Tim's employee ID is 1. Let's just add another employee so you can see how the static field is working. Employee Joe equals new employee, opening parentheses, double quotes, Joe, comma, double quotes, the 11th of November 1990, comma, double quotes, the 3rd of March 2020, closing parentheses, semicolon. System.out.println, opening parentheses, Joe, closing parentheses, semicolon. And if we run that, check out the employee ID for Joe is 2. That's because employee number, that static field, now has the number of the next employee's employee number. Remember, a static field is a place that lets you share data among all your instances. When you're generating an ID for a new employee, it's a place to find the next ID to use. Okay, we'll end the challenge video here and pick it up in the next video. In this video, we created a worker class and an employee class that inherited from worker. In the next video, we're going to go a level deeper and create a specific type of employee. In the last video, we got through 2/3 of the inheritance challenge as shown on the diagram on this slide. We created the worker and the employee classes with the attributes and methods shown here. We also overrode the toString method, which you know by now was originally declared on the object class. We overrode toString for worker and then overrode it again, but extended it further for the employee class. Now it's time to build a more specific type of employee, one that's salaried or one that's hourly. A salaried employee is paid based on some percentage of his or her salary. If this person is retired, then the salary may be 100%, but it is generally reduced somewhat. An hourly employee is paid by the hours worked and the hourly rate they agreed to work for. An hourly employee may also get double pay if they work over a certain amount of hours. The challenge asked us to just pick one type of employee and build it out. I'm going to create the salaried employee next, so let's focus on just that class. We see that we have 2 new attributes that are specific to a salaried employee. These are annual salary and a flag is retired or Boolean. This means our retired person will still get paid, but not his or her full salary. We'll have one method retire that will set the isRetired field to true. Let's create a new class in our inheritance project called salaried employee. And we'll add extends employee right away after salaried employee. And that won't compile, as we see, without a constructor declaration that calls employees constructor. But first, let's add our fields for this class. Double annual salary, semicolon. Boolean is retired, semicolon. And now, with our cursor on line 6, before the closing class brace, we'll use code, generate, constructor, and just pick annual salary. Remember that isRetired is false by default and annual salary is initialized to 0. Now we can create a salaried employee with just one extra field than we did with the employee, the annual salary. Now we're ready to hire a salaried employee. In fact, let's just change our main method and make Joe, our second employee, a salaried employee. Running this will give us the same output because we haven't overridden toString, and actually we don't want to. We wouldn't want our employee's salary to inadvertently get out, so we'll keep it well encapsulated and we won't print that out on the toString method. We did, however, want to override the collectPay method on worker so Joe can get paid. In the salaried employee class, let's add that method. Let's say salaried employees get paid every other week, so we'll want to divide Joe's annual salary by 26 weeks to get his biweekly pay. We'll cast that to an int to remove any decimal part for now for simplicity's sake. By the end of this section, we'll cover several options available for formatting strings. But for now, we'll just pay and hold dollar amounts. And override public double collect pay, opening and closing parentheses, opening curly brace. Return, opening parentheses, int, closing parentheses, annual salary divided by 26, semicolon, closing curly brace. And let's make a call to that method in the main method. System.out.println, opening parentheses, double quotes, Joe's paycheck equals dollar plus Joe.collectPay, opening and closing parentheses, semicolon. And running that, we see that Joe's paycheck equals $1,346. Now let's implement a path to retirement with the method retire on salaried employee. Let me type that out, then we'll talk about it. Public void retire, opening and closing parentheses, opening curly brace. Terminate, opening parentheses, double quotes, the 12th of December 2025, closing parentheses, semicolon. Is retired equals true, semicolon. Closing curly brace. Okay, so first we're calling a method called terminate. Do you remember which class's method that is? It's on worker, the grandparent of this class, or the base class after object. As long as the parent class doesn't override its parent's methods, then these methods can be called from any descendants. Next, we set the isRetired field to true. Before we retire Joe, let's edit our collectPay method. Let's say the maximum pension can only ever be 90% of their final salary. Double paycheck equals annual salary divided by 26, semicolon. Double adjusted pay equals opening parentheses is retired, closing parentheses, question mark, 0.9 times paycheck, colon, paycheck, semicolon. Return, opening parentheses, int, closing parentheses, adjusted pay, semicolon. Then go back to the calling code, the main method on main.java. J.retire, opening and closing parentheses, semicolon. System.out.println, opening parentheses, double quotes, Joe's pension check equals dollar plus Joe.collectPay, opening and closing parentheses, semicolon. And now, running that, we find out that Joe's pension pay will be $1,211. For the salaried employee, we overrode collectPay, a method declared on worker, and we implemented it using code that was unique for a salaried employee. We also implemented a method that wasn't found on either worker or employee because it really only made sense for a salaried employee, which was retire. So did you implement salaried employee? Were you able to do it successfully? Or maybe you implemented the hourly employee class. We're actually going to walk through that next. Let's examine that class briefly. On this one, we have one additional field, hourly pay rate, which is what this worker will get paid for each hour worked. We'll also implement a method called getDoublePay. Let's create a new class in our inheritance project called hourly employee. And now this one too should extend employee. As we did with salaried employee, we'll have a compiler error until we implement a constructor, but first let's add our field. Private double hourly pay rate, semicolon. And now we'll have IntelliJ generate our constructor by selecting code, generate constructor. And that gets rid of our compiler error. In this case, we'll be passing the hourly rate for our hourly employee. Let's add our two methods real quick. We want to implement collectPay for this class, overriding the one on worker, just as we did for the salaried worker, but with a different calculation. In this case, let's just assume our hourly worker gets paid weekly and that he or she works 40 hours in a week. And override public double collectPay, opening and closing parentheses, opening curly brace. return 40 times hourly pay rate, semicolon, closing curly brace. And now we'll implement get double pay. We'll make this one simple too, for the sake of time, and just return double of the normal pay. Public double get double pay, opening and closing parentheses, opening curly brace. Return 2 times collect pay, opening and closing parentheses, semicolon, closing curly brace. Now this call to the method collect pay will call the collect pay on this class and not the collect pay method on worker. Moving over to the main method, we'll create an hourly employee named Mary and we'll make her hourly rate $15. First we'll create the employee and just print out the employee data. Hourly employee Mary equals new hourly employee, opening parentheses, double quotes, Mary, comma, double quotes, the 5th of May 1970, comma, double quotes, the 3rd of March 2021, comma, 15, closing parentheses, semicolon. System.out.println, opening parentheses, Mary, closing parentheses, semicolon. Next, we'll print out both collect pay and get double pay. System.out.println, opening parentheses, double quotes, Mary's paycheck equals dollar plus Mary.collect pay, opening and closing parentheses, semicolon. System.out.println, opening parentheses, double quotes, Mary's holiday pay equals dollar plus Mary.get double pay, opening and closing parentheses, semicolon. And running the code, we get the information for Mary. You can see her employee ID is 3, her weekly pay is $600. Her double time pay would be double that, or $1,200. That was a quick implementation of the hourly employee class. Did you pick that one and did it look anything like this one? Or are you still a little confused about what we did? Let's see if we can figure out what we really did here. This slide is showing our Joe and Mary objects. Each method call made on these objects points to the code that will actually be executed. In other words, it shows where the method is, what class it's on. This isn't always so obvious when you're using inheritance. When Joe and Mary call getAge, the method's implementation is on worker and not overridden by any other class, so the getAge method on worker is executed. When Joe and Mary call to string, this method has been overridden twice, first by worker and then by employee. But it wasn't overridden by either salaried employee or hourly employee, so the method from the employee class is the one that's used. Now, looking at the collect pay method, this method was overridden by both salaried employee and hourly employee. Joe will execute the method on salaried employee, and Mary will execute the one on hourly employee. And finally, salaried employee has a method, retire, that's not overridden, meaning it's only on that class. It's a method specific to a salaried employee. An hourly employee has its own method, get double pay, which wouldn't apply to a salaried employee, so we declared it on this class and not in any super class. Okay, so that was the challenge. I hope you got a lot out of that. If you're still confused, don't worry. The next 2 videos are going to review some of the points we've covered, so let's move on. Let's now discuss the difference between the this and the super keywords. And we'll also find out about the differences between the this and super method calls, as you can see by adding parentheses on the end. Alright, so let's start with the super and the this keywords first. Now, the keyword super is used to access or call the parent class members, variables and methods. Now the keyword this, on the other hand, is used to call the current class members, variables and methods. This is required when we have a parameter with the same name as an instance variable or field. Now note that we can use either of them anywhere in a class except for static elements like a static method. Any attempt to do so there will lead to compile time errors. The keyword this is commonly used with constructors and setters and optionally used in getters. Now in this example, we're using this keyword in the constructor and setter since there's a parameter with the same name as the instance or field. In the getter we don't have any parameters, so there's no conflict, so therefore this keyword is optional there. Now the keyword super is commonly used with method overriding when we call a method with the same name from the parent class. Now in this example, we have a method called print method that calls super.print method. In other words, it's calling the method with the same name from the parent class. Now, without adding the keyword super in this case, it would end up being a recursive call. What that means is that the method would call itself forever, or actually until memory is fully used on your computer. That's why we need the super keyword so that we can call a method with the same name from a parent class. Alright, so in Java we've got the this and super parentheses call. So notice the parentheses. These are known as calls since it looks like a regular method call, although we're calling certain constructors. You use this parentheses to call a constructor from another overloaded constructor in the same class. Now the call to this parentheses can only be used in a constructor, and it must be the first statement in a constructor. It's used with constructor chaining, in other words when one constructor calls another constructor, and it helps to reduce duplicated code. Now the only way to call a parent constructor is by calling super parentheses, which calls the parent constructor. The Java compiler puts a default call to super parentheses if we don't add it, and it's always a call to the no argument constructor, which is inserted by the compiler. In other words, a call to the constructor that hasn't got any arguments. And keep in mind that the call to super parentheses must be the first statement in each constructor. And importantly, a constructor can have a call to super parentheses or this parentheses, but never both. Alright, so let's look at some code which I would call a bad constructor example. Here we have three constructors. All three constructors initialize variables. But there's repeated code in each constructor, as you can see there. We're initializing variables in each constructor with some default values. Now you should never write constructors like this. Let's look at the right way to do this by using a this parentheses call. In this example, we still have three constructors. This example is very similar to the previous example, but the difference is that the first constructor calls the second constructor calls the third constructor, and then the third constructor actually initializes the instance variables. In other words, the third constructor does all the work. Now that we've done this, no matter what constructor we call, the variables will always be initialized in the third constructor and only there. This is known as constructor chaining, and what we're doing is making sure the last constructor has the responsibility to initialize the variables. Alright, so looking at both examples on screen now. On the left-hand side again, this is the bad example of constructors. And on the right-hand side, we've got the good example. Again, the problem with the left-hand side is the duplicated code. So as you can see, all three constructors on the left-hand side are initializing the variables. Now contrast that to the solution on the right-hand side. We've got one constructor that initializes variables, and the other constructors are just calling each other. Ultimately, we end up in the third constructor. And that's again called constructor chaining. With that constructor chaining, we can, and do, avoid code duplication. And by the way, duplicated code can lead to many bugs and a lot more work on your behalf. It's also bad practice, as a rule, to write duplicate code, which of course we did in the bad example. Alright, let's have a quick look at the supercall example. In this example, we have a class shape with x and y variables, instance variables, and a class rectangle that extends shape with variables width and height. In the rectangle class, the first constructor is calling the second constructor. Now the second constructor calls the parent constructor with parameters x and y. Now the parent constructor will initialize the x and y variables, while the second rectangle constructor will initialize the width and height variables. Here, as you can see in this code, we have both the super and this calls, but in different constructors. Now you may want to watch this video a few times, or you may also want to then continue through to the rest of this section and then come back to this one to see if that actually makes sense. It's very important as a Java developer to understand the differences with these calls to be able to use them properly. Alright, so let's move on now to the next video. This video is specifically about method overriding versus overloading. Let's review the main differences between method overriding and method overloading. Method overloading means providing two or more separate methods in a class with the same name but different parameters. Now the method return type may or may not be different, and that allows us to reuse the same method name. Overloading is very handy because it reduces duplicated code and we don't have to remember multiple method names. We can overload static or instance methods. To the code calling an overloaded method, it looks like a single method can be called with different sets of arguments. In actuality, each call that's made with a different set of arguments is calling a separate method. Java developers often refer to method overloading as compile-time polymorphism. This means the compiler is determining the right method to call based on the method name and argument list. Now, usually overloading happens within a single class, but methods can also be overloaded by subclasses. That's because a subclass inherits one version of the method from the parent class, and then the subclass can have another overloaded version of that method. There are some rules about method overloading. Methods will be considered overloaded if both methods follow the following rules. Methods must have the same method name, and methods must have different parameters. Now, if methods follow the rules above, they may or may not have different return types. They may or may not have different access modifiers. They may or may not throw different checked or unchecked exceptions. Okay, so that was method overloading. Let's discuss a little bit more now about method overriding. Method overriding, well, that means defining a method in a child class that already exists in the parent class with the same signature, in other words, the same name and same arguments. By extending the parent class, the child class gets all the methods defined in the parent class, and those methods are also known as derived methods. Method overriding is also known as runtime polymorphism or dynamic method dispatch because the method that is going to be called is decided at runtime by the Java virtual machine. When we override a method, it's recommended to put an override immediately above the method definition. The override statement is not required, but it's a way to get the compiler to flag an error if you don't actually properly override this method. We'll get an error if we don't follow the overriding rules correctly for that method. This is officially called an annotation, which we'll be discussing later in the course. We can't override static methods, only instance methods can be overridden. Some rules about method overriding. A method will be considered overridden if we follow these rules. Firstly, it must have the same name and same arguments. The return type can be a subclass of the return type in the parent class. It can't have a low access modifier. In other words, it can't have more restrictive access privileges. For example, if the parent's method is protected, then using private in the child's overridden method is not allowed. However, using public for the child's method would be allowed in this example. Now there's also some important points about method overriding to keep in mind. Firstly, only inherited methods can be overridden. In other words, methods can be overridden only in child classes. Constructors and private methods cannot be overridden. And methods that are final also cannot be overridden. Now a subclass can use super.method name to call the superclass version of an overridden method. Let's see an example now of method overloading and method overriding. On the left, we've got a simple overriding example. As you can see, we've got two classes, dog and German Shepherd. Now the class German Shepherd extends dog and overrides the method bark. As you can see with overriding, we've got the same name and same parameters for the method. In this case specifically, we don't have any parameters, but they would need to be the same in the case of overriding. On the right-hand side, you can see a simple example with method overloading. Here we've got the class dog with two methods that have the same name, bark, but in this case they've got different parameters. The second bark method has an int parameter, while the first method doesn't have any parameters. Hopefully, now you can easily see the difference between overriding and overloading when comparing these two examples side by side. Let's recap now the most important rules about overloading and overriding methods. In the following table, you can see the main differences between overloading and overriding. Now, some points, like checked exceptions, are probably still unknown. We'll cover exceptions in greater detail later in the course. On the left-hand side, we've got overloading, and on the right-hand side, we've got method overriding. Now, with method overloading, we've got functionality to reuse the method name with different parameters. Overloading usually happens in a single class. However, it can be used in a child class because the child class inherits methods from the parent class. Now with overloading methods, they must have different parameters. But they might have different return types, access modifiers, or even different exceptions. With overriding, we're reusing behavior which the class has inherited from the parent class. Overriding can be in the child class or grandchild class. It's always in two classes that have it as a relationship. Methods that are overridden must have the same parameters in the same order, and they must have the same return type or covariant return type. I'll come back to this point in just a minute. Overridden methods can't have a more restrictive, what I call a lower, modifier. So in other words, if the parent method is protected, then the child method can't be private. The Java compiler calls this assigning weaker access privileges. But it could have a higher modifier or greater access privileges, so in this scenario, since the parent method is protected, the child method could be public. We'll talk more about this in more detail when we explore the concept of polymorphism in the next section of the course. Let's get back to the covariant return type. The return type of an overridden method can be the same type as the parent method's declaration. That's easy to understand, but it can also be a subclass. Why didn't we just say return type could be the same class or a subclass? Well, later we'll be dealing with other types that aren't classes, and so the term covariant return type is more appropriate, and that's why we use it in this list of rules. The term covariant type can include types such as interfaces and generic types. But at this juncture, we'll just simply look at a base class and its subclass to demonstrate what this looks like. We briefly mentioned in a previous video that there's a clone method on the class object that all classes inherit from. A simplified look at this declaration for our purposes is shown below. And if you override this method by using IntelliJ's code generation tools, it will generate this code in your class. But in general, when you're cloning an instance, you're going to want to return an object that's the same type as the object you are cloning. Remember, we said all classes ultimately have object as a base class, so every class can be said to be a covariant of object. Let's see what a clone method would look like for a person class. Here, we show the generated override on the left for comparison. On the right, we have the clone method implemented on a person class. We've omitted the throws clause declaration, which is valid to do for an override, and also notice that we're declaring that the return type is a person, not an object. Person is a valid covariant return type for object, so this clone method in the person class is a valid overriding method, overriding object's clone method. Notice also we made the access modifier public on the method in person, though object declared it as protected. It's valid to go in this direction, meaning allowing the overriding method to have more access or be less restrictive. Alright, so hopefully that'll now make sense about covariant return types, and that's giving you a good recap of method overloading versus method overriding. I'll see you in the next video. We're going to talk about a fairly new feature, the text block, as well as other ways to format output. In the last videos, we've covered a lot of topics with classes and objects. In the next couple of videos, I want to revisit strings because they're so intrinsic to Java, it's important to talk about them a bit more. But before we do that, let's take a look at a fairly new feature in Java, the text block. The text block is just a special format for multi-line string literals. It's simply a string with a new representation in the source code. It became part of the official languages of JDK15. Let's look at it next in some code. I've created a project called string formatting with the usual main class and main method. To start with, let's look at an example in code that uses the pre-JDK15 way of handling multiple lines of text. String bulleted equals double quotes print a bulleted list colon plus double quotes backslash u2022 first point plus double quotes backslash u2022 subpoint semicolon. System.out.println opening parentheses bulleted closing parentheses semicolon. Okay, so this code is using the concatenation operator, the plus sign, to add several strings together. And we're using the Unicode character backslash u2022 to include a bullet point character on these two lines. And if we print that out, we get a single line of text, print a bulleted list, first point and subpoint. That's not what I really wanted because I wanted some formatting and these strings on multiple lines. I can do this with some special combinations of characters called escape sequences. An escape sequence starts with a backslash. Java has several, but the most common ones, the ones you're most likely to use, are shown on this slide. These can insert a tab, a new line, a double quote character, or a backslash character if you need it in your text. Let's add some of these characters to our multi-line string in this code. We'll add some new lines after each of the first two lines, and we'll also add some tabs before the bulleted points. We want one tab before the first bullet point and two tabs before the second bullet point. And although that code is pretty ugly, if we run it, we get a formatted bulleted list. That looks pretty good. Now let's use a text block to reproduce this output. String text block equals triple quotes. Print a bulleted list colon backslash U2022 first point. Backslash U2022 sub point triple quotes semicolon. System.out.println opening parentheses text block closing parentheses semicolon. You can see right at the start we're creating a string variable and assigning it something. This something is the new format called a text block for creating a multi-line formatted string. You'll notice that we start with 3 double quotes there. This is required and they must be on their own line. The text that follows is the text that's part of the string. And we end with another 3 quotes which close or complete the text block. Everything between the 2 sets of triple quotes is the text block itself, and you can see we didn't include any additional quotes or plus signs. And we also got rid of the tab and new line escape sequences. The text block lets us format text in the source code the same way we want to see it in the output. Let's run this and see what we get. You can see we get the exact same output as we did when we concatenated several strings and used escape sequences. That's really it. The text block makes outputting many lines of text using indents and new lines a lot easier, as I hope you can see. We've looked at formatting text over multiple lines in 2 different ways. Next, let's look at formatting numbers in text that will output. There are several ways to do this. Up until now, we've used system.out.println and system.out.print, but there are 2 other methods we haven't yet discussed. These are system.out.printf and system.out.format. These methods behave the same, so for our examples, we'll just use system.out.printf, but be aware you can change printf to format with the same results. Let's start with a simple example, then we'll explain how this works. Int age equals 35 semicolon. System.out.printf opening parentheses double quotes your age is %d, comma, age closing parentheses semicolon. You'll notice we're using printf in place of print or println on system.out. Printf is like print in that it doesn't end with a new line character. But this method has multiple arguments. The first is a string which will be printed to the console, and the following arguments are values that will be used in the string. First, you'll notice our string contains %d in it. This is a special indicator called a format specifier. This is a placeholder for other data which should replace this specifier in the text. In this example, we are going to replace %d with age, and that's why we pass age as the second argument to this method. Now running this code, we see we get the output, your age is 35. Let's try another example. This time, we'll pass age and year of birth, which we'll try to calculate using the year 2023 as the current year. Before we do that, we'll first add an escape sequence in the first string so we have a new line printed between statements. Int year of birth equals 2023 minus age semicolon. System.out.printf opening parentheses double quotes age equals %d, comma, birth year equals %d, comma, age, comma, year of birth, closing parentheses, semicolon. In this last statement, we have 2 instances of %d, so we should pass 2 arguments, age and year of birth. And running that, we see the result. Your age is 35, which means your birth year is approximately 1988. Let's take a moment and look more closely at this format specifier %d. At their most complex, format specifiers take the form shown here. They start with a % and end with a conversion symbol and have lots of options in between. We've looked at one conversion type, D, which is the symbol used for a decimal integer value. Let's go to Java's API documentation for a class called formatter, which is the basis for many of the formatting methods we'll be talking about. Okay, so if we scroll down, we can see the conversion symbols shown in this table. The ones you'll be using the most are those for the two different numeric types, D and F. D formats a decimal integer, as we've said, and would be used for any of Java's whole number primitive types, like short, int, and long. F formats a decimal number, so it can be used for floating point numbers, a double, or float. But you can see there are many others for different types of numbers, dates, and time, as well as general specifiers. And look at the last one, the letter N, called the line separator, so this would print a new line character. The difference between the escape sequence, \n, and this format specifier, %n, is that %n outputs the platform-specific line separator, so it's preferred. You can find the URL to this documentation in the resources section of this video. Okay, so let's get back to the code. From that documentation, we learnt that we can replace our escape sequence, \n, with a format specifier, %n, so let's do that in our current code. And we'll also add it to the end of our second statement. Now, let's see what happens if we replace %d with %f. We'll copy the first system.out.printf line, which prints out age only, and paste it, and we'll replace d with f. This compiles, but if we run it, we get an exception, illegal format conversion exception. This is because it was expecting a float or double, and we passed an integer. Let's actually cast age to a float then. Now the code runs, and look at the output. We see age is printed with a decimal point and 6 zeros following it. This is the default format for the floating point number specifier. What's nice about using this method, actually the reason it exists, is we can configure the specifier so that we can output this number in any way we want. Let's say we want 2 decimal places and not 6. We do this by specifying the number of decimal places, called precision, between the % and the conversion symbol, f. We add the decimal and then 2, and that tells the formatter we only want 2 decimal places for the number printed. Now running this, we get 35.00. We've set the precision to 2 decimal points, in other words. Okay, so that's how we specify precision, but now let's consider formatting the width of numbers, which is a separate option. Let's create a quick loop that'll print out a series of numbers. For, opening parentheses, int I equals 1, semicolon, I less than or equal to 100,000, semicolon, I star equals 10, closing parentheses, opening curly brace. System.out.printf, opening parentheses, double quotes, printing %d %n, comma, I closing parentheses, semicolon, closing curly brace. This loop just prints out numbers, multiplying by 10 each time. And running that, we get output for 6 numbers on through 100,000. What's important to notice are the numbers are all aligned on the left. We can change this by specifying the width of the number in the specifier. First, we'll set a width for the number. Our largest number in the output is 100,000, so let's make the width 6, so we'll add 6 in the specifier. And running that now, we get the numbers aligned on the right because we said each number will fill up 6 spaces. Those are some of the most common things you do with formatting. We use system.out.printf, and remember system.out.format can be used anywhere system.out.printf is used. But there will be times you want to format strings and output them to a file or error log, for example, or maybe to a database. The string class itself has 2 methods to support this type of formatting as well. One is a static method called format. Let's see what that one looks like in code. String, formatted string, equals string.format, opening parentheses, double quotes, your age is %d, comma, age, closing parentheses, semicolon. System.out.println, opening parentheses, formatted string, closing parentheses, semicolon. Here, we're creating a string variable and assigning it the output of the call to string.format, a static method. Like system.out.printf, this method has a string as its first argument, followed by arguments that match the specifiers in the string. And running that, we get the same as before, your age is 35. And we could also have done that with the string instance method formatted. This method was included in JDK 15, and it works the same as string.format, except you don't need to pass the format string as an argument. The string itself is the format string. Let's code that one next. Formatted string equals double quotes, your age is %d dot formatted, opening parentheses, age, closing parentheses, semicolon. System.out.println, opening parentheses, formatted string, closing parentheses, semicolon. When you use this method, you just pass the arguments that match the specifiers in the current string, and the result is a formatted string. Running this output gives us the same output as before. Okay, so those are some of your formatting options. There was a time when some of these formatting options were much slower than simply using the concatenate operator, the plus sign. But Java continues to make performance enhancements on these methods. The argument for using them is that they make the code easier to read and maintain, and you have many options for outputting different specifier types. In this video, we've shown you the text block, system.out.printf method, and 2 formatting methods on string. In the next video, we'll review more methods on string. I'll see you in that next video. In the previous video, we looked at 2 of string's methods for formatting. We've also briefly looked at a few more obvious string methods in some of the sample code we've shown to date. The string has over 60 methods available. We won't cover them all here, but we'll cover the ones you'll probably use the most. The string is a sequence of characters, meaning its characters are ordered and indexed. The index starts at 0 and not 1. This is important to know if you're going to operate on strings successfully. In the table below, we show the indices above each character for the string hello world. We can say the character, H, is at index 0 and a W is at index 6. The length of this string is 11, but its last index is 10. We can split strings methods up into 3 basic categories. String inspection methods. These provide some information about the string with methods like length, is empty, and is blank. Methods for comparing string values. These usually return a Boolean value, string values are equal or not. String manipulation methods. These transform one string value into another. Let's start with a look at some of the string inspection methods. We have some methods that tell us about the string value. The method length tells us the number of characters in a sequence. The method chart will return a character if we specify an index position. There are 2 methods, index of and last index of, that can tell us if the string value contains a specified character or substring. The methods is empty and is blank tell us whether the sequence is empty or contains just white space characters. I've created a project called All About Strings with the usual main class and main method. Let's start with another method that will print some string information using a couple of the inspection methods. Public, static, void, print information, opening parentheses, string, string, closing parentheses, opening curly brace. Int length equals string.length, opening and closing parentheses, semicolon. System.out.printf, opening parentheses, double quotes, length equals %d%n, comma, length, closing parentheses, semicolon. System.out.printf, opening parentheses, double quotes, first char equals %c%n, comma, string.char, opening parentheses, 0, close both parentheses, semicolon. Closing curly brace. First, with this code, we're creating a variable called length and setting it to the length method. Then we print that out using printf to reinforce what we learnt in the last video. We also want to print the first character, and for this, we use the method chart and pass it 0, which gets the first character in the string. And here, notice this additional specifier we're using, %c. We haven't used this before, but it just prints a single character. Let's call this method from the main method and we'll pass it hello world. Print information, opening parentheses, double quotes, hello world, closing parentheses, semicolon. And now if we run that, we see the length of the string is 11 and the first character of the string is H. Let's add some more functionality to the print information method and now get the last character. For character sequences in Java, the position starts with 0 and the last character is 1 less than the string length. Let's add that code. System.out.printf, opening parentheses, double quotes, last char equals %c%n, comma, string.char, opening parentheses, length, -1, close both parentheses, semicolon. And running that, we get last char as D. You can use the method char with any index from 0 to the length -1 to retrieve the character at that index. Passing any other index that's not valid will cause a runtime exception when the code runs. Now, let's look at the difference between is empty and is blank next. First of all, if a string is empty, its length will be 0. We don't want to pass a bad index to the char method, so if the string is empty, we'll return from the method before those statements. Let's add that code. If opening parentheses, string.isEmpty, opening and closing parentheses, opening curly brace. System.out.println, opening parentheses, double quotes, string is empty, closing parentheses, semicolon. Return, semicolon, closing curly brace. Let's test an empty string by calling this from the main method. Print information, opening parentheses, double quotes, closing parentheses, semicolon. And running that, we see the last two lines that length is 0 and that string is empty. But if the string is blank, this means there are still characters, but they're just white space characters like tabs, new lines, spaces, etc. We can still check the length and use the char method for the first and last character, so we won't return from the method in this if statement. If opening parentheses, string.isBlank, opening and closing parentheses, opening curly brace. System.out.println, opening parentheses, double quotes, string is blank, closing parentheses, semicolon, closing curly brace. Now we'll add another call to our print method in the main method. Print information, opening parentheses, double quotes, \t\n, closing parentheses, semicolon. And when we run that, we can see there are 5 characters in the string where isBlank was true, and the first and last characters are white space of some sort. That's the difference between isEmpty and isBlank. Now lastly, let's talk about the index of and last index of methods. First, these methods have several overloaded varieties. You can search for a single character or a string. Let's look for the letter R in the hello world string. String hello world equals double quotes hello world semicolon. System.out.printf, opening parentheses, double quotes, index of R equals %d%n, comma, hello world.index of, opening parentheses, single quotes, R, close both parentheses, semicolon. And running this, we see we get index of R equals 8. Now, let's call that same method, but this time we'll search for a string and not just a letter. Let's also look for the string world in hello world. We'll copy that last statement and paste a copy below. We'll change the letter R to world in the label. And we'll change the character R to the string world in the call to the method. And running that, we get index of world equals 6. Hopefully, there's no surprises with those 2 overloaded versions. What happens if we use this method with the letter L? Again, let's copy the statement that searches for the letter R and paste that. And we'll change the label from R to L. We'll also change the argument of the method from R to L. And now let's copy and paste the statement we just created. This time we'll change the method name to last index of. And running that, we get index is 2 for the first call, but index is 9 for the next one. The first method, index of, gave us the position of the first L in hello world. And the second method, last index of, gave us the position of the last L in hello world. That's the difference between those two methods. But what if we want to get the position of the second L? How would we do that? Well, both of these methods each have a second parameter, an integer. Passing this argument tells the code where to start searching for a match. We found the first L at position 2. If we wanted to start looking for the next L, we'd start looking after that at index 3. We can pass 3 as the second argument to the index of method. And we can do something similar with the last index of method. We said the last L was at index 9, and since this method searches forward for the character and not backwards, we'll use 8 as the second argument. Let's copy both of those previous statements and paste copies and add 3 as the second argument in the first method call. And in the second method call, we'll add 8 as the second argument for the last index of method. If we now run this, both of these calls find the second L in the string using different methods. The index of method found it looking forward, starting at index 3 and searching towards the end of the string. The last index of method found it looking backwards, starting from index 8 and searching towards the beginning of the string. Okay, we've covered what I call the string inspection methods. Now let's look at the next set, the string comparison methods. Some of the string comparison methods will check for equality of the string values like equals, equals ignore case, and content equals. Others test whether a substring is part of a string value like the contains method as well as the ends with and starts with methods. The region matches methods also do this, but it lets you specify regions of the strings to test for matches. There are 2 others that fit into this category, but not shown on this slide because we'll be talking about the compare to and the matches methods later in the course for more advanced topics in the context of sorting and using regular expressions. Most of these methods are pretty straightforward. Let's create a variable called hello world lower and assign that to the result of the toLowerCase method from the hello world variable. Then we'll use the equals method and test if hello world equals hello world lower. String hello world lower equals hello world.toLowerCase opening and closing parentheses semicolon. If opening parentheses hello world.equals opening parentheses hello world lower close both parentheses opening curly brace. System.out.println opening parentheses double quotes values match exactly closing parentheses semicolon closing curly brace. And let's copy and paste that if statement. We'll change equals to equals ignore case and change our output slightly. And if we run that, hopefully there are no surprises here. We don't get any output from the first if statement because the cases of the text values aren't equal. But we do get output from the second if statement that the string values match if we do ignore case. Let's quickly look at a couple of the others. We'll add a test using the starts with method. If opening parentheses hello world.starts with opening parentheses double quotes hello close both parentheses opening curly brace. System.out.println opening parentheses double quotes string starts with hello closing parentheses semicolon closing curly brace. And next we'll copy and paste that to test the ends with method, changing the method name to ends with and passing world as the argument. We'll also change our message slightly to string ends with world. And lastly, let's just also include a test of the contains method. Again, we'll copy and paste the previous code, the if statement with the ends with method. And we'll change the method from ends with to contains. And we'll change the message to say string contains world. Okay, so we have 3 new tests, and running this code shows us the results we'd expect. String starts with hello, string ends with world, and string contains world. Okay, so there's one more we haven't yet tested, and that's content equals. We can copy the equals if statement from above and paste it after these other tests. We'll change the method from equals to content equals. This time we'll test the string literal so that the argument equals the value in the variable, so we'll make the argument hello world. And if we run that, You can see that the values match exactly. You might be wondering why Java has both the equals method and the content equals method. The content equals method isn't limited to just comparing string objects. It can be used to compare a string builder's value, which the equals method doesn't support. We'll talk about this more when we look at string builder. We've covered string comparison and string inspection methods. Let's end this video here, and in the next video, we'll cover our final category of methods, which I'm calling the string manipulation methods.
It's break time. Do you like this video? Don't forget to subscribe to get new videos. Share this video to open new premium videos and ebooks. We'll be a star freelancer.
In the last video, we covered some string basics, inspecting string values and comparing strings. Okay, so now we'll move on to the string manipulation methods, which I've split into two groups as well. The first set of methods don't actually change the underlying meaning of the text value, but perform some kind of cleanup. For example, the methods remove unnecessary white space, or they change the case of the text, or they add or remove white space for indenting purposes. We have methods named indent, strip, trim, to lowercase, and to uppercase. The second set of string manipulation methods transform the string value in some way and return a string with a different meaning than the original string. These include methods for creating strings from other strings with such methods as concat, join, and repeat. There are methods to replace characters in the string or replace some parts of the text with a different set of characters with replace, replace first, and replace all. And lastly, we have methods to get parts of the string value with the substring and subsequence methods. Let's create a new class in this same project, all about strings, and we'll call it string methods. We'll add a main method to this class by typing in the shortcut PSVM. And now let's get going by reviewing a method we looked at briefly in a previous challenge, the substring method. Let's type this out, then we'll talk about it. String birth date equals double quotes the 25th of November 1982 semicolon. Int starting index equals birthdate.index of opening parentheses double quotes 1982 closing parentheses semicolon. System.out.println opening parentheses double quotes starting index equals plus starting index closing parentheses semicolon. System.out.println opening parentheses double quotes birth year equals plus birthdate.substring opening parentheses starting index close both parentheses semicolon. Okay, so here we have a birth date as a string. Java has classes for dealing with dates, but for now we'll make this date a string to explore some of the string methods. And next, we call the index of method we talked about, passing the string 1982. This will tell us where, in the string, the year 1982 can be found. We print that out, then we print out the birth year, which was extracted from the birth date variable with the substring method using that index we just got. Now running that code, we see that the start index was 6, meaning the string 1982 was found starting at index 6 in the sequence of characters. And we were able to extract the year from the birth date variable successfully, birth year equals 1982. The substring method that has one argument will retrieve a string starting at the index passed and retrieving the remaining string. But the method substring has an overloaded version that takes an ending index as well, which will get the string starting at the specified start position. Instead of returning the rest of the string, this version of substring returns the part of the string up to but not including the character at the end position we specify. Okay, let's extract the month from this date, which is in the format DD for day, for month, and YYYY for year. For this date string, the month is starting at position 3 if we start counting at 0. And because we only want 2 characters in the result, we need to use 5 as the second argument to this method. This method will get the characters starting at index 3 and include the characters up to but excluding index 5. In other words, it gets the characters at position 3 and 4. System.out.println opening parentheses double quotes month equals plus birthdate.substring opening parentheses 3 comma, 5, close both parentheses, semicolon. And the result of that is that month equals 11. That's substring, which you'll most likely be using a lot. Let's look at another very useful method, and that's join, a static method on string. This joins a series of strings together with some delimiter. In fact, we can build a date string here using this method. String new date equals string.join, opening parentheses, double quotes, forward slash, comma, double quotes, 25, comma, double quotes, 11, comma, double quotes, 1982, closing parentheses, semicolon. System.out.println, opening parentheses, double quotes, new date equals plus new date, closing parentheses, semicolon. And if we run that, you see we build a date string with the same date as before using this method. This is a good method to use if you ever need to create a comma delimited string as an example. That's a useful method, but we could also do this using the concat method. It would be a little tedious, but let's do it. New date equals double quotes 25 semicolon. New date equals new date.concat opening parentheses double quotes forward slash closing parentheses semicolon. New date equals new date.concat opening parentheses double quotes 11 closing parentheses semicolon. New date equals new date.concat opening parentheses double quotes forward slash closing parentheses semicolon. New date equals new date.concat opening parentheses double quotes 1982 closing parentheses semicolon. System.out.println opening parentheses double quotes new date equals plus new date closing parentheses semicolon. First of all, let me discourage you from writing code like this. Although it's perfectly valid, it's pretty inefficient. Each call is a new creation of a string object. But if we run this, we get the same result as we got with join. The concat method does what the plus operator does when used with strings, but actually less efficiently when it's used with string literals. There are two other ways to write this code. Let's look at the first, which is just using the plus operator on a bunch of string literals. New date equals double quotes 25 plus double quotes forward slash plus double quotes 11 plus double quotes forward slash plus double quotes 1982 semicolon. System.out.println opening parentheses double quotes new date equals plus new date closing parentheses semicolon. Again, it's unlikely you'd write code like this, but it's more efficient than the previous code. This is because Java's compiler recognizes this statement as a single string because of the use of literals and the plus operator. The full string, in other words the full date string, will be used in the generated by code. And let's look at another way to do this. New date equals double quotes 25.concat opening parentheses double quotes forward slash closing parentheses .concat opening parentheses double quotes 11 closing parentheses .concat opening parentheses double quotes forward slash closing parentheses .concat opening parentheses double quotes 1982 closing parentheses semicolon. System.out.println opening parentheses double quotes new date equals plus new date closing parentheses semicolon. What about this code? This coding style has a special name and it's called method chaining. You can write string methods this way because they return strings. But again, this is just like writing the concat statements, each on its own line. Each call to the concat method is still a new string object being created, but instead of assigning that result to a variable, we chain it to another method result. Okay, so that was the concat method. We'll be talking about a better class for this kind of work a bit later, meaning stringing a lot of text together, and that class is the string builder. Another very common string method is to replace a character or a part of the text with some other character or string. Let's quickly look at the replace string varieties we have. At first, we use the replace method with single characters, and we'll replace the / with a simple dash. System.out.println, opening parentheses, new date.replace, opening parentheses, single quotes, / comma, single quotes, minus, closed both parentheses, semicolon. And running that, you can see it replaces every / with a dash. Let's copy and paste that last line. This time we'll change the arguments to strings. You can use a single character as a string, so I'll do that with the number 2. But we can replace every instance of 2 with an actual string, not just another character, so here we'll replace 2 with 2 zeros. And you can see the output from running that, we get every 2 replaced by 2 sets of zeros. So let's look at 2 more replace methods. We'll copy and paste the last statement and change the name to replace first. And we'll again swap the / with a dash, but this time notice these are string values and not character literals. And paste that statement again and change the method to replace all. This time we'll replace a / with 3 dashes. Let's run this code. You can see the replace first method just replaces the first instance where there's a match, so only the first / was replaced with a dash. In contrast, the replace all method replaced all occurrences. There's another important difference between these 2 methods and the replace method. The first argument for these last 2 methods is really a regular expression string, which is a special syntax that looks for patterns in a string. We'll look at regular expressions later in the course, but in general, you can use replace first with basic strings to replace the first instance. But if you want to replace all occurrences of one string with another, use the replace method rather than the replace all method. Okay, so lastly, I want to talk about 2 more methods, repeat added in JDK 11 and indent added in JDK 15. Let's first look at using repeat to create a multi-line string with the escape sequence \n. System.out.println, opening parentheses, double quotes, abc \n dot repeat, opening parentheses, 3, close both parentheses, semicolon. System.out.println, opening parentheses, double quotes, minus dot repeat, opening parentheses, 20, close both parentheses, semicolon. The second statement was added, so the output will be easier to compare, so let's just run this. And you can see from the output that the repeat code produced 3 lines, all having ABC in them, plus an empty line in the first case, and a separating line of dashes in the second case. That's the repeat method, but now let's use it to help us understand what we can do with the indent method. Let's copy and paste those last 2 lines. This time, we'll chain the indent method to that repeat method. And we'll pass 8 to the indent method, meaning we want 8 spaces at the start of every line. And let's run this. And you can see the output. Compared to the previous output, every line of text in this string was indented by 8 spaces. And this method, the indent method, can also be used to remove some leading spaces, so let's try that next. Again, we'll copy and paste the previous 2 lines. This time, we'll insert 4 spaces before the ABC string before we actually repeat it. And then we'll chain the indent method, but this time we'll use a negative number, -2. And running that, you can see that the multiple line string was now outputted with 4 spaces, which we had in the first string, but only 2 spaces at the start of each line. Using indent with a negative number is a way to remove spaces from each line in a multi-line text value. This was a bit of a contrived example, but I hope you can see how indent would work with text blocks or strings with multiple lines. That was a pretty fast review of many of the most commonly used methods on string. But hopefully you got a lot out of that. We'll be using strings a lot, and you'll see these methods time and again as we progress through the course. In the next video, we'll be talking about another class that works with character sequences or text values, and that's the string builder. I'll see you in that next video. In the last video, we talked about the string and many of its methods. Because string is immutable, each method call returns a new instance of a string. As an alternative, Java provides a mutable class that lets us change its text value or character sequence. This is the string builder class. We've already talked about creating strings, and the preferred way, the most efficient way, is simply to assign a literal or concatenated literals to a variable. We show this on the left of this slide. Let's compare that to the string builder, which has 4 overloaded constructors. These are shown on the right side of this slide. There are 4 ways to create a new string builder object using the new keyword: pass a string, pass no arguments at all, pass an integer value, pass some other type of character sequence like string builder. Getting back to the code, let's compare the string and string builder classes a bit. I'm starting out with a string options project with the usual main class and main method. First, we'll create a couple of overloaded methods, one that will take a string and the other will take a string builder. Both of these will print the argument that's passed, and both will call the length method, which is a method on both string and string builder. Public, static, void, print information, opening parentheses, string, string, closing parentheses, opening curly brace. System.out.println, opening parentheses, double quotes, string equals, plus, string, closing parentheses, semicolon. System.out.println, opening parentheses, double quotes, length equals, plus, string.length, opening and closing parentheses, semicolon. Closing curly brace. Here, we're printing out the string and the length of the string passed as the argument. Next, we copy this method and paste it. We'll change the parameter type and name, changing string to string builder and the string parameter name to builder. We have to change that in both statements in the method as well. And that all compiles. So now, in the main method, let's create some objects. String hello world equals double quotes hello plus double quotes world semicolon. String builder hello world builder equals double quotes hello plus double quotes world semicolon. What I wanted to show you with this code, this second statement doesn't compile. This is an important difference between the string and the string builder. You can't assign a string literal to a string builder variable. We have to use one of the constructors, so let's do that. We'll remove that assignment to hello plus world. Instead, we'll create a new string builder and pass hello plus world to the constructor. We've created 2 types of objects which have the same set of characters in them. Let's make a call to our print information methods for each of these objects. Print information, opening parentheses, hello world, closing parentheses, semicolon. Print information, opening parentheses, hello world builder, closing parentheses, semicolon. And if we run that, we see that the sequences have the same length as you'd expect since the values are the same. Okay, so now let's examine what we mean when we say the string builder's text value is mutable but the string's isn't. First, we use the concat method on string, which is a lot like using the plus operator on string. The result is a new string object with the argument value concatenated to the existing text. For string builder, a similar method is called append, so we'll use that. Hello world.concat, opening parentheses, double quotes, and goodbye, closing parentheses, semicolon. Hello world builder.append, opening parentheses, double quotes, and goodbye, closing parentheses, semicolon. And running the code now, look carefully at the results. String is still hello world, but string builder is hello world and goodbye, and its length has increased. Let's talk about what happened by looking at a quick slide. When we passed the string literal and goodbye to the concat method, this created an object in memory for that literal and goodbye. It also created the result of the concat method, the object, the string, that has the value hello world and goodbye. But our code has a mistake in it because we didn't assign the result of the method, the concat method, to a variable. This is actually a common mistake to make. It's important to remember to assign the result of any string manipulation method you call on a string to a variable. These methods don't change the internals of the existing string object, as we show here. The string referenced by the hello world variable never changed. Instead, a new string was created by the method call. Now let's compare that to what happened with the string builder. On this slide, I show strings and string builders in different colors with the string builder object in green. We still have the objects in memory that represent the string literals that were passed to the string builder, in this case hello world. But you can see that after the call to the append method, we still only have one string builder object. The variable hello world builder is still referencing the same object, but the value of that object changed. This is important because it means the character sequence in the string builder changed. And this time, we didn't have to assign the result to another variable to access the result. String methods create a new object in memory and return a reference to this new object. String builder methods also return a string builder reference, but it's really a self-reference or a reference to the same object. Unlike strings, we can call methods on string builder without the need to assign the results to intermediate variables, as we saw with strings. String builder methods return this self-reference to support chaining methods together. Okay, so getting back to the code. In the main method, we'll create two more string builder instances. This time, we'll make them both start out with empty character sequences. In other words, they won't contain any characters or any text. And we'll call our print information method for string builder for both. String builder empty start equals new string builder opening and closing parentheses semicolon. String builder empty start 32 equals new string builder opening parentheses 32 closing parentheses semicolon. Print information opening parentheses empty start closing parentheses semicolon. Print information opening parentheses empty start 32 closing parentheses semicolon. In the first case, we don't pass any arguments in the constructor, but in the second, we're passing a number 32. Let's run this and see what we get. In both cases, we have empty strings as the value of the string builder sequence and length is 0. Okay, what's the difference here? Before we talk about that, let's change our information method and add a call to another method on string builder, a method named capacity. System.out.println opening parentheses double quotes capacity equals plus builder.capacity opening and closing parentheses semicolon. We'll run this code, then we'll talk about it. A string builder is mutable, which means it can shrink or grow in size. By default, an empty string builder starts out with a capacity of 16, meaning it can contain up to 16 characters before it needs to request more memory. In the second example, we created a string builder with a starting capacity of 32, which means our sequence can grow up to 32 characters without needing to request additional allocation. Every time a string builder needs to increase capacity, the data stored in the original storage needs to get copied over to the larger storage area. Let's see this in action. Let's append some text to our two empty string builder objects. Empty start.append opening parentheses double quotes a .repeat opening parentheses 17 close both parentheses semicolon. Empty start 32.append opening parentheses double quotes a .repeat opening parentheses 17 close both parentheses semicolon. Here we're using the repeat method, which we introduced you to in the last video. So this creates a 17 character string filled with A's. For the first string builder object, which has a capacity of 16, this is going to require a request for a larger memory area to store the extra data. Let's run this. First, look at the value in the string builder objects. Both contain a string of A's and both have a length of 17 as expected. But in the first case, the capacity is now 34 when we started out with 16. The new allocation size is determined by the JVM. In the second case, the capacity is still 32 because we didn't require a reallocation since the appended string still fit in the original capacity. What happens if we change our code in the first instance to something bigger than 34 characters, which we saw was the next allocation step? Let's change our first call to repeat to create a string of 57 characters. Now, the output shows that the capacity of the first empty string builder is actually the same size as the string we passed in, 57. At this stage, it's not that important that you understand how the next capacity is determined. But it is important to understand that the capacity does need to adjust as the text in your string builder grows. If you know you plan to house a large text value in your string builder object, start out with a larger capacity. The string builder class has many similar methods to strings, but it also has methods to remove and insert characters or strings and truncate its size. This slide shows some of these methods. Delete and delete chart will remove text or a character from the string builder's text. The insert method inserts text into the string builder text at the specified index. Reverse reverses the characters in the sequence. And setLength is a way to truncate a string builder's text value. Let's just look at some of these methods next in our code. Firstly, we'll copy and paste this code from above, changing the variable name to builder plus. Then we'll delete a character, the capital G. And while we're at it, we'll insert a lowercase g where the uppercase G used to be. Builder plus.delete chart, opening parentheses, 16, closing parentheses, dot insert, opening parentheses, 16, comma, single quotes, G, closing parentheses, semicolon. System.out.println, opening parentheses, builder plus, closing parentheses, semicolon. We're chaining methods here again, this time with the string builder object. And running the code. The output shows that it looks like we've just replaced a big G with a little g. But we did it by first using the delete chart method and then the insert method. The string builder class does also have a replace method which requires a start and end index to identify what will be replaced, which is different than the replace method for string. Let's set that G back to a big G using the string builder replace method. Builder plus.replace, opening parentheses, 16, comma, 17, comma, double quotes, G, closing parentheses, semicolon. System.out.println, opening parentheses, builder plus, closing parentheses, semicolon. Again, the ending index we use with this method is used as an exclusive index, so this code simply replaces a single character, the letter lowercase g. And lastly, let's look at the reverse method and the setLength method, and we'll chain them together. Builder plus.reverse, opening and closing parentheses, dot setLength, opening parentheses, 7, closing parentheses, semicolon. System.out.println, opening parentheses, builder plus, closing parentheses, semicolon. The reverse method will reverse all the characters and then call the setLength method with the number 7, meaning we're truncating the string builder text value to 7 characters. And we see the result of that, goodbye spelled backwards. This video ends our first section on object-oriented programming with a review of one of the most used classes in Java, the string, and its mutable version, string builder. We use strings very often, but the string builder class is often a better choice when creating and manipulating text. In the next section, we'll be covering other object-oriented features such as composition and polymorphism, and we'll talk in more detail about encapsulation. Congratulations on completing this first section, and I'll see you in the next section. Welcome to Section 8 of the course. Tim Buchaka here again, and as promised, this is part 2 of the object-oriented programming sections of the course. We've now covered the basics of object-oriented programming in the previous section, but it's now time to look at the remaining 3 major components of object-oriented programming. These are composition, polymorphism, and also encapsulation. By the end of this section, you should have a solid overview of what these concepts are and also how to apply them to your programs. Let's make a start on that right now. In the previous set of videos, we had a discussion about and learnt about inheritance. It's time now to talk about composition. Composition is another component of object-oriented programming and is very useful in day-to-day programming. But as a refresher, I want to review another inheritance example before we move into composition. Let's say we're interested in building a computer and we want to assemble it. All the parts are manufacturer's products which we have to buy and assemble to sell our final product the personal computer. Next, we'll look at a class diagram of some computer products or computer parts. In this instance, we have a base class called product, and all of our computer parts are going to inherit from product. All our parts will then have the same set of attributes, a manufacturer and model, and dimensions, the width, height, and depth in other words. All of these items are products, a particular type of product. Personal computer, monitor, motherboard, and computer case are but a few parts or products you can think of that would be sold by a computer distributor. Okay, let's build this. I've created a project called Computer Factory with the usual main class and main method. Next, let's create the product class. We'll select New Java class and create a new class called Product. And we'll start adding the attributes. Private string model semicolon. Private string manufacturer semicolon. Private int width semicolon. Private int height semicolon. Private int depth semicolon. And we'll add a constructor, but let's only include the model and manufacturer in the constructor for simplicity. We'll select code, generate constructor, and select the first two attributes. Okay, we now have our base class, and next let's create a couple of the subclasses. We'll add them all in the same Java source file as the product.java file. Remember, only one class can be public, so we'll omit the access modifier for these classes. We'll start with monitor. For monitor to be a subclass of product, we have to add extends product. Class monitor extends product opening curly brace. Closing curly brace. And we'll generate the constructor, so selecting code, generate constructor, which should insert the two attribute constructor mirroring products constructor. Okay, that's our first subclass. Let's copy and paste that class to create our second class. We'll rename the method name and the constructor changing monitor to motherboard. And finally, let's create computer case the same way. We'll copy the motherboard class and paste it, renaming the class and constructor to computer case. Okay, so our three classes all extend product. We can say now that monitor has gotten is a relationship with product, meaning that a monitor can be said to be a type of product. And that's the relationship between the two classes. And we can quite correctly say that all three of these parts, monitor, motherboard, and computer case, are all types of product. And that's essentially what inheritance is. Inheritance defines it as a relationship. Composition defines it as a relationship. Next, let's look at how we'd use composition to create a personal computer. To keep this diagram simple, I'm showing only that personal computer inherits from product, but remember all of our classes are really subclasses of product. But a personal computer, in addition to being a product, is actually made up of other parts. This diagram shows that a computer has a motherboard, a case, and a monitor. The motherboard, the computer case, and the monitor are computers, not in the same sense that they are products. So that's what composition is. It's actually modeling parts, and those parts make up a greater whole. In this case, we're going to model the personal computer, and we're modeling that has a relationship with the motherboard, the case, and the monitor. And we've already created the parts, but we didn't really make them different from each other. Now we'll look at another diagram that shows these classes with some state and behavior specific to their product type. This diagram shows the three classes that will make up the personal computer. We'll have size and resolution for the monitor, and we'll want a method called drawPixelAt, so the monitor has behavior to draw. For the computer case, we'll have a power supply and a method press power button. And for the motherboard, we'll have slots for RAM and cards, as well as a BIOS attribute and a method called load program. Getting back to the code, let's add these members to our parts. We'll start with the motherboard and add the three attributes first. Private int RAM slots semicolon. Private int card slots semicolon. Private string BIOS semicolon. And next we want to generate another constructor which takes these three attributes but also calls a super constructor. Positioning the cursor below the first constructor, we can select Code, Generate, Constructor, and select all attributes. And that will give us another constructor. Okay, and now we've also said this class will have one method called loadProgram. We'll add that as a public method with one parameter, the program name, and we'll just print text out in this method. Public void loadProgram, opening parentheses, string, program name, closing parentheses, opening curly brace. System.out.println, opening parentheses, double quotes, program, plus, program name, plus, double quotes, is now loading dot, closing parentheses, semicolon, closing curly brace. That's our motherboard class, pretty straightforward as you can see, with nothing particularly complicated there. Now let's move on to our monitor class and add those fields, size and resolution. Private int size, semicolon. Private string resolution, semicolon. And again, we'll add another constructor. Setting the cursor after the first constructor, we can select Code, Generate, Constructor, and pick the two new attributes. Okay, so now we have the fields and the constructors. What we're going to do here next is create a public method called drawPixelAt, and it's going to have an X and Y location and a color. We want to use string.format, which we learned to do in the last section. And we'll just print a simple message out. Public void drawPixelAt, opening parentheses, int X, comma, int Y, comma, string, color, closing parentheses, opening curly brace. System.out.println, opening parentheses, string.format, opening parentheses. Double quotes, drawing pixel at %d, comma, %d in color %s, comma, x, comma, y, comma, color, close both parentheses, semicolon, closing curly brace. And that completes the monitor class. Finally, let's finish computer case, which we've said has a power supply in one method, press power button, so we'll have the power supply field. Private string, power supply, semicolon. And placing the cursor below the first constructor, select Code, Generate, Constructor, and pick that power supply field. And now we just want to create a method called press power button. And we're just going to add a simple print line that says power button pressed. Public void press power button, opening and closing parentheses, opening curly brace. System.out.println, opening parentheses, double quotes, power button pressed, closing parentheses, semicolon, closing curly brace. Now that we have all of our parts done, it's time to build the computer. This is the fun part where we actually create a class that's comprised of the computer case, the monitor, and the motherboard. We want to create another new public class. New Java class, and type in personal computer. And the first thing we want to do is add extends product to this class too. Even though our personal computer has a bunch of parts, it's still a product with all of product's attributes. You can use a combination of inheritance and composition to create your model as we're doing here. And this class won't compile until we have a constructor, but let's wait to do that until after we've added our attributes. Let's look at our personal computer class diagram again. This will be our personal computer, and we've said it inherits from product, which we've already done with the extend statement. But it also has three fields, which are classes. These are monitor, motherboard, and computer case. Let's build this personal computer class now using composition, which means we'll add three attributes. Private computer case, semicolon. Private monitor, semicolon. Private motherboard, semicolon. And you can see the obvious advantage here, because if you're using the extends option to inherit, Java only lets you inherit from one class at a time. You could see that we'd run into difficulties and limitations quite quickly if our only tool was inheritance. In this case, what we've said is the personal computer consists of these three other classes, namely the computer case, the monitor, and the motherboard. Before we do anything else, we should add a constructor. You can see IntelliJ isn't happy with us because we haven't done that yet. Positioning the cursor after the last attribute will again select code, generate, constructor, and all three attributes. And that gives us a constructor. And for this class, we do want to add some getter methods for these attributes. And we do that by positioning the cursor after the constructor. Then we can select code, generate, getter, and select all three of the attributes. And we get three getter methods. Okay, that's our personal computer. We've described what we want to assemble. I'm going to end this video here. In the next video, we'll actually assemble the parts together and we'll look at how to access the functionality of the parts through the personal computer container. I'll see you in the next video. In the previous video, we started talking about composition and compared it to inheritance. We've said that inheritance is a way to reuse functionality and attributes. In contrast, composition is a way to make the combination of classes act like a single coherent object. In the last video, we stopped right after we created the classes for the parts, but we hadn't yet put all the parts together. In this video, we need to assemble the personal computer. Now it's time to run some code and see how we'd use this in reality. Going back to the main class and the main method, let's start creating some objects. So first we'll create an object of type computer case. We'll create a Dell 2208 case and it will have a 240 power supply. Computer case, the case equals new computer case, opening parentheses, double quotes, 2208, comma, double quotes, Dell, comma, double quotes, 240, closing parentheses, semicolon. Okay, that's our definition for a computer case now. Remembering that when we create the personal computer, which we're going to be doing shortly, it needs this reference. PCs generally can't be put together without a case, so what we're doing here is creating that case. Next, we need to create a monitor. This time we'll say it's an Acer 27-inch beast, so we'll pass in the size and the resolution of 2540 by 1440. Monitor, the monitor equals new monitor, opening parentheses, double quotes, 27-inch beast, comma, double quotes, Acer, comma. 27, comma, double quotes, 2540 x 1440, closing parentheses, semicolon. We've now got a case and a monitor that ultimately are going to be used to create our PC. Of course, we now need a motherboard. And we'll make this an Asus BJ200 model. We also need the number of RAM slots, which we'll say is 4. And the number of card slots, let's just say there's 6. And the BIOS, let's say it's version v2.44. Motherboard, the motherboard equals new motherboard, opening parentheses, double quotes, BJ200, comma, double quotes, Asus, comma. 4, comma, 6, comma, double quotes, v2.44, closing parentheses, semicolon. Okay, that gives us our motherboard. And now that we've got all our parts, we can put our personal computer together. We've created instances of a monitor class, a motherboard class, and a computer case class, and it's time to build this and see what we can do with it. The personal computer will have the same manufacturer and model as the computer case, so 2208 is the model, then Dell is the manufacturer, and then we'll pass the other variables to the personal computer. Personal computer, the PC, equals new personal computer, opening parentheses, double quotes, 2208, comma, double quotes, Dell, comma. The case, comma, the monitor, comma, the motherboard, closing parentheses, semicolon. And you can see that here we've created the PC object by passing those three other objects to it, as well as the model and manufacturer. In previous videos, with inheritance, we were able to use a method from the base class. But how do we get access to a composite object's methods? In other words, how do we make it do anything? Well, we can do this by telling one of its parts to do something. For example, if we want to draw something using the monitor, how do we access this method? We have the method drawPixelAt on monitor, but how do we access that? Well, we can get the personal computer's monitor object using the getter method and then call drawPixelAt on that object. So let's do that. The pc.getMonitor, opening and closing parentheses, .drawPixelAt, opening parentheses, 10, 10, double quotes, red, closing parentheses, semicolon. That's one way of executing functionality by using the getter method from personal computer to get the instance of the monitor class that the personal computer contains. In this code, from that returned object, we're chaining the call to the method drawPixelAt, and that's invoking that method for us. Likewise, we could call the method loadProgram on the motherboard, passing it Windows OS, for example, as the program we want to run. The pc.getMotherboard, opening and closing parentheses, .loadProgram, opening parentheses, double quotes, Windows OS, closing parentheses, semicolon. We're doing the same thing here. We're getting the motherboard object that's been created and that personal computer has a reference to with the variable motherboard. And we use a getter method to get that reference, then execute a method on that. Lastly, let's do that with the next method, the press power button on the computer case. The pc.getComputerCase, opening and closing parentheses, .press power button, opening and closing parentheses, semicolon. Here, in all three cases, we're ultimately accessing functions in other classes, the case, the motherboard and the monitor, but we're accessing them through the PC object. This is what composition is. This is the difference from inheritance. What we did to call the PC object was we created our case, our monitor, and our motherboard. And in reality, when you're putting a computer together, that's what you'd be doing. You'd buy the computer case, you'd buy the monitor, and you'd buy the motherboard, and you'd then put it together to build the PC. We built this personal computer by passing objects, the parts, to the constructor, which essentially is like assembling the computer. Let's continue on now and look at another scenario whereby we can actually hide the functionality further. In this case, we're not going to allow the calling program to access those objects, the parts, directly. We don't want anybody to access the monitor, motherboard, or computer case directly. What we'll do first is we'll go to our personal computer class and we'll comment out all the getter methods. You'll remember this encapsulates these attributes, it hides them from the calling code. And just to go back and show you what happened, we're now getting an error because those methods no longer exist. We really don't want the main class or any class except the personal computer class to make calls on its parts. Okay, so next, let's create methods on personal computer which we'll expose to the calling code. The first one we'll call drawLogo, and we're going to implement that in a private method. And it might do some fancy graphics, but here we're obviously not going to write that code yet. Instead, we'll just call drawPixelAt on the monitor attribute of our computer. We're making this private because the only code we want to draw the computer manufacturer logo is the personal computer itself. Private, void, drawLogo, opening and closing parentheses, opening curly brace. Monitor.drawPixelAt, opening parentheses, 1200, 50, double quotes, yellow, closing parentheses, semicolon, closing curly brace. Next, we want to call this method from a method we'll call PowerUp. If you think about a computer, when it starts up, you press the power button and then you see a logo come up on the screen. Public, void, PowerUp, opening and closing parentheses, opening curly brace. Computer case.press power button, opening and closing parentheses, semicolon. drawLogo, opening and closing parentheses, semicolon. Closing curly brace. Here, we've got a public method called PowerUp and a private function called drawLogo. The PowerUp function of the personal computer will draw that logo on the screen as part of starting up the computer. And now, going back to the main class, we'll comment out the 3 lines that I'm compiling. Instead, we'll make a call to the PowerUp method on the personal computer. The pc.PowerUp, opening and closing parentheses, semicolon. And now if we run that, we get the result that the power button was pressed and then drawing pixel at 1200, 50 in color yellow. From the calling code's perspective, this code in main didn't have to know anything about personal computer's parts to get the PC to do something. composition is actually creating objects within objects. It's like creating a master object. In this case, the personal computer is managing and looking after all its parts, and it uses composition to achieve that. In future videos, we'll continue to give you examples of both inheritance and composition and what goes into deciding which to use. As a general rule, when you're designing your programs in Java, you probably want to look at composition first. If you do any sort of research on the internet, most of the experts will tell you that as a rule, look at using composition before implementing inheritance. You saw in this example, we actually used both. All of our products, the parts that made up the finished product, and the finished product itself were able to inherit a set of attributes like the manufacturer and model. And the calling code didn't have to know anything about these parts to get personal computer to do something. It was able to tell the personal computer to power up, and the personal computer delegated that work to its parts. The reasons composition is preferred over inheritance. Composition is more flexible. You can add parts in or remove them, and these changes are less likely to have a downstream effect. Composition provides functional reuse outside of the class hierarchy, meaning classes can share attributes and behavior by having similar components instead of inheriting functionality from a parent or base class. Java's inheritance breaks encapsulation because subclasses may need direct access to a parent state or behavior. We showed you an example of using the protected access modifier in a previous video, and we'll talk about why this breaks encapsulation in the next videos on encapsulation. Inheritance is less flexible. Adding a class to or removing a class from a class hierarchy may impact all subclasses from that point. In addition, a new subclass may not need all the functionality or attributes of its parent class, and therefore adding the subclass will muddy the waters, meaning the model no longer represents the reality in the code. Let's say we want to include digital products like software products in our product inventory. Should digital product inherit from product? Here we show the model with digital product inheriting from our current definition of product. If we do this, this should mean digital product has products attributes, but this isn't true now. A digital product wouldn't really have width, height, and depth, so this model isn't a good representation of what we want to build. It would be better if we didn't have those three attributes on product, but instead use composition to include them on certain products, but not all products. Now, consider this revised class diagram. We haven't completely removed the class hierarchy, but we've made the base class, product, less specific or more generic. We've removed the width, height, and depth attributes from product and made a new class, dimensions, with those attributes. And we've added an attribute to motherboard, which is dimensions, which has those attributes. So what do you think? Is this a better model? Well, it's more flexible. This design allows for future enhancements to be made, like the addition of the subclass digital product, without causing problems for existing code that may already be extending product. By pulling width, height, and depth into a dimension class, we can use composition to apply those attributes to any product, as we did here with motherboard, but we're not requiring that all subclasses be defined with those attributes. This is just one example of the inflexibility of inheritance compared to a more flexible design with composition. Now that you've seen some examples of composition in action, it's challenge time. I'll see you in the next video for that challenge. Welcome to the composition challenge. In this challenge, you need to create an application for controlling a smart kitchen. Your smart kitchen will have several appliances. Your appliances will be Internet of Things, IoT, devices, which can be programmed. For example, you might do stuff in your kitchen in the morning in a rush to get to work and then expect your smart kitchen appliances to run automatically at a later time. It's your job to write the code to enable your smart kitchen application to execute certain jobs. Methods on your smart kitchen class will determine what work needs to be done. Add water will set the coffee makers has work to do field to true. Pour milk will also set refrigerators has work to do to true. And finally, load dishwasher will set the has work to do flag to true on that appliance. To execute the work needed to be done by the appliances, you'll implement this in two ways. First, your application will access each appliance by using a getter and execute a method. The appliance methods are order food on refrigerator, do dishes on dishwasher, and brew coffee on Coffee Maker. These methods should check the has work to do flag, and if true, print a message out about what work is being done. Second, your application won't access the appliances directly. It should call Do Kitchen Work, which delegates the work to any of its appliances. Okay, go ahead and do that. Write code that represents the smart kitchen and see what you can come back with. You'll have to create the appliances as classes with their own methods, as I've shown you on the diagram, and then compose your smart kitchen with these appliances. And when you're ready, come back and check out my solution. Pause the video now, and I'll see you back shortly. Okay, hopefully you managed to figure that out and you had some fun along the way. Let's go ahead and now implement one possible scenario. I've already created a new project called Composition Challenge and created the usual main class and main method. Now the first thing we'll do is create the Smart Kitchen class. We can expand the project panel, right-click on the SRC folder, New, Java Class, and type in Smart Kitchen. And we'll let the attributes, even though we haven't created the individual appliance classes yet. Private, Coffee Maker, Brewmaster, semicolon. Private, Refrigerator, Icebox, semicolon. Private, Dishwasher, Dishwasher, semicolon. Okay, that's not going to compile until we create these classes. And we're just going to add these classes in this same source file. After the last closing class bracket, we'll type in the code for the Coffee Maker class. Now, we could have had all of our appliances inherit from a base class. Maybe you did that, and that would be one valid way to do this. For simplicity, I'm not going to include inheritance in my solution, and this means my appliances won't be extending any class other than the implied one object. Okay, we know Coffee Maker needs one attribute, has work to do, a boolean. Class, Coffee Maker, opening curly brace. Private, boolean, has work to do, semicolon. Closing curly brace. And we'll use IntelliJ's code generation tool to add the setter method for this boolean flag. Placing our cursor after that attribute on line 12, we can select code, generate, setter, and we'll pick the has work to do field. And that creates the setter. And now we'll add the method we want to run if there's work to do. For the Coffee Maker appliance, this is the brew coffee method. And first we'll make sure there's work to do by checking the attribute has work to do. If that's true, we'll just print the text, bring coffee, and set has work to do to false after. Public, void, brew coffee, opening and closing parentheses, opening curly brace. If opening parentheses has work to do, closing parentheses, opening curly brace. System.out.println, opening parentheses, double quotes, bring coffee, closing parentheses, semicolon. Has work to do equals false, semicolon. Closing curly brace. Closing curly brace. Okay, that's the Coffee Maker class. Now we'll just copy and paste that entire class and we'll rename it to Refrigerator. And we'll change the method name from brew coffee to order food. And then we want to change the text in the println statement to say ordering food this time. And finally, for the last appliance, we'll paste the Coffee Maker class again. We'll rename it this time to Dishwasher. We'll change the method name from brew coffee to do dishes. And we'll change the text being printed to washing dishes. Okay, now that we have our three appliances, we can get back to the Smart Kitchen class, which we can see now compiles. Next, we want to add a constructor. When we create a new Smart Kitchen, we're just going to instantiate our own set of appliances by creating our own no-arguments constructor. This means that any code creating a Smart Kitchen won't have to create the appliances individually like we did with the personal computer example in the previous video. In this case, we're saying the kitchen comes with a standard set of appliances when it's created. Public Smart Kitchen, opening and closing parentheses, opening curly brace. Brewmaster equals new Coffee Maker, opening and closing parentheses, semicolon. Icebox equals new Refrigerator, opening and closing parentheses, semicolon. dishwasher equals new dishwasher, opening and closing parentheses, semicolon, closing curly brace. And now let's generate the getters, placing our cursor after that constructor, and then select code, generate, getter, and pick all three attributes. And that does it for the Smart Kitchen. Now, let's go back to the main class, main method. We'll create a new instance of a Smart Kitchen. And then we'll use the getter methods to call specific methods on the appliances we know in the kitchen. Smart Kitchen, kitchen, equals new Smart Kitchen, opening and closing parentheses, semicolon. Kitchen.getDishwasher, opening and closing parentheses, .doDishes, opening and closing parentheses, semicolon. Kitchen.getIcebox, opening and closing parentheses, .orderFood, opening and closing parentheses, semicolon. Kitchen.getBrewmaster, opening and closing parentheses, .brewcoffee, opening and closing parentheses, semicolon. Okay, that's the setup. If we run that though, we're not going to get any output. That's because all the methods expect that the has work to do flag on the appliance to be set somehow. Before these appliances can be ready to do something, we want to put a dish in the dishwasher, use up some products in the fridge, or put water and coffee grounds in the coffee maker, for example. We'll use the getter methods on kitchen to emulate that work first to set some of these appliances into a state of readiness. Kitchen.getDishwasher, opening and closing parentheses, .set has work to do, opening parentheses, true, closing parentheses, semicolon. Kitchen.getIcebox, opening and closing parentheses, .set has work to do, opening parentheses, true, closing parentheses, semicolon. Kitchen.getBrewmaster, opening and closing parentheses, .set has work to do, opening parentheses, true, closing parentheses, semicolon. Now, we've done some stuff in the kitchen, and our appliances are aware of work to be done. And we've also called each appliance individually to do the work on each. Running this code, we can see that our smart appliances ran, they washed dishes, ordered food, and brewed the coffee. That was calling methods outside of the kitchen with code that is aware of the different appliances in the kitchen. We use the get methods to call methods on specific parts of the kitchen. Now, let's create two more methods on Smart Kitchen that hide some of the details from the calling code. We'll just give the calling code a method to pass some Boolean flags to our kitchen, and if the kitchen has a smart appliance that cares about that flag, we'll set that flag. Public, void, set kitchen state, opening parentheses, Boolean, coffee flag, comma, Boolean, fridge flag, comma. Boolean, dishwasher flag, closing parentheses, opening curly brace. Brewmaster.set has work to do, opening parentheses, coffee flag, closing parentheses, semicolon. Icebox.set has work to do, opening parentheses, fridge flag, closing parentheses, semicolon. Dishwasher.set has work to do, opening parentheses, dishwasher flag, closing parentheses, semicolon. Closing curly brace. Okay, here we have a single method that can set some of the appliances has work to do Boolean flag property. Now, let's create a method on Smart Kitchen called doKitchenWork. This method hides what work will be done from the calling code, which doesn't really care about all the individual work items. And we want to add this method, which calls each appliance's method that does the work. Public, void, doKitchenWork, opening and closing parentheses, opening curly brace. Brewmaster.brewcoffee, opening and closing parentheses, semicolon. Icebox.orderFood, opening and closing parentheses, semicolon. Dishwasher.doDishes, opening and closing parentheses, semicolon. Closing curly brace. Okay, now going back to the main method, we'll comment out the code that sets the state on each appliance and then calls each appliance's work method. And we'll instead call the one method on kitchen to set some of the appliances' readiness state. This time, we'll just set work to be done on the coffee maker and dishwasher. Lastly, we'll call the doKitchenWork method. Kitchen.setKitchenState, opening parentheses, true, comma, false, comma, true, closing parentheses, semicolon. Kitchen.doKitchenWork, opening and closing parentheses, semicolon. And if we run that code, because we only said there was work for the coffee maker and dishwasher, we see that those appliances do their bit of work. You can see the output, brewing coffee and washing dishes. If our smart kitchen added or removed appliances, or their types changed, the method do kitchen work could still be called the same way from the calling code. This means that Smart Kitchen can manage all its appliances and their inner workings, simplifying what the calling code needs to know and do. Hopefully you can see that composition is very, very powerful. As we progress through this course, you'll see examples of composition, and as I mentioned earlier, you'll understand more where to use inheritance and where to use composition. Generally, a lot of object-oriented programming experts suggest you try to aim to use composition over inheritance, or to at least look at that first. Hopefully you did well on your challenge. In the next video, we're going to talk more about encapsulation, which is another component of object-oriented programming. I'm going to explain that in more detail in the next video, so let's move on.
This video is over. Go to starfreelance.eu to download these videos, materials, and sources. Watch more videos to get premium videos and ebooks. We'll be a Starfreelancer.